So today I'm going to talk about hardware architectures for lossless compression. This is primarily my research work from my PhD dissertation, which I filed a couple of months ago. Currently, I work for Meta, but today's talk will be primarily on my PhD research work. So the outline of the talk going to be, first I'll talk about the background of this research, and then I'll talk about the motivation behind this research, followed by the canonical Huffman encoders, and then the decoders, and then the gzip encoder. And finally, I'll talk about a tool, which is called D-Scale tool. With that, I will conclude my talk. So I know I have 25 minutes, so I'll try to touch base as much as possible. So without further delay, let's dive into the background of this research. So here we have three plots. The first one is talking about how much data surge due to COVID-19 back in 2020 itself. So due to COVID-19, we saw like a 47% global data surge, right? And then I'm talking about the data center, how much energy they consume. And the estimate is that by 2030, it will be 9K terawatt hour. And finally, from the economic point of view, the data compression market is $4.5 billion by 2026. So here we are looking at three different things. One is talking about we have huge amount of data. The second one is saying, okay, if you want to store those data, then this is how much energy our data center is going to consume. And the third one is saying we have a huge market for this data compression, right? So before diving much into the technical details, what is the data compression? So data compression here, you can see that we have two files. The input is basically the uncompressed file, and the size is 100 kb. And then we have the compressed file where the size is 50 kb. We have a metric here, which is compression ratio, that decides how well is the compression, right? So a compression ratio of 2 says that the compressed file size is 50 kb, down to 50 kb from the uncompressed file, which is 100 kb. Now, there are two types of data compression. You can look at either lossless or the lossy compression. In case of lossless, we are looking at basically where the data fidelity is restored. So we are looking at bank records or text articles or the software codes. There we can't lose any information, right? But imagine you have some video like the one currently I'm presenting. If there are 5 pixels not there, it's still okay. Like we can still retrieve the information. So that's basically the lossy compression. So in case of lossless compression, here we are looking at the original data and then the compressed data by compression. And after the decompression, we're looking at the decompressed data. All the values are exactly same as the input data, right? That's the lossless compression. There is no loss of information. But then, as I said, in case of lossy compression, you can have some pixels here and there, that in case of video, image, or in case of audio, some bytes here and there, still it's okay, right? So that is basically for the visual and multimedia data. Now, Huffman encoder is one of the most famous lossless compression technique, right? So this is primarily from, if you took algorithm 101 in your undergrad, then this algorithm is there, Huffman encoding, right? So you have a stream of symbols. You are trying to find the histogram of symbol and frequency here. And then after that, you are sorting these symbols based on the non-decreasing order of their frequency, right? So once we have that, the next step is basically how you can build this Huffman tree. So building Huffman tree is basically you're trying to find the two lowest symbols, the symbols with the lowest frequencies, and then you add them up. That will give you the new intermediate node. And then you take either symbol from the original list and the new node, or you can take both from the actual original list. And by that, basically you are reaching at the root node, which is the final generated node, that is 37 here in this example. So here, in case of normal Huffman encoding, what we do is that for the code assignment, we just give 0 to the left side of the tree, and then the 1 for the right side of the tree. So basically, the left node is getting 0, the right node is getting 1. So by that, if I have to encode this symbol, so for B, basically, I had to traverse all the way from root to leaf nodes, and that is basically 0, 0, 0, 0. So that's why B is encoded as 0000. Similarly, you can find whatever the encodings for rest of the symbols. But here, imagine if you want to decode it at the receiver end, then this tree has to be there, right? So in case of normal Huffman encoder, you have to send the encoded bits at the same time you have to send a huge Huffman tree, right? So can you eliminate that requirement? So to eliminate that requirement, basically we are going for canonical way of assigning code word, right? So until this point, it's okay, like Huffman tree is there. Now, instead of traversing this whole tree, can we assign the codes to the symbols without traversing this tree, right? So for that, what we are doing is we are adapting some mathematical formula. And by that, we're doing the canonical coding assignment, right? So we have to group the symbols based on their code length. And once the first code word is assigned, the rest of the symbols, they are basically getting code word plus one. Like here you can see that A is getting 00 and then D is getting 01 for the symbol 2 for these two symbols with code length of 2, right? Similarly, once we have B, which is the first symbol with the code length of 4, once that is assigned 1110, then the next one is basically 1111. So it's just the plus one, right? So here in this case, once we have this mathematical thing known to the receiver, then we don't need to send this Huffman tree to the receiver end, right? So by that, basically we are reducing the computational complexity. At the same time, we are reducing the memory footprint, right? So in both like performance and area, we are speeding up by adapting the canonical Huffman encoder. So if you look at the literature, so the idea here is that when you create the canonical Huffman encoder, so the first step is to create this tree, right? The Huffman tree. And you don't need to do resorting at every stage of generating this Huffman tree, right? So if I have this B and F symbols initially, then I have this new generated node 4. But again, I don't need to sort this whole list again. Imagine sorting is a very computationally intensive task. And imagine if you have 512 symbols or more, right? So you don't need to resort at every stage of the Huffman tree. So to eradicate that, we can have like two memories, basically. You can say block RAMs, and then one, you are storing basically the new nodes with their frequency, and then one with the original symbols with their frequency. In this way, we are making sure that whatever the generated node, that frequency will be always higher than this previous one at the original list of symbol and frequency. So this idea was proposed by Matai in ICPP. Now here, if we look at, okay, how about getting the code length and the code word after designing this Huffman tree? So that was part of the research, which I'll describe later. Now, in case of decoder, the idea is that once you have the encoded bits from the encoder, can you design that lookup table, which can index the encoded bit stream? And based on that, you can output the decoded symbol, right? So decoder is, this is the decompression part. So I won't spend more time here. If you want to learn more, then you can refer to this paper here. Now, in case of decoder, again, like the related work is one of the most recent work where it says that you can have synchronization technique. And by that, you can have n number of threads running in parallel. And those basically will make sure that you can have n number of threads running in parallel. And then that will give us the parallel decoding, right? So that's a related work. But again, you can refer to our most recent paper to know how the decoding is done. So for the research motivation, basically the first task we are looking at is how we can speed up the canonical Huffman encoding despite having such serial bottleneck, right? We saw like one step after. First, you have to sort it out, then you have to generate the Huffman tree, then you have to assign the code word, right? So if that is the data path, then how you can speed it up, right? So that is the first question we are asking here. And then the second question we are trying to answer is the decoder architectures, can we optimize for performance and energy efficiency? And finally, the LG77 compression and also the Huffman compression, which makes the G-chip compression. Can we discuss about the static and dynamic part of both the compression techniques? Because dynamic one will be slower than static compression, but this will give us better compression ratio. So there is a trade-off there, right? So All these techniques we are trying to evaluate on these platforms. So the first one is basically a many core processor array, which is known as kilocore, which was designed in our research group and fabricated. Running at 1.2 gigahertz, it's basically a single die with 1,000 processors and 12 memory blocks there at 0.9 volt. That's the frequency, 1.2 gigahertz. And then we also implemented this for FPGA, Intel Max 10, then the EPIC 45 nanometer CPU, and also the GPU. So basically a comprehensive analysis of all these techniques and all the implementations across these computing platforms. And for the benchmarks, these are the most famous benchmarks for lossless compression, the corpus dataset. So those we took for our evaluation for the benchmarking purpose. Now let's look at the encoder, right? The canonical Huffman encoder. If we look at the hardware thing, so first you want to compute the histogram, right? So if I have like 512 symbols, I want to say like what is the frequency of each symbol? You can say that, okay, take maybe 512 max, and then each of the the 512 accumulators, and each of the accumulator will contain like how many numbers of that symbols are there. But this is serial, right? So can we do it in parallel to speed up the operation? For that, what we can do is that we can do the block level, we can partition the input data, and then the input symbols we can do all in parallel for each histogram block. And finally, we can accumulate those data and store it in a RAM, right? So instead of doing it in serially, we are doing it in parallel. And by that, we are speeding up the data path operation. For the sorting, imagine like doing the sorting one by one in serially. Can we do something like intra-block and the inter-block sorting? So this is what we are going to propose in one of the manuscripts, which is currently under preparation. So here, basically, you can see that the unsorted list is here. So what I can do is that I can find like, okay, first do sorting for this sub-block. And then in the second stage, I can do the inter-block sorting. So finally, that will give me the smallest frequency, right? And this is just a block diagram of like the comparator we are using here. Can I do it like the like a level comparators, basically the multi-level comparators instead of a single level comparator here. So by that, basically the critical path is down, right? So these are some of the approaches you can consider to speed up your data path for the encoder side. Now, another critical thing here is that how to find the code length for each of the symbols, right? So for each of the symbols, what I can do is that I can say that, okay, I need to traverse the tree from the root to the leaf node. So for that, then basically I have to have memory elements. And then for each memory elements, I should have some reference for each node, what are the parent nodes. And from that pointer, I need to traverse all the way from 37 down to 17, 17 down to 8, 8 to 4, 4 to B. So this is all like iterative approach, and this will hurt your performance like anything, right? So instead of that, can we have something like the concurrent approach, which we are proposing here, is that once you try to build the Huffman tree at the same time, you can say at what level the nodes are there. And from that level, you can directly compute the code length instead of doing it iteratively after building the whole tree, right? So in the left-hand side, you can see the iterative approach, where first you are trying to build the tree, then you are traversing from the root to the leaf nodes. And finally, you are saying, okay, so this is what my code length for this symbol, and similarly for rest of the symbols. So instead of that, what we are doing is concurrent approach, which will speed up your whole operation here. And also it will save some area and energy. So the details I'm not sharing here. So this is still under preparation. But the idea here is that we have to get rid of this serial bottleneck here and the iterative approach here, which hurts the performance. So next is the kilocore processor array, where we implemented it as the first implementation. So this processor array is, as I said, once you have the die, on the same die, you have 1,000 processors, and then 12 memory elements, each 64 KB of memory. And you can see that each of the processor, you have the DMEM, data mem, instruction memory, oscillators, FIFOs, and circuit switch for the networking, router for transporting your data, and all the FIFO for the CDC and to talk to the next core in the processor, right? So here, this is the mapping of the encoder. This basically says like how the tasks are distributed among the processors. And once we have the input, basically the first thing is histogram can be run it in parallel. And then the same thing is the sorting, and then how to store these left and right nodes. And finally, to find the chord length. Again, the algorithm is already defined, which I just discussed. So the idea here is that you just need to map the whole task to this array of processors. And finally, one of the processors will give you the encoded bit stream. So this is basically after the place and route of the kilocore mapping. So you can see here, only using 66 processors and 3 64 KB memories, the whole encoder is mapped to the processor array, right? So all these have been verified on those benchmarks that I discussed earlier. And these are basically the 64 KB memories on the bottom. And these are the array of processors on the top. So this is just the placement and route tool, which was designed in our research group for our processor chip. And similarly, the cycle accurate simulators and also the compilers have been designed in the group. And that we use, and this is almost 99.99% matches with the RTL, what you can design for ASIC or FPGA. So if you look at the results here, I only put only one slide here. Again, this work is the paper is under preparation, and we are sharing only the results with the two most recent papers. And here you can see that in the x-axis, we have throughput per area, and in the y-axis, we have normalized compressed bits per energy. So basically, one is talking about the performance, and the other one is talking about the energy efficiency. So, and at the same time, you want your implementation to be farthest than the origin, right? So basically, the kilocore is here, and then these two implementations, which are the state-of-the-art implementations on a very high-end NVIDIA GPUs. So you want like much more throughput per area. At the same time, you want the normalized compressed bits per energy, which should be higher, right? So this is the result scaled to 32 nanometer, because as I said, like there are different implementations on different technology node. So to basically have a fair comparison, we have scaled the results to 32 nanometer, which is the technology node for the kilocore. Now let's talk about the decoder. Just one slide, because primarily this talk is on compression. So the decoder is, once we have the header information from the encoder, then we are trying to build this lookup table. And there are a few phases of building this code table. Once we have the code table, then basically we are hashing the encoded bit stream, and that's giving us the decoded symbols, right? So we are reading the bit stream, and the first one is saying, okay, so the 1 we are reading, and that's giving us D. Similarly, the next one is giving us B. So this is the serial approach. But then in this paper, basically we have shown like how you can speed up the whole process. You don't need to do this serial thing, and also how you can design this code table, like the optimized lookup table based decoding. So you can refer that. Again, like this is part of decompression. Now let's dive into the GZIP encoder. So in case of Huffman encoding, we saw it's a bit level encoder, right? So we are trying to compress at the bit level based on the probability distribution. So how about a multi-stage compressor where we can have better compression ratio than the Huffman encoder? So the GZIP encoder is basically, the first stage is LG77, and then the second stage is Huffman, right? You can have either static Huffman compression or dynamic Huffman compression. The static compression is basically the code table is fixed. So then basically you are losing at the compression ratio side, but because the code table is fixed for any data set, then the encoding time is very small, right? But the dynamic compression is on the fly, you are trying to design the code table, and at the same time you're encoding the data set, right? So that's why the dynamic code table will take more time. The dynamic compression will take more time, but at the same time, you'll get the best ever compression ratio. So we are looking at two compressors here. The first one is byte level compression, which is called LG77, followed by Huffman compression, which can be static or dynamic. As I said, the first one is doing byte level compression, and the second one is doing bit level compression. So if we look at the architecture for GZIP, the first one is basically you have some parallel number of bytes as the input. And then you have some hash function to find out, okay, where is the match in the previous window, right? Because we are doing byte level compression. So we are reading each bytes and we are saying, okay, was this byte previously there? Then I don't need to again send it to the receiver. I can just send a pointer to the earlier data and that will take care of it, right? So that's the whole idea of the byte level compression. Now, after the hash level update here, we are doing the string matching. So if you have like a bigger string match, then of course that will result in less number of bytes to be sent to the receiver or as the output of the encoder, right? So once we have the string match, and then basically we have to select one of those match. And after that, we are doing the canonical hop and encoding of the bytes, right? So the first stage is doing byte level compression. We are looking at where was the similarity of these inputs previously in a hashing window. And then we are trying to compress that and we are sending it to the canonical Huffman encoder, which does the next thing, which is bit level compression. So here we can see that it's a sliding window architecture. So basically, these are the previous data. Let's say that my current pointer is here, which is pointing to C, A, and then B as the current data to be hashed. So based on your hardware architecture, you can do how many bytes in parallel. Of course, for that, your storage has to be, I mean, it all depends on your PPA goals, like the power, performance, and area goals, but you can do parallel bytes matching. So you can look at, okay, CAB is there. So similarly here, let's say there are 4 dictionaries which are storing the previous data, right? So here I have PWS bytes equal to 4. So the first one is saying PREV, and then basically we are looking at the next substring, which is REVC, and then EVCA, like that, right? So every cycle we are reading 4 bytes of data. So that's why there are 4 dictionaries and we're looking at 4 bytes in parallel. Based on that, we'll find what is the best match length among all these substrings. So we are looking at the static canonical Hopman encoder. As I said, that the static codes, they are fixed. So basically here, the compression ratio will be less than the dynamic canonical Hopman encoder. Once we have the packets from the LG77, then based on that, we are sending this bit stream. And for the encoded bit stream, there is a format, how many literal codes you can send, followed by the length distance code, and then followed by the distance, and that will take care of how many bits you want for your hardware architecture. These are just saying how many pipeline stages are used, and those are by these bars. You can see here 4 stages, but it's a deep pipeline, not just 4 stages. But again, you can just decide based on your PPA goals. But the idea here is that it's a static canonical Hopman encoder. So basically the encoded part from the canonical Hopman will be fetched. Now, this is the implementation results from ASIC for the GZIP. Again, this is the paper is under preparation, and these are the results in terms of throughput and energy efficiency. As you can see, as I said, like static GZIP will definitely be a lot more faster than the dynamic GZIP. At the same time, we are looking at like the throughput here. You can see that it's almost 5 times the throughput of dynamic GZIP for 4 different benchmarks. And these are basically the energy we are spending, like the number of compressed bits per microjoule. And of course, like the static one, you can have more number of compressed bits per microjoule because you are not doing anything, is just a lookup table indexing. But the dynamic one, you are every time on the fly, you are trying to see what is the encoder output, right? So that's why the energy efficiency will be poorer than the static one. So finally, I'll talk about disk scale tool quickly. So the idea here is that, I mean, this is again back to VLSI 101. So we all learned like what is Dennett scaling, what is Moore's law. And then we saw that, okay, once we tried to squeeze down all these parameters, when we wanted the transistors to be smaller and smaller. So basically the device dimension can go all the way 1/k. K is the scaling factor, voltage 1/k. But again, we are looking at the deep scale submicron. After the 2003, you saw the power wall, right? So we can't do the voltage scaling. At the same time, the leakage is a big problem. And also there are like, you cannot have the dark silicon is there, the leakage power is another problem. And then also the power, like for that much power, can you have a heat sink? So all these factors to like the maximum clock frequency we see these days for the processors, right? Yes, we can design some accelerators for certain functionalities to accelerate the performance, but the general purpose computing, you see these processors, I mean, like 3.3 gigahertz to maybe 4 or 5 gigahertz, but we didn't see that 5 scaling factors. The idea for this tool is basically when we compare some of the results, one thing is in, let's say 32 nanometer, the other results are basically in some, let's say 14 nanometer or 7 nanometer. So can we do a fair comparison? So for that, the deep scale tool was modeled based on some of the scaling data for the available technology nodes, and then you can interpolate for rest of the nodes. The idea here is that this is basically an Excel sheet, and you can download the tool here. So here in this photo, you can see that the current node is 130. You need to give the values for the nodes. What is the current node and what is the target node? And that will, these buttons, once we press it, then that will give us the scaling factors. So the first one, if you press, that will give us the scaling factors for area. So if you want to scale down the results from 130 nanometer down to 45 nanometer, this is 8.3. Okay, and the delay is like 2.4. Imagine 130 down to 45 nanometer, 2.4. Not like every node we are getting twice faster, right? So this is based on the deep submicron data. So the current data. So this is just for a fair comparison of different results. And that's how the tool, and then you can read more about this tool from this paper, and you can download the tool here for your comparisons. Now here you can see that one of the plots from this paper is that the first one is saying, okay, these are the relative values, and this is the technology nodes in x-axis, right? So we are saying that 130 nanometer down to 7 nanometer, how the scaling trends looks like for area, delay, or throughput, or all these metrics. At the same time, look at this percentage variation in the estimated scaling versus the traditional scaling. So the traditional scaling here, I refer to the Dennard scaling, right? There is a huge error in case of delay, energy, and power and throughput, right? Of course, like we didn't go in that train, which was proposed back in 1970s. And so that's why we see like a very big difference here for the lower nodes, especially for 7 nanometer, 10 nanometer, right? So that's the basis of this tool, and these are the results from that tool. And that's all about the scale tool for today. So now to conclude my talk, basically I gave an overview of some of the research areas in terms of compression. And here we talked about canonical Huffman encoders, decoders, and the GZIP compression. We talked about the throughput and energy per byte in terms of performance and energy efficiency. And then also we talked about different platforms where these were implemented, ASIC, FPGA, many core processor, or a GPU or CPU. And finally, I concluded with the deep scale tool, which is a tool for a fair comparison in deep submicron technologies. So with that, I will conclude my talk. And I would also like to wish all of you a very happy holidays and happy new year. And again, thank you so much to all the organizers for inviting me. And I can take any questions from the audience. Thank you.
So now we'll move on to the next speaker. So our next speaker is Dr. Souvik Kundu. He's a member of IEEE, and he received his PhD degree in electrical engineering at the University of Southern California, Los Angeles, California. He also holds 2 master's degrees in VLSI and computer science from USC and IIT Kharagpur. He has been the recipient of prestigious Enabler Fellowship, PhD Achievement Award for his department, and Order de Arete Award from the graduate school during his tenure at USC. His research primarily focuses on the algorithm architecture co-design for energy efficient and trustworthy machine learning for complex computer vision and multimodal applications. His interdisciplinary research has been published in various top-tier venues, including in Nature, NeuroIPS, ICCV, WACV, DATE, ASP DAC, ICSSP, and IEEE TC. Souvik serves as a TPC member and editorial board member in various conferences. He is currently working as a research scientist at Intel Labs in USA. So now I request Dr. Kundu to deliver his talk.
Hi, Sudhakar. Thanks for the kind introduction and thanks for having me. Yeah, so today I'll be discussing a summary topic of some of my PhD research and some of the research that I have been doing at Intel for around 6 months now. And I would like to, this discussion should be interactive. So if anyone has any question, feel free to pause me. I'll also try to pause myself in the middle. So the discussion is regarding challenges and opportunities in edge deployment of deep neural networks at scale, a hardware-inspired algorithmic approach. As Sudhakar has already mentioned, I'm Souvik Kundu. I am currently working as a research scientist at Intel. So I hope the presentation mode is fine, right? Just to confirm.
Yes.
Okay.
Yes, absolutely fine.
Okay. Yeah. So we are actually currently standing at a very interesting juncture of hardware algorithm co-design. And I think this is one of the most important time where we really need to inspire hardware design driven by algorithmic motivations. So if we see how the deep neural network is evolving over last 4 or 5 years, even when I started my PhD, during that time, the deep neural network models are growing like linearly. And it was not that challenging to deploy these models during that time because Moore's law was also growing in quite close to linearly. Now, what happened in last 3 years or 4 years, the DNN algorithm and model, they have exploded. So there has been a new development of transformer models, which are growing like around 240 times every 2 years. That means currently the existing transformer models are having 175 billion parameters, which is nearly impossible to hold in any hardware without enabling distributed computing. Then there are vision transformers, which are also growing like around 10x every year. Whereas the GPU or the TPU memory, due to slowdown of the Moore's law, is growing around 2x every 2 years. And if we try to deploy this kind of DNN models into edge devices like mobile phones or drones or autonomous driving, and there are many applications where we would like to deploy this on edge for agricultural purpose, for business purpose, for our personal day-to-day use purpose, and for military purposes, we get even constrained because those resource constrained devices, they don't have luxury of large memory or large compute power, right? So there the memory is around 10 to the power 4 times less compared to server memories. This creates additional problem because the model size is growing around 240 times a year, whereas the memory space is growing around 2 times a year only at max. Apart from that, the issue of energy budget and the storage, there is another concerning issue is robustness, because we want to use AI mostly everywhere. And many of those applications are extremely sensitive towards the end user choice. For example, autonomous driving, it is a safety critical application. There is another growing concern, which is privacy. India, US, these countries are really bothered about the way data is being used by the service provider. For example, Amazon, Google, how the data is being used after collecting from the user. So privacy is a concern. So it is becoming a challenge of having a resource constrained deployment while we are also trying to improve the robustness of the model so that we can safely, trustworthily use these DNN models for various applications like medical, autonomous driving. And also we want to use this with a notion of privacy. That means we want to use the data, but we do not want to actually disclose the model or the original user of the data, right? So in that context, I would like to highlight some of the summary topics and relevant publications in these areas. So we are trying to deal with the robustness issue of the models while also trying to deploy the energy efficiency because we want to use it on the edge. And then we are also trying to look into the privacy aspect of these kind of energy efficient models that I term as opportunity, because I will highlight few of the privacy concerns that we have recently published associated to deep learning models. But as the first one, which is associated to robustness, they are more like challenges. So that's why I have termed this talk as challenges and opportunities. So it will touch upon both the challenges that we are facing and the opportunities associated to those challenges. So having said this, I will start discussing on the robustness of the energy efficient model. What do we mean by robustness? Robustness is associated to the fact that when a deep learning model is trained on to classify a specific set of tasks, it somehow fails to do so. And one of the major reasons for which it fails to do so is the perturbation on the image, or is the perturbation on the model itself. So this kind of robustness issue can have a fatal consequence, particularly when, for example, we are using such classification model for autonomous driving. If the classification output is not the correct one, then the model can actually enforce the device to do something that is not expected. And this kind of robustness issue can also be as a result of natural occurring perturbations. For example, I have trained a deep neural network model on a sunny day in Bangalore. However, the model is currently deployed on a cloudy or a foggy winter morning in Bangalore. So though the road condition and the pictures were like new or was used by the model, but the current situation of the contrast and brightness has changed because of the weather situation. So these kind of issues can have a fatal impact, and there are various kinds of other ways to perturb the original model's data to actually fool the model. Now, why dealing with robustness while also having model energy efficiency is critical? Because when we try to make the model robust against such noisy perturbations or naturally occurring cloudy conditions, the model try to overfit, and most of the model weights tend to be non-zero. So when we try to train a deep neural network model with most of the parameters trying to be non-zero, it becomes very hard to design an energy efficient version of that, because the baseline principle of having an energy efficient model is to have most of the parameter as zero. Then only we can get rid of most of the computation and save computation as well as memory. However, the existing literature that we have surveyed during that time, they try to solve this issue with around 9 times more costlier solution of training, which actually prohibits our basic purpose of energy efficient deployment. Because if a training is around 9 times more costlier, it becomes excessively hard or in sometimes impossible to deploy such model on battery driven devices, for example, drones. So in that context, we are the first to actually explore a unified, robust pruning approach, which tries to compress the model in the context of the importance of the weights based on both robustness as well as model's own original input. So I think in the last talk, we have got some familiarity with the data compression. So here we are trying to focus at model compression, where the data can be perturbed as well as normal. And in that context, there are various ways to prune a model. So there has been extensive work in this domain of literature. However, we have particularly chosen both structured and unstructured way of model parameter reduction, so that we can have wide range of benefit when we try to deploy this kind of model on the edge devices. And there are various proxies to do so. So we have relied on magnitude and gradient, and we have chosen to do one-shot approach of model reduction because it will help us get rid of the most of the iterative training cost, saving huge amount of carbon footprint during training. Now, this is an overview of the way we have proposed our new form of model compression, which also adheres to the model robustness. Now, as we need to deal with both clean and this kind of adversarially perturbed images during test time, we try to feed both the variants during training as well by perturbing the training image. And then we try to choose and rank the layers based on the importance of those layers towards the final classification performance. And when we complete our ranking of the layers, we try to assign the weights and the non-zero parameters based on those importance of the layers. So we will assign more weights or non-zero parameters to the layers that are more important, and assign less weights or parameters, non-zero parameters that are less important. In that way, we can actually retain the model performance, while we can also adhere to the model energy efficiency for its deployment at the edge. I have summarized the loss function with which we have tried to optimize this specific neural network. The details of this training procedure is mentioned in this paper. And in this paper, we have also shown that we can actually have a significant amount of latency advantage due to the channel pruning, because number of channels present in a deep neural network layer directly contributes to the latency. So as we can reduce the number of channels, we can actually significantly reduce the latency, while we can retain the model performance up to around 10x less parameter. Now, having said that, there is another concern associated to model robustness, is when we train a model to be robust against diverse set of situations, then the model's original performance on the original dataset reduces. This is a fundamental limitation of deep neural network that we recently solved by proposing a new form of conditional learning. For the sake of time, I am skipping one of the existing approach, which also tried to solve this based on feature-wise linear modulation. However, the existing solution had significant amount of limitation. For example, the existing solution has excessive latency overhead as well as memory overhead. Whereas we are the first to solve this problem in a way that does not have any additional latency overhead, because we try to create a model that works on various kinds of scenario, for example, sunny day, cloudy day, night, or we have trained a model in a desert-like environment. Now we are using the model in, for example, in southern part of India, and we should not face any problem. So under those kind of circumstances, if the solution requires excessive latency over it, then basically we are limiting our application to non-real-time situation. However, the irony is most of the cases where we need such robustness requires real-time application. So this is the first solution of literature that actually provided a real-time solution while also having robustness. So we have actually essentially relied on a weight condition learning. This is the first to propose a weight condition learning to actually provide model robustness as well as clean image performance. The original network architecture and training details is presented in the specific paper. Readers can refer to this paper for details. We have also proposed a gradual transition between a very clear situation to a very noisy and robust situation. So if the user is not sure that under which condition he or she should use this specific model, we have actually proposed a switch with which the user can gradually transition between a very clean image-based classification to a very noisy image-based classification. So this is a complete power given to the user, whoever is using this end device. And we have also outperformed the existing state of the art by around 1.43 times faster GPU hyperparameter condition. That means our model can not only perform better compared to the existing approaches, but also they can perform faster. They can train faster, they can do inference faster, they require much less parameter compared to whatever is available in the literature. And also they generalize better on various kind of changing environmental condition, which is a huge bottleneck for deep neural network deployment at scale. So with this, I will try to pause for a bit and ask if there is any question. Okay. So,
Kamal here. Can you hear us?
yeah, I can hear you. I think, yeah, you can ask question. If I cannot, then I can ask, I think, Pradyut, because Pradyut has a mic.
I'm holding mic. So the question around, your kind of literature and the backgrounds of this work. Let's say you mentioned one of the stars that how to, optimizing the model or efficiency, increasing the efficiency of the model in terms of carbon footprint. Right.
Right.
You're not able to hear us?
Yeah, I can hear you. Yes. Optimizing the model in terms of carbon footprint, right?
Yeah. So
Yeah.
do you have any guidance or how to compute the carbon footprint of operating platform?
Yeah, that is a good question, actually. Yeah. So there are few published works that actually try to directly compute the carbon footprint associated to a neural network training. For example, when we try to train a neural network, there is associated floating point operations. So to compute a single forward pass, there is a set of floating point operation. For example, for ResNet 50, the floating point operation is around 6.6 billion. So for one forward pass, if it requires 0.6 billion floating point operation, then for a single floating point operation in, for example, 48 nanometer technology, we can actually evaluate what is the energy associated to that, right? Now, if we can have the result of energy computed for 0.6 billion floating point operation, then we know what is the power consumption associated to one forward pass of a deep neural network. And when we have that data in our hand, we now know how much carbon emission is necessary to generate that power. So from that, actually, we can backtrack that how much carbon emission is actually happening to train your deep neural network model, because it is consuming a certain amount of floating point operation. Does that make sense?
Yes, actually, thank you for clarifying it. Then other question around the same thing is, you are doing the model compression, right? That also has carbon footprint associated with it, right? So is there, net is benefit of doing the model operations? Of course, when you are doing model compression, you are using some operations, maybe that also to take consideration, right?
Yeah, but the thing is that if to do model compression, if we make the compression approach as an iterative approach, then we end up having more carbon emission. But if the compression approach is non-iterative, like what we proposed, is one shot, that means we do only one single set of forward passes to perform the model compression. That essentially means that we are not adding any extra overhead to do the model compression. It is same energy consumption as we need for a normal training. So to do compression, we do not end up having additional carbon emission. We just end up having same carbon emission that is necessary to do a standard training. But during inference, we require around 10 times less carbon emission because our model is already compressed.
Yeah, absolutely makes sense. Thanks.
Okay. Yeah, and if you have any further questions, you can reach out to me or you can refer to this paper as well. But those are interesting questions. Thank you.
Thank you.
Yeah. So with that, I will go to the other aspect of our real-time deployment of deep neural network model, which is a growing concern because of the national limitations and national issues, national securities, which is the privacy. Now here I will touch base on a different aspect of privacy, which is the model privacy. Why model privacy is extremely important? Because currently very new companies are coming up which are trying to use machine learning as a service. they train a model on large corpus of data, and then they provide us as a service. For example, I think everyone knows now about ChatGPT. ChatGPT can do anything. ChatGPT can write our SOP. ChatGPT can write our proposals as well. It can write our resume. But ChatGPT is a pre-trained model. And obviously, OpenAI, who actually released ChatGPT, they want to protect the IP of the model because that can act as a source of income for these companies, right? Because this black box API model, they hold training information of large corpus of data, which is not available to public. So they want to protect the model as an IP. Under that circumstances, we can think of a very easy way to actually steal the information of the model via knowledge distillation. Knowledge distillation is a way where we try to replicate the information of a model to another model. This has become a significant issue. So there is a very well-known conference called ICLR. There is a paper in that conference which proposed how we can actually stop such stealing of model information. And they name this kind of model as undistillable models. So they are saying that if you train your model in their way, then your model's IP is protected because no one can steal your model's information. No one can steal your data information on which the model is trained. However, we are the very first group who actually identified that there is a flaw in identifying or protecting the model IP. The original paper has passed the transferability test of protecting the model IP, but the original paper did not test on a new kind of test that we proposed, which is the depth test. That means we can transfer the knowledge at various depths of a deep neural network. We can transfer the knowledge after first layer or after second layer or after third layer. And the depth test shows clearly that this kind of protected model IP, they significantly fail when we try to transfer the knowledge to a shallower depth. That means if we try to transfer the knowledge after the first layer, there I get a huge success in copying the information. Based on this understanding, in NeurIPS 2021, we have proposed a new form of knowledge distillation with a new form of student. Student means a student model, and we term this as a skeptical student. Why skeptical student? Because these are some kind of deep neural network models which can steal the information of any protected IP model by transferring the knowledge to its shallower depth. And to improve their performance further, we have also proposed a form of self-distillation. Like a model is trying to steal the information, then it is trying to understand what out of those stolen information is useful with the help of this self-distillation. And to train such model, we have proposed a new loss, which is relying on necessarily three different components. First one is the KL divergence component, which is like trying to differentiate between how soft logic based distillation we can copy from the original model that is IP protected. The second component is a self-distillation component, which is more like I am now evaluating my own copied information and trying to get rid of the useless component. The third part is the cross entropy loss, which is generally used in every deep neural network training. So with this, we have shown successfully that we can actually steal any IP protected model. That raises the question that really, can we protect the model or the data under the circumstances of privacy guarantee? As per this paper, it looks like we cannot. And we have also shown various kinds of visualization that why we can successfully copy the information, because we can largely get rid of the noisy clustering that this kind of model IP is trying to provide us. So how a model tries to protect itself? It tries to create a noise in the output cluster. And from that noisy cluster, it becomes very hard to extract the original information. However, we have successfully shown that when we use our training technique, the noisy cluster is largely mitigated. That means now the cluster is not noisy at all. There are different cluster information associated to different classes. And that's why we get huge success in getting the performance. And also we can get rid of the noisy output logic distribution, which is actually directly affecting the probability. In our scenario, there is no such noisy output logic distribution at all. That means we are also not getting any issue from the probability. So with this, we can actually term that the issue of privacy of this kind of deep neural network model is still prevalent, and we need to rethink how we can use this machine learning as a service while protecting our IP. And I'd be happy to take questions on this front as well.
Thank you, Shobhit. It was really a wonderful talk to understand what's happening on the model compressions and to be part of the most talked AI and deep learning models. Thanks for it.
Thank you, Shobhit. Probably we'll connect
Yes,
later.
here are two questions. I'm just sending over the microphone.
There is no question right now. We will connect later, Shobhit.
Okay.
Or we'll discuss about this later.
Thank you.
So, Shobhit, thanks a lot. So our next speaker, though he does not need any introduction from me, but let me read his, some of the current roles. So, Pradipta Batra is currently leading the system and application team in EPIC Group and the technical director, Samsung Semiconductor India Research. His team is responsible for post-critical validation for Samsung mobile wearable SoC EMIC and formulating new EMIC architectures for various applications. He has around 15 years of post-PhD industry experience on power management, architecture, design, modeling, and solution. Prior to moving to Samsung SSR, India, Pradipta worked as an R&D engineer in Samsung Research. Samsung Electronics Korea, where he was responsible for design, developing, and prototyping the futuristic EMIC architecture. Before that, he worked with the Intel India as an EMIC architect and was responsible for the architecture and development of physical synthesizable LDO. Pradipta Batra has a PhD in electrical engineering from IIT Kharagpur. Throughout his academic and professional journey, he has numerous international patents, journal and conference on this level. So, without any time delay, the floor is yours, Pradipta. PD, sir.
Thank you for the warm welcome, and it is a good opportunity to be presenting in this conference for this good university. This I would without any much of introduction, I would like to directly jump into the presentation. I think we don't have much time on that. So can I share, Pratyut?
Yes, you can share.
Yeah, sure. Thank you. Is it visible now?
Yes, it is visible.
Thank you. So this talk is primarily about power management for mobile applications. But having said that, I would try to come to power management for mobile from a bit more top level approach, and then show the diverse options that power management in today's scenario or today's applications it exposes to. This is not a session where I will be explaining the design details, but I would be more elaborating on the breadth so that aspirants can feel comfortable and feel more enthusiastic in, or maybe understand the real life challenges in this kind of domain. So moving on. So what is power management actually? So when we talk of power management, whatsoever be the application, whether it is a consumer application, it is a high power solar application, or we primarily have an input source and then we try to generate a fixed DC or AC supply without any variation. Now, whether the source is an AC or DC, there can always be fluctuations. So we cannot have a direct connection directly. So what we place in between is a converter. I will get into the converter, but let us assume it to be a box where there can be anything. There can be switches, there can be controllers, anything. Why we need a controller is that from the input, a varying input, we will go to a steady state output, where the output will, irrespective of the input fluctuations, the output will stand constant under whatever be the conditions, whether the load that is being pulled increases or reduces, the input fluctuates based on the voltage. The regulator blocks should always continuously define a fixed supply. So as I mentioned, I will start it from a top-down approach. So voltage conversion can be in different formats. It can be DC to DC, DC to AC, AC to DC, or AC to AC. So we can have power management boxes in any of these conversions. So power converters, if you consider DC to DC, we can consider cell phones as one of the examples. Then the DC to AC, we can have inverters. We can have various other applications as well. These are a few which are mentioned. Now, if you look at industrial terminology, power management, people confuse a bit between two separate things, which I would like to highlight here. One is power optimization, like you have a processor or an SoC, where there can be various digital circuits, there can be various analog circuits, like there can be a processor, there can be a camera, there can be sensors. There also power optimization is required. People sometimes call it power management. When I say power optimization, it is based on how to channel the power properly, or how to shut down applications, or how to do power gating. Those kind of things belong to the power optimization category. So this talk is more into power management, where we take power from a source and then generate a fixed voltage for the SoC. So that includes, as I mentioned, all the converters, all the various sorts of converters. When we talk of mobile applications, it will be only DC to DC, and with the DC source being a battery only, a lithium-ion battery. And apart from that, there will be another battery management aspect. So when we talk of battery management, there are various features. I'll come to it one by one. But battery management means how to handle the battery problem. Any question?
So there is a question. Please continue.
I'm hearing a lot of echo. Any questions, or should I continue?
Continue. Yeah, please continue.
Okay, thank you. So I'll move on to the next slide. We'll be focusing on power management, as I mentioned. So let's have a holistic feature of the whole thing. So there are a lot of people, a lot of companies. The previous talk was very, very detailed and very fundamental. I would look at, being an industry person, I would like to give more opening to what industry is doing, how much is its exposure, or what is the future growth in this particular domain. So there are various companies that are working. I did not mention Samsung here because I don't want to get into copyright issues, but yeah, Samsung too does, apart from a lot other companies that are mentioned here. So if you look at a market share, it's close to 30 billion right now, and it is moving forward towards 50 billion in about 10 years time, with about 5.1 CAGR from 2022 to 2031. So that, which means it is a fixed market, means a fixed growing market. When I say fixed growing, it is continually growing. And why do you think it is growing? Means whatever applications you use with 5G, with 6G coming into picture, and I was reading a survey some time back, there was the number of end users who would be using mobiles in the coming days would cross billions. So with this kind of growth, any applications you drive, just because we are talking of cell phones, with any cell phone applications you drive, you need PMICs. So the number of phones grow, the number of PMICs grow. It's a very simple, straightforward approach. So even if some application doesn't work, some improvisation, some innovation doesn't work in other areas, it is definitely a growing sector in PMICs. As I mentioned, the growth in this market is a steady and it will remain constant, irrespective of other domains or other areas. Of course, there are definitely other booming areas. I am not trying to demean that, but what I want to specify here that this is a standard growth area. And for a large cap company kind of thing, I think this is a fairly good CAGR. 5% of CAGR for a large cap sector is a really good amount. I would put it that way. And the biggest thing is that power management circuits are mostly analog design based. Of course, there are digital controls, there are digital circuits which interact with the interfaces between them. But it is a more analog specific thing. If you look at India, I think there is a wide opening here for analog engineers. We have analog engineers, but there is always scarcity in this. Even if you look worldwide, I think analog engineers are always in the demand, and power management being mostly analog driven, the requirement, the need for the analog circuit designers would always be there. Talking of coming 10 years in the least. So this is another area where I wanted to highlight a bit, like what are the power domains, defining on the current requirements and the voltage requirement and based on the performance. So if you look at of course when you put at mobile, IoT, MCU, these would come into the first blue oval, where the current requirements would be less. Of course, CPU performance compared to the high power servers would be definitely lesser. So rather it should be placed it like this, where you have a wearable device. So wearable device would be on the lower sector. Then you have automotive dashboard kind of applications. And the automotive dashboard, and within that mobile sector can also come into play. So those are medium kind of there, where the power requirements would be medium. When I say power requirements are medium, you can consider it as 20 to 50 watt at max, not beyond that. And if you go to higher sectors which are servers, networks, those would be like 200 watts or 300 watts. I am not going to even higher power sectors where there can be DC to AC kind of, which is the high tension lines and all those. But in medium to low power segments, this is the broad horizon where you can categorize different things. So this talk is primarily focused on the medium to low power applications, where I'm talking of wearable devices, IoTs, and consumer mobile applications. Please stop me anywhere if you have questions. Moving on to the next one. Now, what are the primary challenges? The primary challenges are, as you scale down in digital applications, you can with the reducing technology, you can definitely scale down. But the problem with this kind of sector is that you cannot scale down drastically or dramatically. To scale down, you have just because it has inductors and parasitics. So to scale down, you have to increase the frequency. So once you increase the frequency, the losses would be increasing. So conduction loss versus leakage and the switching losses, we have to find a sweet spot for it. So it cannot be scaled down like other technologies or other analog or digital circuits, where it can be scaled down directly. Of course, leakage matters there as well. But here it is a fundamental problem where we try to compromise between switching and conduction losses. So we are kind of limited with scaling down the device sizes. Okay, so this is kind of a block diagram where we if you look at a motherboard of a single mobile phone, you can find that there will be an SoC primarily in standard mobile phones. I am not categorizing or not specifying on any particular thing, but in general there will be an SoC, and you can find maybe one or two PMIC chips. So what the PMIC chips do, when I talk of PMIC is a power management IC. So there will be PMICs which will be driving the various rails. So one SoC may require about around 10 supply rails of various voltages and various current levels based on the different applications that are being driven in the SoC. So more than one PMICs are also possible in any mobile applications. If you look at it, this is the left side block is kind of a block diagram of one PMIC towards the left one. So what we have in a PMIC block PMIC chip, you will have apart from the some standard analog cells which we call as housekeeping cells. There can be voltage references, there can be band gaps, there can be controller circuits. Apart from that, you will find switch regulators. I will not categorize directly. Let us consider regulators first. DC to DC, where you have the input as battery to a lithium cell battery, 2.7 to 5 around 5 volts lithium cell battery input, and then there will be which will be generating the different outputs, and then you will have the battery charger circuit as well. So these are the primary blocks which will be there in a PMIC thing, which will be supplying to various applications in the SoC. So to categorize a bit more, on the right side you can see a battery. Every block you can figure out that there can be different. Now let me categorize a bit on the different kinds of switching on the regulators. Now we have switching regulators and we have linear regulators. I will differentiate those, but normally high frequency applications and very sensitive applications, let's say RF circuits, they would be driven by linear regulators, which linear regulators have a fairly cleaner supply because they don't use switches. Switching regulators will be operating in a very high frequency thing, so they are given to provided to memories, digital circuits, digital applications like those kind of things. So and which requires high current kind of thing. So they are categorized. So one PMIC can have maybe 10 or 20 bucks. It can also have maybe 20 or 30 LDOs. I'm talking of present day mobile applications. Again, there will be 2 or 3 PMICs of that sort. So in total, there can be about 40 bucks and maybe about 70 LDOs if you look at any standard mobile what you have in today's date. So that is how we categorize it, and then there will be a digital circuit apart from the housekeeping circuit. What does the digital circuit do? The digital circuit actually maintains a relationship between the two between the switching converters, the battery management, and the SoC when it needs to be grown up, and how it needs to be turned on, turned off based on the application, based on what the requirements are. This I will skip for the timing. I'll move on to the next one, and then we'll control back on that. So this is ideally a linear regulator. So the linear regulator, what we do is we have an R1. R1 is actually a resistor. It is actually a resistor divider. The R1 is actually the switch which controls the output voltage and regulates the output voltage through the controller. So how the switch, the resistor is actually replaced by a switch, and then it is controlled by a controller. So what does the switch do? It operates in a saturation zone, and then the The gate is actually controlled by a bias voltage, which is defined by a controller. Now the controller can be different. It can be various sorts of controller, which we can have a holistic view, but the primary difference is the primary thing that I wanted to point is that we have a fixed input voltage and we control the only one switch and we generate a fixed output. So you can see there is no switching involved here. We just switch on the switch partially or fully based on what the output voltage is required. So it's just a resistance drop across the switch. So the output is fairly clean. That's the philosophy of a linear regulator. As I mentioned, linear regulators are used for supplying very, very sensitive circuits like RF or sensors. And this is the concept of the switching regulator. So when we talk of switching regulator, there can be various types of switching regulator. Switching regulators can be in buck, where the input voltage is higher and the output voltage is lower. So we step down, and if it is if you have to step up, then it is a boost. All the configurations depend on how you place the switches, where you place the switches, and how you operate it. There can be another switching converter which is buck boost. These three types are mostly used in mobile applications. So we actually operate the switch. We turn the switch on and off based on the controller feedback from the output, and the duty cycle of the switch, how much percentage is on, generates what will be the output voltage. So that the controller is defines the duty cycle, and that defines the output voltage, and it is based on the different regulations. So now, talking of all this, I have talked about so many switching, so many converters, so many different things. What is the challenge area? Now, based on, as I skipped that slide, that was that showed that what could be a load step, or say you suddenly open an application which demands a very high current. Okay, now the converter has to, if you increase the current suddenly, then the output voltage would suddenly drop. It would drop very drastically. Now you have to control that. You cannot let that voltage drop. If that voltage drops, then the power will shut down for the SOC. That is the challenge where industry is moving into, and they are using various types of control to control this. So this picture actually shows a basic and a fundamental block diagram of a voltage mode control, how things are operated in a very fundamental thing. So we have the voltage feedback, we use a compensation, we compare it across a sawtooth ramp, and then we use some logics to drive the power switches. Now this is a voltage mode control, and it has its own limitations. The bandwidth and all those limitations are there. Now based on the application, what are the load current profile for the SOC? Based on that, we tend to change the controller and the switching converter also. So why change the controller? To generate the performance. So there can be different types of control. There can be current mode control, there can be adaptive on-time control, there can be resonant control, there can be various types of control. I don't want to get into it, but what in this short amount of time I would want to specify that the fundamental challenge is to optimize this controller and to make it based more real-time specific. Like if you can have an AI-based thing where you can predict what the SOC is demanding, and you can adapt the controller based on that. Adaptive on-time control kind of does that a bit, but if you can do that, and a lot of innovations are happening on this zone. So if you can do that, then you can improvise on your performance. And the second is the change in the switching converters. Say you have two buck converters in parallel. Two buck converters will have 4 switches, 2 inductors, and then 2 capacitors in output. Instead, if you can club them and make it a single inductor double output, then you improvise on the form factor. So that these kind of improvisations industry looks forward to. They do work on it, and they while staying a little bit focused on maintaining the without disturbing the output voltages. And this is a typical layout. What we do. This is only about one switching converter. If you broaden it, there will be we will have a switching converter zone, we will have a LDO zone, we will have a digital zone, and then we will have a connectivity zone, housekeeping zones as well. So in this, I just want to focus on how to place and how to optimally place so that the heating and the current are uniformly distributed, so that there are no burnouts in any of the metal layers or anywhere. I think I would like to control and ask more questions from you. I kind of tried to run through it. I probably could explain more on controllers, but I would ask like you to ask a few more questions on this.
And before going to I just want to understand is the layout, optimization of this layout. Does this happen through tools or it's manual? How to do all this?
As I mentioned, power managements are mostly analog. There is only a small digital section. So analog layout is still manual. It's not optimized yet. And digital part is synthesized. Yes, only the digital part, which is about 10 to 20% of the whole unit.
Okay. Some questions from. Is there any scope thermal optimization also?
Yeah, please go ahead.
Yeah, I was seeing how you are managing the thermal optimization.
Yeah, so means the manual layout do take care of thermal optimization. We follow, means we have some thumb rules where to place which power MOS, which and to how to place the buck converters, how to place the LDOs, which converter is drawing how much of current. Based on that, we optimize it. And as you know, probably analog design layout is more of an experience. You do it over time and then you gain that experience. So that is how you do the means thermally you optimize the thermal thing.
Are there any question? Have any question? Okay, so if you don't have any question, then we want to thank you, Dr. Patra, for your time and coming and talking to us. And yeah.
Yeah, thank you so much. I tried to hurry you through it. If you have any other questions later on, also you are means please feel free to contact me, and I would be more than happy to answer you. So yeah, and I would expect more and more people from colleges, from universities to jump into this sector so that we have more resources and more knowledgeable persons in this zone.
Yeah, hopefully student finds it interesting and they will connect with you. Let us give a big round of applause. With that, we are closing the session.
Yeah, thank you so much.
Let us start the panel discussion. I would like to first invite Dr. Rajkumar Ilagiri to start the session by giving a brief introduction. We have with us a distinguished engineer from Dell Technologies, and along with us, we have research scientist from IBM Research Lab. And we have our associate professor, Dr. Ramakrishnan from the Department of Electronics and Communication Engineering. And myself, Dr. Pradut Kumar Sanki from the same department. So I would like to request Dr. Rajkumar Yalagiri to give a brief introduction, and then we will start this panel discussion.
Yeah, thank you all. Thanks for the opportunity. I'm Dr. Rajkumar, currently with EPIC Semiconductors, located at Bangalore as well as in Coimbatore. Previously, I was with IIT Madras as a Chief Information Officer, and before that, I was with Bosch Bangalore, particularly the head office, Koramangala office, as a senior architect. And I have a 25 years of experience, and I did my PhD in electromagnetics in France. That is my brief intro. Hello.
I would request Dr. Somu Maiti from Dell Technologies to introduce.
Hi, am I audible?
Yes, you're audible.
Hi, this is Dr. Maiti, and I work in Dell as a distinguished engineer. And I look after the product and application security for Dell. And I have I lead a team that does penetration testing as well as security development lifecycle and a lot of different other stuff. So I'm more into the other part of the domain where we mostly look into the cyber security and information security as well as CTS, cyber physical system security.
Okay, thank you. I would like to request Dr. Kamal Das to introduce in the panel.
Hi everyone, myself Kamal Das, and I actually work in IBM Research India in Delhi location. We do have a couple of labs in India, one in Bangalore, one in Delhi. So, by profession I'm a mathematician, but I try to use mathematical knowledge to solve some real world problems like last 7 or 8 years, we try to use remote sensing data, AI and physics-based model to compute soil moisture, soil nutrient that can help climate model as well as for agriculture applications. So we do use a lot of sensor data. It can be the image or it can be the signal from the on-ground sensor for driving different analytics. And joining this conference, I learned that there are various doing on semiconductor and different parts of building this devices. And I'm happy to participate and learn more about this industry. Thank you.
Okay, thank you very much. Sir, actually, we want what will be that future of the semiconductor. Am I audible, sir? So we want from you what will be the future of that our student, those who are studying BTech in our university and even in India, what will be their prospect, future prospect, and what are the opportunities that are available in the semiconductor industry, and whether our students would able to work on this hardware or these simulation on software. So what will be the challenges, opportunities, if you could just highlight. And then some of our students also joined here, they would able to learn a lot of things from you.
Is it addressed to who?
Students. It is addressed to students.
No. The professors point to address to Rajkumar or somebody else. That is the point I'm.
Question
is from. Yes, sir. It is from. Partly, we would like to listen from the EPIC Semiconductor, because it is that company is related to semiconductor. And,
yeah, Ramakrishnan sir can start and then I'll join. Or that's the reason I asked whom this question has been posed on.
Okay, sir.
Yeah, thing is, as far as semiconductors are concerned, my background is on embedded systems. I worked on embedded systems for 10 years in industry. So I will be talking about my embedded system perspective. As far as embedded systems are concerned, if the students are having knowledge on microcontrollers and digital circuit design, and if they are able to write a C program for microcontrollers like ARM microcontrollers, definitely they will have a better opportunity to get into embedded industry. Of course, they need to have hardware, schematic design. So the schematic design, they have to learn there are lots of various EDA tools are available for learning embedded, learning embedded hardware design, schematic design, and PCB design. So as far as the hardware is concerned, the students should concentrate on a single. I think ARCAD is a industry accepted tool. ARCAD and Altium people are using widely in industry for hardware design. And as far as the firmware design is concerned, and for ARM, we'll be using the tools Scale and IAR. These are all the tools which are widely used in industry. And as far as open source thing is concerned, if students are learning about embedded Linux, then the prospect to get into embedded industry is more. So as far as software is concerned, they need to know embedded C and embedded C++ programming. So this two programming, if they know C and C++, embedded C and embedded C++, so they can do better. They can get better opportunities. And industry, I haven't seen anybody using Arduino or other Raspberry Pi kind of tools in the industry. At least in mainstream industries, not. So it's better if the students concentrate on embedded C and embedded C++ and embedded Linux. And as far as microcontrollers, there are we can categorize the embedded systems into two categories. One is low-level embedded systems, which are based on microcontrollers, and another one is high-level embedded systems, which uses operating systems like embedded Linux or any other advanced real-time operating systems. So this comes into the category of high-level embedded systems, where we'll have embedded processors with MMUs, memory management units. So students, I think BTech students, they can restrict themselves with low-level embedded systems, and if they have mastered that, then probably they can concentrate on learning this high-level embedded systems, which are designed by using embedded processors and operating systems. So if they want to know operating systems, definitely they need to. So embedded programmers should be like a mix of electronics engineer and computer engineer. So the students needs to have these skills. So they need to be good at programming. And yeah, embedded. That's. I hope I have answered the questions, at least for the embedded systems. That's it from my side. Thanks.
Hey. Dr. Jam, could you please introduce yourself first?
Yeah. So can you hear me?
Yes, right.
Yes, you are audible.
Okay. So I am Ravindra, assistant professor at IIT Guwahati in Electronics and Electrical Engineering Department. My specialization is in solid state devices, and I basically work on resistive sensors and mainly optimization of sensors for various gases. Yeah.
Okay. So now let us come back to this the same question again. What will be the future prospect of semiconductor industry, and what will be the opportunity of our students, those who are studying BTech? And again, one more thing is that, like, whether will we introduce that instead of some fundamentals which are pretty old, so to introduce that new software or hardware simulation at the beginning of engineering, because many students nowadays, they are learning these recent trends instead of fundamentals. And one more problem is that if you introduce them fundamentals, they are not interested in. If you give them, this is the board, this is the hardware, this is the software, you do it and get your work done. Without understanding of the fundamentals, they can do it. That is what my question is here. What will be the suggestion from the industry? So how the way we will have approach to the student so that will be beneficial to our student.
Okay, can I take this question? Because as I represent both the sides, as academia as well as the industry. Currently, I'm with KTU Kerala, where they are interested in making a BTech in VLSI. And they want to dedicatedly have the VLSI as their core competency in the coming years, because the government of India norms is another 5 to 10 years they are focusing on VLSI. Particularly, the government of India is one of the initiative is India should have few fabs or a good quality fabs, and then that will take its own sweet time. So in that aspect, I'll tell you the prospects and I'll tell you the challenges and then how it can be addressed. That is how it can go. And prospect is people are working on connected chips, and even quantum computing with respect to the chip design has come, or optimized to chip solution or a chip design is a coming way forward. That is where the whole world is moving out. And they need a lot of quality engineers in terms of who can work with respect to the chip design using appropriate assimilation tools. And if we are able to have the fab in India, then they can work with even the fabs also. So that is going to be there for another minimum 5 to 10 years, or at least another 5 years down the line. That is the prospects. But the challenge, what we have it right now, even I was there with a few universities, the fundamentals are not really strong with the current generation. I don't blame any particular group. The current generation, they just wanted everything as an instant. And they're not very keen on focusing on learning the fundamentals. Even it is some of IIT Madras colleagues also sharing the same. Even in IIT, the trend is a little bit changing. So it is scary for the upcoming generation. So my request is particularly with respect to the digital logic or digital circuits, if they are strong in fundamentals of digital logic, that will help in terms of if they are moving into in that case, if they are working on an analog IC, then they should be focused on analog. But at least they should know the basics well. The fundas should be strong, so they can be molded to anywhere. So that is where the real training has to be started or focused more. And down the line, it can be third year or final year, they can use the 1 or 2 good projects using a Cadence or a Synapsys or a Xilinx. There are a number of simulation softwares. Even I'm sure SRM AP is having a lot of softwares. But the students has been given hands-on and they have to be thrown into the water. We are there to pull them out, but we have to throw them into the water. Let them try to swim. Then if there is a critical situation, anyway, we are the lifesavers. We will do it. But that is one thing, if we are able to focus, then there is a lot of very good opportunities in front of every stakeholder, not only the industry, not only the academia, not only the student. So that is my perspective or my point of view as of now.
That again, whatever you said, that what we are also facing, would it be possible from the beginning of the BTech students some handling with the industry? Because we also have introduced that MTech in VLSI. So what we are planning, like if it is possible for handholding the industry with the MTech's batch, then probably they can able to understand that the industry requirement, and they can able to again work for the industry, and they would be ready. If we will teach them, again, they would not able to interface themselves properly with the industry. So what would be the role of industry here to play to induct MTech student as well as BTech student at the beginning of their career?
Who is to answer that?
Sir, I'm asking that You should guide us whether we could able to start these things at the beginning of their handholding with a like EPIC Semiconductor. Would it be possible to have a handholding from the beginning of their BTech course or MTech course, so that they would be after the graduation they would be able to fit for the industry?
So I'll put it in two ways. The handholding will be a tough task. Say, for example, when it comes to, we are, what is it called, working 24/7 for a tape out. We have three products or three, what is it called, three tape outs. Chip finishing. Tape out is a term which they will call it for a chip finishing. So in parallel, we are working on three chip designing, which is getting closed. They are supposed to get closed by yesterday, but at least we are hoping we'll give it to the TSMC before the January first week or second week. So withholding, in the sense, I'm not sure whether you want us to have a, what is it called, part of the curriculum design, curriculum delivery, curriculum evaluation, and then the performance of the students. That is what you are telling us a withholding. Or beginning of the even first year or first semester itself, some of the industries like a semiconductor or any core companies, they'll come and then deliver it, or they'll give the taste, the what is it called, the beginning, what can be done or what is expected from the industry, so that if some of them, not everybody can be interested in core companies, there will be a number of different aspect or aspirations for every different individuals. But those who are interested can stay in touch with the industry of their interest, and then they will get what is it, molded, and they are good. If industry thinks they are a value addition, then even they will take care of them in terms of different directions or aspects. So withholding, I'm not very clear. The withholding is a very broader term. If you're narrowed down, what is expected? Say, for example, there are some even SRM AP, you are having many courses which is dedicatedly supported by the industry. Say TCS is having, and then what is it called, IGKR. There are a number of dedicated courses you are having it. But what do you mean by withholding is has to be a little bit tailored down.
Thank you very much, sir. What we are planning now, like design the course curriculum. So we, from our academic, we are designing the course curriculum which is not aligned to the industry. Because after graduation, they are not able to fit, they need some training. So if that's what I'm asking, if that training should be introduced at the beginning of their career, as you have said, let them throw into the water, let them swim. If they will get something into that software industry for designing the hardware, let them learn. So in that direction, if we could able to do, and also our course curriculum, if we able to modify with the inputs of the industry, so that they could be fit immediately after their graduation. So that is my understanding over here.
Yeah, then that is what we are looking for. Because say, for example, the training period can be minimized, and also the institutes or universities can have a software. So for example, if we are working on 3 nanometer or 4 nanometer, but you will be working on 60 nanometer or a 10 or even 65 nanometer, that's fine. Because all we needed from the BTech or to some extent MTech students is, are they able to do it on their own? Are they able to use the tools without anybody's support? That kind of a confidence or independency we have to inculcate it to the students. Even I'll go one step ahead, even it should be there for few faculties. If they are able to handle the projects on their own, so that they will, under them, the students will get the, what is it called, enriched experience, and that will help industry and even the students, because right now we are spending ample amount of quality time in terms of training them. So that can be minimized. That is where the institutions can play a very bigger role or a vital role, and it will be good for all the stakeholders. Even industry will be happy, because on the day one, if they are able to work, it is good for them. Similarly, if you are able to work in the cutting edge technologies or appropriate softwares, then the companies will give you the co-creation of the projects, so that some of the POC or proof of concept can be done in the university. And then after a certain stage, it can be translated to the companies. So that is very much possible, sir.
Okay. Thank you very much, sir. I would like to request Dr. Jha to comment on that.
Can I?
Yeah.
Yes.
Let me,
Okay.
put another
Dr.
prospect
Das.
around this discussion on semiconductor. So, I came from a different background, but the way I see the semiconductor industry, before commenting anything, I want to comment some of the data which are available in public domains about, say water top 10, or let's say top few industry which are extracting or using more, water from the environment. So let's say Samsung. Samsung is the highest water consumer company across the globe. So they consume around 163 billion liters of water for 2021. And the second highest company who use most of the water from the environment is the TSMC. They use 78 or close to 80 billion cubic liter of water from the environment. And the third one is Intel, and the fourth one is Google, and Google is around 15 billion liter of water. So you see the difference between Samsung, TMC, Intel versus Google. Google is, even though they are in fourth position, but they are using many magnitudes lower water than the top of these three companies. And may I ask you what these top three companies are doing mostly? They are actually semiconductor producer, right?
They are producing chips.
So now my question is, this semiconductor is usually water thirsty companies, right? To producing one chip, you require huge amount of water. And these things is coming in light for last, decades or so, because when we go for water crisis issues and we want to count where this water is going, right? And most of the time sustainability reports of those companies are actually aggregating, and they're hiding some of the data, masking it, and they're showing some numbers to the world. My question is this: if we know that the semiconductor is required that much of water, are there anything coming from it? Of course, industry may be optimizing many things. Are there any research ongoing in the academia to reduce this kind of natural resources on producing the semiconductors? Maybe designing the entire process in differently, or coming with a material which can replace water, right? Because there is this a tussle ongoing where to put the semiconductor industry. So even if, let's say, some industry want to set up some labs in a manufacturing plant in India, if that region is water scarcity, government is not going to permit them, right? And most likely the industry expert who is joining in this panel session, right, sir can comment on us. Yeah.
Okay, so this is actually a very good perspective, because most of the time when we work on these semiconductors and chip design, we mostly think about the performance, right? Performance, heat management, all these things. But sustainability, creating sustainable chip, that is also going to open a new door for us. And that is probably like future has many directions. That is one of the directions. How to create the sustainable chips? What are the researches on that? As well as the students, they should also be aware that this is also one of the directions that they should follow. So I agree with Dr. Dash.
Yeah, and before student, I guess the academia should come up with a plan to design such courses where, let's say sustainable chips can be a subject where, how to count the water footprint on producing chip, or how to count the energy and then convert that energy into carbon footprint. And there is, there will be time that every chips will come with a number of how much carbon footprint it has been used to produce that, and water footprint it has been used for produce that chips, right? And that time is not far. So in order to optimize the natural resource energy or carbon footprint, that should become collaborative effort from industry as well as from the academia to design the courses, start the research directions, and explore what are the things can be done to optimize water use or energy consumption to make the chips more sustainable, right? The growth of the chip, growth of this manufacturing industries are exponentially in order, because we are seeing this lot of shortage in the car sector, different sector, right? And this is going to grow in manifold in coming 10 or 12 years, right? And then the water will be the same quantity. You have to optimize on water part, otherwise there will be a big problem.
Okay.
Thank you.
Professor Jha, if he wants to add something.
Now I would request.
Actually, the
Dr.
question was for Professor Jha.
Yes,
We hijacked the question.
Okay. So now as an academician from Indian Institute of Technology, Guwahati, I would request Dr. Ravindra Jha to comment on that and how these the sustainable things can be integrated as a part of our curriculum and also how to teach the student.
Yeah, so I was not part of this panel discussion. I just walked into. But this is actually truly a challenge for us also. At IIT Guwahati, as I'm part of VLSI group there, so I understand that I mean, my job is to prepare my students for industry, okay? Because most of them are interested in industry, industrial jobs. They are not willing to take, they don't want to go for higher studies and all. But anyways, we are regularly updating our syllabus, okay, as per the need. Recently, I mean, that is very internal, but I can say that we are also trying to bring industry just after their coursework, when the student finishes their coursework, say after 1 year or so in MTech. Second year is totally project, okay? So we are trying to bring industry from the initial point when the student completes his coursework. The undergrad students are already going to, from their second year onward, they are already going to for internship. So they have a bit flavor of industrial work starting from their second year. Coming to this sustainability thing, frankly speaking, we are struggling to bring industry in actual fabrication. In semiconductor fabrication, we don't have anyone till now. Government has pushed about 76,000 crore rupees, and many industries have shown their interest. So right now we are not worried about much about this sustainability thing. Right now our aim is to bring something, okay, frankly speaking. So once, because even if we start now, say at 180 nanometer node or so, we can't directly start with 5 nanometer node or something, okay? So, but this studies, this Samsung and other that Kamal has just pointed out, I will disagree with the point, because most of the work that Samsung and I don't know about Samsung, but other semiconductor industries they are taking on, they are taking help of foundries. So actually the culprit is the foundries, not these companies directly. Okay, so if you want to catch someone, you should catch TMSC or Global Foundries or someone else. Okay, so this is my take on this. Thank you.
Okay. But anyway, we have to make the entire ecosystem sustainable.
Yeah,
just
that's true.
That's the thing. Yeah. And second, I just want to add probably the last point for this panel discussion. So one thing I just want to add. So this is many times I have heard from many academicians, and in many college campuses I have been there. So many professors have been asking that how we can make our students industry ready. Probably this panel discussion also discussing the same thing. And my take, like I am taking a little radical steps here. What I'm going to say, probably many of you will not agree. First of all, the students cannot be industry ready from the day one, or the day they finish their education, they cannot be industry ready. That is not the intention, and that cannot happen also. Industry or wherever it is, anywhere somebody is working, it's a cumulative experience that will make them ready. It's not, there is no course, no certification, nothing can make them industry ready. So that is completely different thing. But the question is whether should we focus on our curriculum to make it more practical? Yes. Whether industry wants or not, that is the secondary thing. But whether they should be more hands-on oriented, more practical, yes, that should be our focus, so that students can understand it better, they can relate with the real world, and wherever they go, they can contribute there. That is my take. Industry, being industry ready is not that thing. So every day we are learning new things, and not only me, probably our CEO is also learning every day something. So he is also not an industry ready. Okay. So this is what I wanted to say. With that, probably we are end of this discussion.
Thank you very much. And I would like to request Dr. Rajkumar Ilagiri to conclude that panel discussion.
By the way, the people who joined online, they are missing the snacks and tea.
Thank you. Anyway, thank you very much. But I'll touch upon our IBM, if I'm correct.
Yes, IBM research, sir.
Yeah, IBM.
I'm from, and IBM research is hugely involved in semiconductor research, not in production, but doing research.
And I am from Dell. We don't manufacture semiconductor, but we use that most.
Truly. No, I just touch upon the, what is it called? It's an interesting point, because even when I was with Bosch, I asked a similar question for the automotive sector. So, for example, that's one of the reasons most of the car manufacturing hubs in the this side of the Asia Pacific region rather than the other side. So there are a number of allied situations or issues which is related to manufacturing sector, and one of our panel member touched with respect to the foundries has to be the one, but it is a cumulative, or all the stakeholders are responsible for it. But leave aside that as a topic for automotive as well as avionics sector as well as the chip design. The current scenario is, even I touch upon the last speaker's point, the industry ready means he correctly touched. We are expecting the institutes to give them more practical exposure or applied learning. Because when they are not at all even aware of what are the simulation tools which are getting used in industry, that is where the pain point comes. Now the industry institute, in the sense, they even after 10 years, 15 years, even we are keep on learning. It's not like earlier when we are finished our PhD, we can sit and relax and then that is the end of the story. It is not the case now. Each and every day there is a new technique and technology, and if you want to be in the market, we have to. So if it is there for experienced professionals, then we have to inculcate that the taste or a habit of learning proactively or independently, have a hands-on experience is what we are. The academia should focus with respect to the students who are keen on core companies. I'm not sure about the IT companies or a service sector, but generally, because this will needs more of the logical thinking. If some design is gone wrong, then you have to sit and then you have to debug it on your own, where which gate has gone and which transistor is not working, what logic has gone wrong. So that kind of understanding should be there with respect to the subject. If that is able to be done, then we are on the right track or a right direction. That is what I will assume, and that's what all our other speakers also touched already. And please.
I do have one last recommendations on the comments on making student industry ready. Okay, I certainly agree that student or the end of their semester may not be ready for industry, but we can help them to gain more understanding about what's going on in industry by doing the small projects, what they do in the BTech project or MTech project as a part-time project, right? So in that project, we saw that students come with ideas, sensor, this sensor is sensing water quality, this sensor is sensing soil moisture. But actually we want to, if you can give them a flavor, real world flavor, you are building some prototype. If you can go outside the campus, you find a water body and put it there, Can you sense the water quality there? That's the industry. The building prototype, sometimes it works, sometimes it does not work. It is not efficient or some problems. If you can solve that problem by taking simply out of this lab to that water body and put it there and sense it, that's the industry. If you can done that part, you are ready for the industry. So my 1 cent is on that, recommendation.
Just to conclude, even co-creation with respect to our SRM AP on VLSI and related ECE topics, we are in the progress. Just to add a point to the same, exactly in the same similar line. Yes, Professor Ramakrishnan. Yeah.
Yes, I have one question. What is the IP solutions students can study or they can try to do so that that will be helpful for them to, for example, nowadays the RISC-V processor, lots of people are talking about a RISC-V processor. So they are telling that the RISC-V may take over. So what is your take on that?
So you asked the right question, but again, I'll stick back to my first answer. Even one of the difference between what I experienced from IIT students and other students is they are fundamentally strong, so they can cope up with any new upcoming trend or a technology. Whereas the rest of the groups, they are keen on one particular thing and then they stuck there. So I completely agree your point, but what I request you is they should be capable of handling to any new upcoming trend or a technology. That is where we focus. So at least they'll reach to the what is upcoming on the at least in another 3 to 5 years. Yes, RISC-V is the one which is predominantly dominating the market now. But better we'll see them if they are ready for any new trend which is on their way.
So they should be, students should be good at fundamentals.
Yes, yes. Very vigilant and assertive and alert. And then they should be, so they should have a clarity. Okay. That is what at the end of the day make the difference.
Thank you, sir.
Okay. So, Professor Shanti.
Okay, then thank you very much, sir, for joining the panel discussion. So now I would like to proceed for the next session. Thank you very much, sir.
Thank you all.
Thank you all.
Thank you, everyone.
Hello, everyone, and from my side, it's a good afternoon to you all. And I'm called Mayur Kumar Chipa. I'm lecturer and engineering coordinator at EPIC University in Kampala, Uganda, East Africa. And thankful to Madam Saganta to give me this opportunity to talk about the photonic crystal-based devices for photonic integrated circuits. So yes, as we all, most of us, we are working in the field of electronic devices, electronics and communication engineering. Apart from that, optical fiber communications, optical engineering. But when you look at the future, which is going to be talk about the photonic integrated circuits, which require the photonic devices and which can be used in a complete circuits to perform the various operations required for optical communications as well as for optical devices. So my today's talk will be on photonic crystal based devices for photonic integrated circuits, and I hope the participants, either you are doing bachelor's degree or master's or even at the PhD, definitely will be benefited with this talk. And definitely if you have any questions at the end, please feel free to discuss to me and you can ask me queries, or even you can write into the chat box. I'll respond to your queries, right? So the content which I will be discussing here, moreover about the photonic crystals, actually, like how the photonic crystals based technology how it all started. And then apart from that, what is all about the history, like how it all started. And then what kind of various the photonic crystal based, the passive components are being designed by us and various other groups, like optical communications, mostly for waveguides, optical bands, optical filters, multiplexers, demultiplexers, optical switches, optical logic gates, with encoders as well. And then lastly, a combination of all these makes a photonic integrated circuits, and that's what we're going to discuss in the today's session. So what actually a photonic crystal is all about? A photonic crystal is a periodic arrangement of a dielectric material that exhibits strong interaction with light. So apart from the photonic crystal fiber, which we already know about, that it's having a core and a cladding where the light travels into the TIR with the phenomena of TIR, the total internal reflection with the core of the fiber, and there is a cladding to provide it the TIR. So all the sessions, all the things we have already seen in the previous about the optical fiber communications. Then there's the phenomena came that if there is a periodic arrangement of dielectric materials, and that can also exhibit the interaction with the light. So apart from the core and cladding of optical fiber, there is also a kind of periodic medium or periodic arrangement of dielectric material rods where the light can also propagate. So this was the concept, or this was the basic phenomena of how the photonic crystals came into the axis. So if you look at the history of photonic crystals, how it came. So first ever it was reported in 1887 by Lord Rayleigh, saying that if there's a periodic arrangement into the one-dimensional, like if you can see on the structure, it's going to be have like it's going to be have in 1887 the first time it had like where it's going to be have two dielectric material rods. One is of the green color and another one is of the blue color. So it is called as the 1D photonic crystal, means it is going to be have the periodic arrangement into the one direction. That's why it is called as the 1D photonic crystal. And apart from that, in 1987, after some 100 years of time, it came as the 2D photonic crystal and the 3D photonic crystal, where the dielectric material rods are being repeated periodically in two directional as well as into the three directional. So that is all about, you can see the periodic arrangement of dielectric material rods, and the different color represents the materials with the different dielectric constant. So that's all about the photonic crystals, where there is a periodic arrangement of dielectric materials keep on either in one directional or a two directional or a three directionals. So if you look at the screen, where the first ever the reported work was in 1887, which is also called as the 1D photonic crystal, the paper by Lord Rayleigh on the maintenance of the vibrations by forces of double frequency and on the propagation of waves through a medium endowed with a periodic structure. So yes, if there is a medium endowed with a periodic structure, there is a propagation of waves possible. That's what it was first ever reported in 1887. Then in 1987, by the two people, one is called the Ali Abornwich and the Sanjeev John, in the physical review letters in 1987, after 100 years of paper by the Lord Rayleigh. So it was all about the inhibit spontaneous emission in solid state physics and electronics, and then the strong localization of photons in certain disordered dielectric superlattices. So these were the two papers by the two scientists who gave about that how the photonic crystals came in 1987. So this was the most peer-reviewed papers which is being followed for this area. So the question comes, is it like something the photonic crystal it came for the first time, or is it like something it's coming from the nature? So it comes from the nature in such a way that if you look at the feather of a butterfly, if you look at for the sea mouse, a metallic wood boring beetle, if you look at the feather of a peacock, opals, if you look at them, if you look at them at if you look at them at the microstructure, if you look at the feathers of a butterfly or feather of a peacock, if you look at the micro scale, you'll find them there is a periodicity. So particular wavelength of light is going to be absorbed, and that's what you get the different wavelength of, the different wavelength of light you can see in their feathers, and that's what you can see the concept of the photonic crystal, which comes from the nature itself. So the thing is that if you create such kind of periodic structure, particular wavelength of light can propagate through the structures. That's what the concept came from the nature itself. In the same way, if you look at the structures which can be created in this the photonic crystals, so there are the two kind of structures which can be created. The one is going to be have the dielectric rods in air, or you can say the dielectric rods on a wafer. So if you look at, for an example, if you look at the comb, if you look at the comb, which is going to be having one directional, or it can be in the two directional if you have the circular one. The same way, the another structure is called the air holes, the holes in a dielectric wafer. So if you create the holes into a wafer, also there is a periodicity. So there are the two kinds of structures can be created, either rods and air structure or the holes in a wafer structure. So these are the two kinds of structures which can be created. So either we can have the different lattice structures, either we can have a square lattice or a triangular lattice or a hexagonal lattice structure, the different shape of the structure. Why can't we have only the square and only hexagonal? Because if you look at the nature again, with the honeycomb membrane holes, the structure looks like as an hexagonal lattice structure actually. So this is an hexagonal, the holes keep on repeating again and again with the periodicity. That's why the holes on a wafer structure came into the axis actually. So when you're talking about the two different kind of structures, either the membrane holes or the deeply edged pillars on a wafer. So what we have realized that if you're having a pillar structure, the transfer electric modes exist, and if there is a holes in the structure, the transverse magnetic modes exist over there. So if you're having if you are working on the structures like the passive devices for optical communications, mostly for the devices part or the components parts, yes, we do design using the rod structures. And if it's all about the holes, mostly for the sensing applications, where these holes are being filled by the different biomolecules or different chemicals or different gases to have the sensing applications. So yes, if you want to design the devices, go with the rod and air structure, and if you want to create the sensors, go with the holes in the membrane structures. So that's what we can say, that the concept of the photonic crystals comes from the nature actually. So when you talk about the features of the photonic crystals, like what actually the photonic crystal is all about, what kind of structures can be created, or what kind of defects can be created. So all those things we shall be discussing here. So what actually the photonic crystal is all about, in which the refractive index varies periodically, either in one directional or two directional or three directional. It has an ability to suppress or enhance or control the propagation of electromagnetic waves. So we can create the two kind of structure. One is called as the photonic crystal waveguide, the PCW, where a line defect in a photonic crystal can be created, and then PCW can be created. The same way, one is called as the photonic crystal ring resonator, where the point defect can be created into a photonic crystal structure, and then the PCR can be created. So it can guide the light from one point to the another point without much loss, even around the bands. So that's what the concept of photonic crystal came, where if you look at the fiber, optical fiber, which you are having the glass fiber or the plastic fibers, if you bend an optical fiber at an angle of 90 degrees, what's going to be happen? There will not be the TIR. So what could be the solution for that? So on that, for the solution for that, the optical bands are being created so that the light even can propagate through those structure. So these defects, which we talked about the line defect and point defect, shows the frequency selective propagation in a photonic crystal waveguide. And you must be surprised, like Mr. Mayor, what are the different types of defects? How do they look like? Are they talking about a line defect or a point defect? But what actually the meaning of defect is all about? So the defect is equivalent to breaking the perfect periodicity. Now we can say, suppose there is a periodic structure, right? It works as an insulator. There is no propagation of electromagnetic waves. It's an insulator structure. But as soon as you create a defect means what? So suppose if I'm talking about a line defect, means I'm going to maybe remove a complete rod of lines, or I change their positions, or I increase their radius, or I decrease their radius, or something like that. Same way, when I'm talking about a point defect, it means that I'm talking about a single particular rod. Means if so what does it mean by the defect? So particularly you can see there's a yellow rod is there. So if I shift its position, that is also a defect. If I increase its radius, it's also a defect. If I reduce its radius, it's also a defect. Even though I remove this rod position from here, it's also a defect. So what does it mean? If there is no rod has been removed, there is no defect. It works as an insulator, no propagation of electromagnetic waves. But as soon as you create the defect, the periodicity is going to break, and then the electromagnetic waves can propagate through those structures actually. I hope you understood the concept of photonic crystals, right? And I'll show you in some of the slides what happens when the defects are being created, and then what wavelength of lights are being propagated through the structure. Because there is no defect, no propagation. The defects are being created, then what wavelength of light? Because mostly for optical communication, we talk about in terms of frequencies or mostly to the wavelength. So what wavelength of light is going to propagate, that we shall see in the due time. So when you're creating any such kind of optical devices, other as said in the waveguides or resonator, filter, multiplexer, all such kind of devices, when you're creating, what shall be the designing parameters we need to take in care? So if you look at the structure, suppose this is a rod structure, you can say in one directional, then it's going to be a 2D or a 3D. But what could be the designing parameters? So the designing parameters, the first one is all about the number of defects. So either I'm creating a resonator structure or I'm creating a waveguide structure. So number of defects is a very important parameter. It's not like just to remove number of lines in a vertical or horizontal way just to create a structure. No, it's very it's very optimized way to calculate that how many rods need to be removed actually. And then the distance between the defects, and this is called as the lattice constant, or sometimes they call it as the pitch, means what is the spacing between the each rod actually. Then the number of the size of the defect, either you can talk about in terms of diameter or you can talk about in terms of radius. We shall be knowing what is the radius actually of this rod structure. And then the refractive index of the defect. Definitely when you talk about in terms of optical communication, we more talk about in terms of refractive index, means what kind of material I'm going to talk about, either silicon, germanium, gallium arsenide, indium phosphide. What it's a combination of maybe a group of 3 materials or a group of 4 materials. But what kind of materials we're going to talk about, we shall be knowing their dielectric constant, also to their respective refractive indexes actually. So these are the 4 parameters are very important when you're designing the optical devices using the photonic crystals. So the photonic crystal, there's an important phenomena of photonic band gap actually. So what does this photonic band gap is all about? The photonic crystals which have band gap due to the periodicity in the materials dielectric constant, in the gap the electromagnetic waves or the light cannot propagate into the crystal structure. So there is no defect, it works as an insulator, no electromagnetic waves or the light can propagate through the structure. So a wavelength of range for which a material neither absorbs light nor allows the light propagation, or a range of wavelength the electromagnetic propagation is absolutely 0. So we find a range of wavelength which cannot even pass through the structure. So as soon as we create the defect into the structure, those wavelength of light can pass through the structure. So the photonic band gap, which is the forbidden gap of photons. Likewise, we talk about electronic band gap, where that is a forbidden gap of electrons. Either the electrons will be into the valency band or into the conduction band. The same way it is going to be here. So if you look at the photonic band gap structure, so if you look at the structure now, it shows me the band gap range from somewhere in the range of 0.541628 to 0.877675. For which materials? So here we have used a material for silicon, which is having a refractive index of 3.46, which is mostly be used for optical devices. Why we use only this refractive index mostly for silicon? Because if at this refractive index of silicon, we get a wavelength range from 1139 nanometer to 1846 nanometer. Now, why we are using this wavelength? Because these range of wavelengths is covering our optical, the second and third optical windows, which we have like 1351 and 1311 and 1550 nanometer wavelengths. So both the wavelengths which are using for optical communications are being covered using this range of wavelengths for a silicon material. That's what we try most of the device using the silicon photonics, using the silicon materials. So what could be the structures can be created. So if we remove a particular line of rods, it is called as the line defect, where you can say wherever the defect is there only the light propagates through the structure. The same way, if the defects are being created into a band structure where an L-shaped band has been created, where the light only propagates or the electromagnetic waves only propagate through the band structure where the defect has been created. So even at an angle of 90 degrees, the propagation of light is possible into the photonic crystal structures actually. So this is when we are creating a defects in just a line structure, or either in horizontal or vertical or whichever the shape. It's only about the line defect. But when we have to create a resonator structure, resonator where you can find there must be a bus waveguide, there will be a dropping waveguide, in between them is going to be a resonator, is going to be a circular resonator definitely. So for such things, we also need to have a point defect so that such kind of structures can be created where a particular wavelength of light is going to get resonate through the resonator and is going to either a forward direction at the port 3 or is going to be have a backward dropping at the port number 4, and if it's not being resonated, it will be traveling to the port number 2. And you must be saying, then where shall we use this kind of structures so that the light can propagate through the structures? So the one of the application is all about the channel drop filter using the circular photonic crystal ring resonator. So what you can find in one of the most prominent devices in the telecommunication industry is the channel drop filter. This prominence is consequence of both its importance and its size. So the channel dropping filters and devices that are necessary for the manipulation of wavelength division multiplexed optical communication. So what you can find, for an example, if I say from the input port, there are the 3 wavelengths are coming, F1, F2, and F3. So F1 and F2 are being unaffected with the resonator and they are traveling to the output port on the same waveguide, or you can say the bus waveguide. But a particular wavelength, as per the design parameter of the structure, particular wavelength of light, you can say the F3 wavelength is going to get resonate through the structure and is going to get dropped either at port 3 or at the port 4. Port 3 means the forward dropping and port 4 as a you can say the drop background, or you can say the backward dropping of the structure. So the same way we designed this kind of optical channel drop filter where you can find the periodic structure has been created with the respective design parameters, and we had one input port. Apart from that, we had the 2 of the dropping ports. One is the point number 1 and one is the point number 2. So particular wavelength of light, if it's unaffected, it will be going to the port number 2. And if it's being resonated and being dropped, it will be dropping at the point 1. So that's what you can see the refractive index view profile, where you can find, because on the first structure you can see they looks like as the points, but it's not the point. They are the vertically polarized rods on a wafer. So you can see on a wafer there are the vertically polarized rods, and here you can see their electromagnetic field view, that how the light propagates and how it is going to be resonate. So if you need to have some more details, the paper is available on Optical Engineering Journal, so you can go through with that paper, where we improved the dropping efficiencies in the 2-dimensional photon crystal based channel drop filter for CWDM application, and we shall be discussing some more about what actually the wavelength division multiplex is all about and how it is being categorized into the CWDM and the DWDM, actually the coarse wavelength and the dense wavelength. We shall see more details in the technology part. Apart from that, we also had a paper on optical demultiplexer using the various photonic crystal ring resonator, where you can find demultiplexer where we have a single input, but it's going to be output at the 4 different outputs. So particular wavelength of light will be going to the particular output port. So if you have the 4 different wavelengths, they are going to the respective output ports 1, 2, and 3, and 4 actually. So this paper we talked about the modeling of a small size and the low crosstalk, the dense wavelength division multiplexing, demultiplexer based on the photonic micro ring resonator structure. Apart from that, we also had a work on optical switch. Now, what actually optical switch is all about, where particular wavelength of light is going to be switched from one of the port to the another port, depending on the temperature effect. It's also being called also as a temperature sensor, where particular wavelength of light is being shifted from port 1 port A to the port C, and that's where you can find how the optical switch can be designed using the temperature effect. And this work was published in Optic Journal. So such kind of devices also can be designed like based on the optical logic gates. In the photonic crystal based optical logic gates, where you can find most of us, those are from electronics background, they must be knowing about like AND logic gate, OR logic gate, to perform all the arithmetic logical operations of your computer, the where the CPU is being designed. The same way, when you have the photonic integrated circuits to perform various logical operations, obviously we need to have the different logic gates, where here the AND logic gate has been designed, where whenever the input, only one of the input port is high, the output is low actually, right? And when both the input ports are high, when both the inputs are 1, 1, the output is going to be 1, and that is what the AND gate works actually, and that's where we have designed here the AND gate. In the similar way, we also trying to design the OR gate, where OR gate is all about where any of the input is high, the output is going to be 1, irrespective of 0 and 0 input conditions. So obviously when there is no input, there is no output. That is very obvious here. But the same way here, how to design the OR gate, which is being designed here. You can see here it's the reflectively view profile also. Here you can see the simulation result, which reflects when the input conditions are 0, 1, 1, 0, and then 1, 1. And for that, all the three conditions, the output is 1. That's what we can see here. Also, the work which was the realization of all optical logic gates using a single design of 2D photonic crystal bandgap structure using the square ring resonator structure. So this is the way you can find. We also have the two different kind of structures are being created, either square lattice structure or a hexagonal lattice structure. So definitely certain advantages are there for the certain structure which we are going to design actually. So this was the work we published. And what was the novelty of that work? If you look at the recent paper being published, or recent work which is being done by the researchers around the world, they have designed the multiple logic gates with the multiple structures. Now we came with the concept that how we can have a single structure of the photonic crystal, but which can work multiple logic gate operations with a single structure. And that's what we designed. And it was well recognized and well published in the Optical Engineering Journal during 2021. Yes, definitely we did this work during COVID period, but at least the work performed well, and we got this paper actually during that time. So if you're interested, you can go through with that paper with this link. Apart from that, we recently this year we had this paper on optical encoders actually, where we have the multiple inputs and it's going to be to the respective output ports, and that's what we tried to design the optical encoder, which is actually a 4:2 encoder. So where we had 4 inputs and then 2 output ports, Y0 and Y1, and accordingly with the input ports we had an output ports. Then we calculated their contrast ratios. Apart from that, we also calculated the response time. When it switched from 0 to 1 and 1 to 0, what is the response time in femtoseconds? And then we calculated the data rates in the terabits per second. And that's what we find, that we designed ultra compact with the improved data rate optical encoder based on the 2D linear photonic crystal ring resonator, and it was published by Springer Journal Photonic Network Communications, and during this year only. So this is all about the different devices. Now we can say, okay, now you have like various devices. Where do we use them actually? So we look at the technology part. It is being designed for wavelength division multiplexing, because which transports the multiple signal onto a single optical fiber by using the different wavelengths to carry each signal. It is being categorized into the 2 ways. One is called as CWDM and one is called as the DWDM, called as the coarse wavelength division multiplexing and dense wavelength division multiplexing are the two the WDM technologies, where the CWDM is categorized by the wider channel spacing. What does it mean with the wider channel? Where in CWDM we have around 18 central wavelengths from 1271 to 1611 with the spacing of 20 nanometer for each wavelength. Means 1271, 1291, 1311, 1331, 1351 likewise. Same way, when you look at for DWDM, where the spacing is very less in the range of 0.8 nanometers. So there are hundreds of wavelengths, but the spacing is very less actually. And apart from that, we have the technology in the range of photonic integrated circuits. So what range of wavelengths, or we can say, is it the wavelength which is being given, or we design any structure for any wavelength? No. We designed them for as per the ITU International Telecommunication Union standard ITU T G694.2, where the different optical bands has been designed, and O band, E band, S band, C band, and then to the L band. So most of the devices which we have designed is for 1311, that is all about your O band, and the lastly to the 1551 nanometer, that is all about your C band applications, because at those wavelengths we shall find that it's having the lowest attenuation, and that's where we have the different sources are being available for those wavelengths actually. Apart from that, when you look at for the photonic integrated circuits, because here we have very many, actually one more thing, as you look at the theme of the conference is all about the EPIC, electronic and photonic integrated circuits. So most of us or most of my colleagues must be working on electronic devices. We are talking about different electronic components, but now how come we are talking about now to the PICs called as the photonic integrated circuits, that the current data network rely on a mix of optical carriers and then electronic circuitry. The signals are transported in the optical domain by fibers that support the high bandwidth and the low losses. So meanwhile, the electronic device distributed along the backbone provide the rest of the essential functions needed for a modern packet switching network, such as routing, storing, and queuing of the data traffic. The performance of such networks, however, is limited by the electronics, which have a maximum speed of only about a gigabit per second. What else if you have to go for the TBPS and more than that? So to satisfy the increasing bandwidth requirement of emerging applications and to eliminate this bottleneck, we wish to replace this electronic circuitry with the analogous optical system that provide the transparency and then high bandwidth while consuming the significantly less energy. So these photonic crystals offer a handy alternative technology that allow us to design the nanoscale circuits that can control the flow of light with innovation or innovative silicon platforms actually. And this is where we talk about silicon more about, we talk about Silicon Valley and all, we're going to talk about more about silicon devices. And that's where the integrated circuitry comes here, where you can find a single structure, where you can find here, we're going to talk about a tapper, which is being connected to the fiber to the, which is being connected from fiber to the photonic crystal waveguide structure, which is going to be have an optical waveguide, then it's going to have a splitter, then it's going to be have a demultiplexer, a waveguide curvatures, maybe at an angle of 90 degree or 60 degree or 120 degree, and then to the ring resonator, and then finally it's going to drop. Apart from that cross connect, you can say, or you can say the optical switch. So that is why you can look at here, instead of having multiple single devices or are being connected into a circuitry so that it can be used for a photonic integrated circuit. So if you look at this kind of structure, where you can say we do have input ports and then we do have the 3 different output ports actually. Now if you look at this structure, which is a combination of a photonic crystal waveguide mode coupler, then is going to be here having a regular photonic crystal waveguide, then power beam splitter number 3, optical cross connect at 4th, then optical resonator at 5A, 5B with the 120 degree of the photonic crystal waveguide. So yes, we can use multiple waveguide bands, not only for 90 degree, but maybe 120 degree and then a 60 degree of band, then a delay line or a phase shifter, and then finally to the wavelength multiplexer. So you can see here multiple optical devices or multiple photonic crystal based devices can be incorporated onto a single design to make an integrated circuitry. Apart from that, guys, when you look at for the work which you are doing in the ways of photonic crystals or the silicon photonics, it's not like you must be saying, Mr. Mayu, you're working in the area of 2021 or 21st century. But is it something like it is something new to this field? No. If you look at for the first ever, the silicon product were introduced on the market by the Couture in 2006. And then after that, many more companies came into this area. If you look at this present time, most of the European countries, they are working on this photonics technologies, either they are assembling, design, packaging, and also technology. We shall see what are the different companies are here, but it all started in 2006. And apart from that, if you see the year by market, you can see a lot of companies came into this, like Intel, HP, Cisco, IBM, and all very many companies came into this axis, a research done by the Yale development. So if you look at the recent, the silicon photonic market for 2019 to 2025, for forecast by the application by again the yield development, you can see the market was in 2019 was something around like $480 million. But if you look at for 2025, something around 3.9 billion US dollars actually. So you can see those are many of us, those are working into this area of photonics and the electronics. The future is too big, where you can see the development of a lot of devices, and the growth rate is almost around like 40%, where it's not only about the data center transceivers, long haul transceiver, optical interconnects, automotive lidar system, immunity test, fiber optic gyroscopes, 5G receivers. So yes, it's going to be have the huge market. And when you look at for the companies, like where we shall be working, like those are the companies who are working into these domains. So we shall be looking into the companies which are working into this domain. So if you look at the readiness of the silicon photonic players, so definitely from volume suppliers to the prototype designers to the R&D. So there are very many companies around the world which are working into those areas, not only in the Europe, around the UK, around the US, all such countries, even Asia's now. So a lot of companies are there who are working into those key areas of photonics and the core electronics, which can have for photonic integrated circuits. Apart from that, I'm thankful to the electro optics, the Photonics 100, and I'm fortunate to be the part of this. The 100 people who are the industry's most innovative people. So my work has been recognized by the electro optics, and you can find, since I'm in Uganda right now. So apart from the entire Africa, there's only one person who is being chosen. So this is a really proud moment for me also to be the part of to be listed into the Photonics 100 for 2023. So thank you to all listeners for being with me and giving me this opportunity to talk to you all about. So thank you once again to all the organizers of this conference and all my friends, colleagues, and the university management for giving me this opportunity, and especially to Madam Swagata to giving me this opportunity to talk to you people about my work, which I'm doing on the photonic crystal-based devices for photonic integrated circuits. So what I've realized that the photonic crystals allow us, the photonic crystals allow us to manipulate the light in a ways that have not been possible before, and that's why you can see how people now are talking about the photonics. And that's where again I'm thankful to the SRM University and then Madam Swagata and her team to bring out this kind of theme where people can really talk about the work which they're doing in the field of photonics, photonic waveguides, electronics, so that the young researchers can also be benefited to get an idea to work on what kind of domains they can work, which industry is required. So thank you so much once again to all of you for listening to me. If any questions are there, feel free to discuss to me. Thank you once again. Have a nice day. And that's where you can take a look on beautiful Kampala, which is the capital of Uganda. Yes, so the light is required by everyone actually. Thank you very much, guys. Thank you, everyone.
Thank you, Dr. Mayur, for giving such a informative session. Now the stage is open for the audience. We would love to get some questions from the audience. Any questions from the audience?
Yeah, thank you so much for this informative session. I have one question regarding the dense WDM system that we developed. And regarding the speed, we are having this selectivity depending on the temperature variations, right? So,
yes, sir.
Will there be any effect on other channels also when you vary those temperatures? So how much crosstalk will be there and how much efficient that selectivity will be? Is there any plot or results, something like that, that you can show us?
So I'll say this way, when you look at for the optical switch, what happened in the optical switch when a small change into the temperature, what happened actually when the particular wavelength was traveling to the, you can look at the simulation results where it was on port number C. But what happens when a particular temperature is being changed, the particular wavelengths are being shifted from port C to the port A. So what is going to be happen when you look at for this non-linearity, when the temperature changes? So we have talked about the linear changes into the temperature. We are not discussed about the non-linear changes into the temperature. So whenever there is a linear change into the temperature, along with that, there is a shift into the refractive index of the materials. And as soon as there is a shift in resonator wavelength refractive index, the same way there is going to be a shift into the resonating wavelength as well. And that's what we have realized in this work actually.
In the last slide, we showed those 4 channels.
Okay. You're talking about this one?
Yes. So when you talk about this demuxing, using various ring resonators.
Yes, please.
So you have a chip here where you are varying the temperature. Will there be any crosstalk between the 2 channels?
Sir, okay, thank you for your query, sir. But this ring resonator, which we have structured here, is not based on temperature. This is a normal structure, which is going to have the different structures of the resonator, and we have changed the properties of the coupling rods here actually. So what happens here is not the effect of temperature. It's just about the structure has been created, where we are going to use a different concepts of one is all about the inner rod structure of the resonator. Apart from that, the coupling rods, also to the scatter rods which have been placed. So apart from that, what we have realized that particular wavelength of light is going to be dropped on each of the port, and definitely is going to have the crosstalk, which you have when you're talking about the structure, we find the very less crosstalk at the second and then third wavelength. And when we realize for the first channel and then fourth channel, where we have realized some crosstalk, that's why we got the efficiency somewhere around like 90 to 92%. But when you look at for channel number 2, where we have received the 98% of efficiency, so it's definitely there is a crosstalk for such kind of structures. Even you can see at the simulation results also, where the particular wavelength is being dropping at the channel number 4, but at the same time it is also we can see there is a crosstalk. There is a at the port number 2. The same way when you're doing for port number 3, there is a crosstalk on port number 2. The same way when you're dropping at the port number 2, there's some crosstalk at the port number 4 also. So yes, we have realized some of the crosstalk also. I'm sorry, I have not mentioned that the graph here, which gives me that particular wavelength, how much is the crosstalk, but it is there, sir.
Oh, thanks.
I'd like to ask 2 questions. Maybe I've not heard the presentation. Just out of curiosity, I was asking. Here, everywhere is about 2 questions I have. First question is, everywhere they're using about AI and ML and machine learning, deep learning, all those things. So in the optical communication point of view, say, my research area is purely signal processing, and I'm also working about deep learning. So in this, anything deep learning can be applied in the optical communications, deep learning or machine learning concepts. In what way it can be applicable?
So, sorry, sir, I didn't hear you well, sir. I mean,
no, I want to know that deep learning or machine learning concepts can be applicable in the optical communication field. In what way it is applicable?
Sir, in optical communication, it can be designed where the optical communication has to be used like an optical switch has to be designed, or maybe in terms of like optical demultiplexers, optical multiplexer applications, where such kind of structures can be designed in such a way that, yes, definitely when you talk about in terms of optical fiber, where the taper has to be connected with the waveguide structure.
No, my question is deep learning or machine learning can be used in optical communication. Yeah.
I didn't work on that, sir, actually, but I have heard like some people are working on the areas of neural networks and all. But I'm not sure about that, sir, like the way it has to be used. But I've seen some paper where people talking about in terms of the optimization parameters for designing the such kind of structures, because sometimes people say, why this refractive index of this material, so why to change the properties. So if yes, if you're applying the concepts of AI and ML, where we have the predefined sets of different refractive index and the material properties, designing parameters, yes, it can be, it's possible to get the optimized parameters of the design structures. yes, we can use this concept of AI and ML here. So far, I have not used them, but I make sure that they could be used for optimization of the designing parameters for such kind of structures, sir.
Okay. Thank you, sir. And the second question is about the cryptography. Nowadays, it's full of data and it's about science, data science, and encryption, decryption, cryptography, cybersecurity, all those things. So, in what sense it is on the optical communication, the point of, because it's purely optical nowadays for connecting all those things. So 5G, 6G, 7G, all those things nowadays more going for optical. Now, my question is, in the cryptography point of view, what's the optical communications that we can use optical cybersecurity?
In the ways of, I'm not sure about the data in cryptography and all, like how it's going to be used over there, because most of the work was related to work on for designing those structures for optical communications, and that's what we find that that how they can be used for optical communications. But definitely, when you look at for the 5G and the 6G applications, definitely to connect the different the BT sessions and the BSCs for the wireless communications, they also being interconnected with the optical fibers. And you can say where the speed of you can say the latency is over the period of 4G to the 5G and to the 6G now is going to get reduced. So they need to have the high speed optical fibers and the devices which can work on those kind of networks, and so that the latency can be reduced. So I'm sure that they're going to be used for the 5G and 6G applications, but how about the encryptography? I'm not much sure about that, sir.
Yeah, hi. Regarding Karthikeyan's question, just can I interject a little bit? So this is Dr. Gautam. So what I feel I don't know, I'm not, instead of thinking from a design perspective, can we synthesize, can we think AI/ML in the synthesizing perspective? Like, can we know our what is the end goal, and can we design these structures with AI and ML? But that is predict which kind of structures will be required for a particular certain. In the sense of a synthesis problem, can we take up AI ML? Can it be done?
Yes, definitely, sir. Like when you look at for the like that's what I'm showing you here, like the parameters which are being used for designing of such structures. If we create the data sets of those kind of the designing parameters, like the way we are having, like for silicon, what are the different refractive indexes, what could be the rod radius, maybe either somewhere around 0.1 micrometer to the 0.2 or something like that. Apart from that, what is going to be the lattice constants, what we take mostly about like 580 nanometers or something like that. And if we have all the design parameters and we can create the data sets for them, and we apply this concept of AI and ML, which I've recently come across one of the paper where people says that they apply this concept of machine learning and artificial intelligence in such a way that to optimize the designing parameters of the structure. So if you have the prescribed the data sets available for all the materials and their parameters, so accordingly we can get an optimized parameter that if I use silicon for 3.47 refractive index, maybe with this radius, this much of lattice constant, this much of dielectric constant. So if I have the certain parameters, we can see what wavelength of light is going to pass through the structure, what will fit into the band gap structure. So yes, if I apply this concept of AI and ML here, yes, we can find the optimized parameters so that it will reduce our time while calculating these parameters theoretically and to get a particular wavelength of light. So yes, it will be good to apply the AI and ML here and to get the minimize the time to design such kind of structures. It can be used, sir.
Okay, sir. Thank you so much. It's a nice talk. We are happy to listen to your talk. It's very interesting talk. Thank you so much.
Thank you very much, sir. Thank you, sir.
Okay, thank you, sir, for such a wonderful presentation.
Thank you very much.
So now, in this Young Researcher Forum, our next speaker is Dr. Surajit Bose. So before going to the talk, I would like to introduce Dr. Surajit Bose. Dr. Surajit is basically from Kolkata, West Bengal. He obtained his bachelor's and master's degree in physics from the University of Calcutta. He received his PhD degree in nonlinear dynamics of specialty photonic crystal fiber from CGCRI Kolkata, that is Central Glass and Ceramic Research Institute. Presently, Surajit is currently a postdoctoral researcher at the Institute of Photonics at Leibniz University, Germany. His research interests include quantum photonics, light sources, nonlinear optics, solitons, supercontinuum generation, photonic crystal fiber, etc. So now I would like to invite Dr. Surajit Bose to deliver his talk.
Hello, good afternoon, everyone. Thank you for the kind introduction. Although it's good morning for me. Can you able to see the entire screen?
Yes, sir. Sir, can you make the PPT in?
Yeah, I am trying.
Full screen mode.
That's why I'm asking. Yeah, but it sometimes gets stuck. Yeah, I think now it's working.
Yes, sir. Now it is.
Yeah. Once again, thank you for the organizers to give me an opportunity to give a talk here. So my topic is to color pulse compounds in different optical systems. Well, this topic is the work is based on mainly simulation based work, and let's start. So my outline contains the basic motivation. Well, I would say this motivation is not for this particular work. Its motivation is mainly for this simulation based work, why we are interested to do these things. And then I will go with some introduction, because before going to the topic, I think since the audience is a kind of broad one, so I would like to give some introduction of about my topic, that's why I choose nonlinear Schrodinger equation, and then about solitons, and then about dispersive wave. And then on the next part of my topic, I would go to these two color pulse compounds, where we see that whatever we will show in the first part about solitons and dispersive wave, and then I am going to show about their interaction, and in one of the special case I would show about soliton molecule, and then this can be explained through this kind of trap state, and finally one example of about some specialty optical fiber where we can also see this kind of trap state, and finally we are going to summarize with an outlook. So the main motivation of about computer simulations, well, I find that in many cases that if you have a say complex system, and it's very difficult to get analytic solution for this complex system. It's not that difficult, and it's also that if you have some equation, we need to approximate certain parameters and make the equation simple, and then we got analytic solution, and then we missed a lot of information. Then obviously for these complex structures or complex systems, we have definitely an experiments, but there also lies some difficulty. Like I also did some experiments, and while doing so, I understand that for experiments also, like controlling the parameters is very difficult, or maybe all the parameters is like if you have some say 3 or 4 parameters, and it's difficult to control all the parameters, and noise is another important thing which is very difficult to avoid, and if we need some new measurements stuff, we always need to change it, and it makes cumbersome and time consuming. Whereas if we do kind of some, say, I would like to call this computer simulations work is equivalent to kind of numerical experiments, where the advantage is that we can always complement the theory and experiments and also predict the new phenomena. So in one of the situation, I will show that it's already that it is how it's useful for verifying, which is already established, and this can also help to predict new phenomenon, which we did here actually. So let's start with this about generalized nonlinear Schrodinger equation. So the equation might look a bit complicated in when we see this in this form. So let me clarify that what does actually is doing. So it is solving actually an envelope or one can say an electric field. So what does this Z here actually is doing? So suppose we have an optical fiber and we launched an ultra short pulse inside the optical fiber, and we know that due to this nonlinearity and dispersion, it will change, and we would get the information of the field at every distance through this equation. So sorry, so this term actually indicates the loss. This is dispersion, and then we have some complications here. It includes this both the nonlinearity of about Carr nonlinearity and Raman response function. So the first part of my talk, sorry, it's I use this equation, and the second part is I use this, but it's not that kind of thing. One can do all the results from here also, but in some cases this non-envelope form is also important, especially when we show that in my later part of my talk, where we consider actually two pulses which are like far apart from the frequency domain, and in that particular case it is actually useful. So what does this equation do? Or let's see. So I'm trying to give a kind of general kind of things of about say solitons. So what are solitons is like, say, so suppose if you have kind of this matrices, and if we know that if the runners are moving, so after some time we will see that that's runners are spared, because some of them will travel, some of them will have a high velocity, some of them will be the slow velocity, and in this way it will disperse. And but if we can make a kind of soft material, we can make this runners a kind of confined. So similar things happens here actually when we say launch this ultra short pulse in an optical fiber. Dispersion will always be there, and that's why this every frequency component will travel with different velocities. So we will see immediately this pulse getting dispersed. But if we can adjust some nonlinearity with it by including Carr effect, one can balance these things. Balance in the sense, actually we need to choose an anomalous dispersion and also this Carr nonlinearity in such a way so that the sharp gets balanced, and we see some wave packet, some waves which remains unchanged in time domain. So let's see how we can do it with this equation. So I showed a very complex equation, and now I am showing a very simple equation. So what I did say, or any, just to avoid all the terms and see that we have one simple equation where we on the left hand side we have this propagation of the envelope, the right hand side is only have this group velocity dispersion, and we have one nonlinearity term called so when we have this, when we make this equation very simple, yes, this equation have definitely a exactly integrable solution. We can solve directly by analytic method. Then we will show that once this equation becomes complicated, that it's not possible. So I started, so this is the initial condition, or I would say the second hyperbolic solution of this equation. So I choose a simple parameter to show here what is happening here is actually. Now I will show this kind of figures all throughout my talk. So let me just clarify this, what is happening here. So this y-axis is here is the distance in, like, say we have an fiber length, and this x-axis is the time, and the other figures we have this frequency. One can solve this equation in time domain, and then one can Fourier transform it to see what is happening in the spectral domain. Now if you see this, what is happening, that there is no change, that we have a wave launched and it does not change, it remains same after this propagation. And what is going on this some horizontal white lines, so actually it is scanning all the informations, and we are here showing one spectrogram where this time and frequency information both can be simultaneously shown at a particular distance, and here the distance is changing, but you see there is no change because it is stationary. So let's see a bit complicated situation. So this is for the fundamental soliton. So next, when we go with the higher order soliton, we see that it's not remains as it is. So here the pulse gets compressed at some times, at some distance rather, and then it spreads into two lobe. Again, it compressed. So what actually changes here? It changes here is this, like there is a factor called n. Now previously it is this n is actually 1 for the fundamental soliton. Now it can be n equal to 2, it can be n equal to 3, 4, so on for the higher soliton. So for this case, actually, I choose n equal to 3 to show the effect of this higher soliton. And you see this spectrogram that it is changing kind of immediately at every distance. So let's make this equation a little complicated. So previously we have an envelope with the beta 2 is the group velocity dispersion. Now I implemented a third order dispersion. Now what is the utility of the third order dispersion? Well, this third order dispersion is important. You take any material, say for say silica, there is some zero dispersion wavelength, and near this zero dispersion wavelength where this beta 2 is very small or nearly zero, and there actually comes the importance of this beta 3. So here I choose very simple parameters again and trying to simulate what is happening actually. So we choose this as a simple group velocity profile with this zero dispersion frequencies about 10, and we see immediately that the fundamental soliton, which does not change in my previous case, it actually starts radiating across this zero dispersion point, and we call it as a dispersive wave. And this radiation is occurring not only at a particular distance, this occurs at various distance. And one can see here in this spectrogram immediately that there are two forms of radiations which is coming out. One is directly from the soliton and another is radiating. So this is actually the dispersive wave which I'm trying to say here. This is useful in one of the cases that I will show. So what we understand that we have a soliton and the soliton perturbs and it radiates to the dispersive wave. Now what happens if we give an higher order soliton in presence of this third order dispersion? Obviously that will also like split. In one of the cases I show that how this higher order soliton evolves, but due to this third order dispersion, this acts as perturbation, and this pulse actually splits into 2 or 3 components depending upon the value of n, and we see that there is a strong radiation which is crosses across this zero dispersion point, and it is also shown it here how it is happening. Now this location of this dispersive wave can be predicted analytically also by using a phase matching condition. Now this kind of equation what I showed here, or I would say the numerical benefit of this kind of equation is that they can predict the dynamics of what is happening in, say, the supercontinuum generation. So what is supercontinuum generation is we have, say, an ultra short pulse which is going inside the fiber, and we see an extreme nonlinear broadening over the output. So this picture I took during my PhD. It's in mobile. I saw it's a very beautiful moment for me. Like I launched 1 micron and light of the laser, and one can see this visible part of the spectrum. Now this kind of dynamics can be predicted through this equation. So for this, the parameters which I choose, we have a photonic crystal fiber that is having a zero dispersion wavelength at 780 nanometer. We pumped at 835, and the complicated equation which I showed earlier actually can be useful to predict all the phenomena like we see here, solitons and then splitting of the solitons, And then we see here the dispersive wave, and actually we see the interaction of dispersive wave and solitons. So my take-home message is that using this equation, one can model this type of important phenomenon. So we explained what is soliton, what a dispersive wave, and then I'm trying to show the importance of them in a different context. So we have solitons, we have dispersive wave. What happens if they interact with each other? So if we choose, or rather if we choose a particular dispersion profile, for us, for the dispersion profile is very important actually, because so if you choose two nearly group velocity matched soliton and dispersive wave, we see that the pulse collide with the soliton. So I would say this is my soliton, and this, which looks kind of spreading, this is the dispersive wave. So it actually reflects in time domain. We see that this reflection and also the transmission can be possible in time domain through this interaction. And since we are talking about nonlinear optics, so this change in group velocity is actually producing new frequencies here. And we can see easily, or rather we can see in a nice representation how this dispersive wave comes and it scatters to a new frequency component here. So the next case is that if we increase the intensity of this dispersive wave, the situation becomes a bit complex. So here the soliton remains unchanged, but here if we applied a strong dispersive wave, say for example, in the first case, I implemented like 0.02, and here if we increase the amplitude, it not only creates new frequencies, but it also disturbs the soliton. It forces rather the soliton to change its frequency also. Now, there is another method where we don't need actually two input actually, because in the previous case, what I was telling is about we need two inputs, but from the experimental point of view also, like it's difficult to get two lasers of dual inputs, and also it's not only about lasers of dual input, we need actually some condition. It's not like that they will interact and you will see this reflected components in time domain. You need to design for a particular profile and particular these things. So maybe these things can be generated by using a kind of one pump also. So all the simulations are done based on the photonic crystal fibers. So if we have this kind of fibers dispersion profile, which is realistic, is definitely realistic because I consider all the realistic parameters for that. And if you pumped it in the normal dispersion regime also, it's possible, or rather the dynamics itself has this potential, to create actually soliton out of that, and also due to the shock front, the soliton created, and one can see this interaction of this dispersive wave. And so I highlighted this portion here. Actually, we can see this thing of about this interaction. Now let me go about my topic of about two color pulse compounds. So I showed here what are solitons, what are dispersive wave, and it's possible to have the interaction between solitons and dispersive wave. Now go back to here. So let's first talk about the different systems which is already there, where people have studied this interaction of these solitons and this dispersive wave. Actually, these dispersive waves can be trapped also by decelerating soliton also. Actually, solitons and dispersive wave, we have this equation and they belong to this opposite direction, dispersion. If we think about that problem through this potential problem, usually we have a kind of repulsive potential, and that's why we see the scattering. But if we can, instead of this repulsion, if somehow people made it actually by adding a deceleration term on that, an extra term on it, which gives a kind of attraction, and then one can trap also. And there is always another method of just by using solitons as a kind of cavity, one can use this also as a trapping phenomenon. But what we did is actually we used soliton molecules with 2 frequencies to have this phenomenon, and we predicted actually in 2019, and then we started working on more about this topic, and we see recently that there's a recent experimental demonstration of this 2-color pulse compound by inside a Morlock laser, where they change the spectral profile. So what is the motivation for that work? So it was there in the literature of about temporal soliton molecules, where we have 2 bright pulses. It was in 2005. So they used actually to have 2 bright pulses which have some pi phase difference, like we have 2 bright pulses and we have 1 dark soliton here. So what they found is that, and this is a kind of double hump structure in time domain. So what they found interesting is that when they make this kind of structures close to each other, they immediately see that this, like after say we have one fiber and they put it inside the fiber, and the output of the fiber, they immediately see that it is going outward. And here when they put this a little far away, they immediately see that that goes a little inside, like the temporal separation has been decreased. And from there they like compare and they explain that it's a kind of molecule behavior. So what we did, we also utilize this stuff and make it and thinking in a like a different manner. So we also have a kind of double hump structure, but this double hump structure, instead of time domain, we have in frequency domain actually here. So we took actually that's, so what, let me also tell that what are the special things we need for in order to have these things. So we need a special dispersion profile, where we need actually 3-0 dispersion wavelength, which is again a bit complicated, yes, from the practical point of view. So we need 2 anomalous dispersion domain, and we choose 2 pulses which are nearly group velocity matched. These are the preconditions we need actually. And then we took these 2 pulses and we overlapped in time domain, but they are well separated in frequency domain. We see immediately that they are kind of very much robust and they behaves like a molecule. Why I was emphasizing on molecule? Because it's for molecule, they are like radiating, they have a strong binding energy. And when we put these structures, we see here that it is radiating initially. And then what we did is that, since we are much more interested about the interaction, we actually took 2 solitons and let them overlap and see that even after the overlapping, the structures is very kind of robust. And how we actually testified that whether they still hold these binding mechanisms. So how we tested, we actually in the from the spectrogram also one can see that they are like kind of bound, but we tested like we filter out this, say, one of the components, either it is A1 or A2, and let them propagate. We see here actually in that it is dispersed, but here we see that it is more kind of compact. Yes, although there is some extra radiation, but it is not moving as an entity. Well, this kind of, well, these things one can explain through this quantum mechanics also. So how we make our, say, equation very simple enough, and we say took one soliton and the other one is very, say, weak wave. What we say that, and if we neglect all the terms, all the harder terms, we can make this equation to a simple Schrodinger type of equation, where we can say that the potential can be explained, or the potential can be defined through this cross-phase modulation induced effective terms. So this effect of soliton was introduced in this potential. So what the weak wave feels, the weak wave will feel a kind of strong potential, and these weak states can be trapped actually. So we see here also this different kind of situations where we actually this now the potential, depending upon the frequency we choose, actually the strength of the potential was fixed accordingly. Depending upon this potential strength, one can actually find that how many number of states is going to trapped here, 1, 2, or 3. One can actually easily control or play with these things. Now, I showed in the previous thing to have this molecule and now as trapping. So actually there is a relation between these things. Actually, when we say we took one soliton and one weak wave, and then when we increase this amplitude, we see at some time at moment that their mutual interaction energy got enhanced, and due to this enhancement one can cross over from trapped states to the molecule states. Now this kind of say molecule, what I was trying to say is there are robust when we apply say different other methods, while in practical situation, well, in simulation, okay, I can say that okay, I neglect this term and I neglect those term, but in practical situations it might not be that. So we need to include every other effect and see that whether whatever we demand that about this molecule behavior, whether they will remain molecule or not. So we implemented this Raman effect. We see that obviously the dynamics definitely changes, but we still see this kind of binding mechanism is still there. So here what we showed is here that we have this say one of the frequencies around 3 and one of the frequencies we choose here. So actually when one of the subpulses is moving towards one of the zero dispersion wavelength, is actually restricts this movement. This is due to the spectral recoil effect. This is a phenomenon, that's why this soliton gets this redshift, this restricted, this movement gets, if this zero dispersion is not there, it would move more. So but there is no restriction of these subpulses, but since they are bind, so if one of them gets hindered or one of them gets restricted, the other one also feel it. So this kind of, so from that also we can say, okay, even in presence of Raman effect, the binding effect is still there. So what we find is that in both the cases, that in the subpulse, the dominant subpulse will control the behavior of the other one. Now we can see this impact of third order dispersion, which I showed earlier. So in order to understand this, what we did is actually we distributed these two subpulses. We make these two equations separate instead of having two, make it simple, and we put the third order dispersion in one of the subpulses instead of having both the subpulses. We see that okay, we have this say u and v, the u, we don't have a third order dispersion. Like basically what this third order dispersion is doing is that they are implementing, they are like the velocity is changing. Actually the group velocity is modifying due to third order dispersion. So we plot the centroids and see that if we change this one of the subpulses v, that effect can seen by the other pulse. So from there also we can say that these are the situations where we actually in real life this third order dispersion, this Raman effect will be there. So we can still say that even in this realistic situation, this molecule what we predict will be still be there. So then we start to show some kind of scattering with soliton and dispersive waves. So we can see that this kind of scattering will always be there in this situation. So we took here one, so this is like this two color pulse, actually this two color pulse is also radiate actually. So we saw then in the first during talk that soliton can radiate. It gives a dispersive wave. Here also this, even this two color soliton can also radiate, and this we can actually locate this phase match condition, and it can be also explained through this dispersive radiation, or sometimes it's called Cherenkov radiation. Well, we can use what we showed here, that it is also possible that this two color soliton molecule can also show kind of reflection in this scattering kind of phenomenon can also be shown here also. Now these kind of things, whether we can generate from say from the real point of view or from the realistic point of view. So that's why I designed photonic crystal fiber with such parameters where we can get kind of this 3-0 dispersion wavelength. So the initial whatever I showed is kind of hypothetical dispersion profile. And then here I designed the structures and trying to make all those things happen, whether it is possible to make it with a single input, because from the practical point of view, it will be easy if we have this kind of things, at least what I understand. So if you launch this say 1550, again, I choose the 1550 because this is very important related to the communication region. So if you have this 1550, and here I choose a simple parameter of about say 50 femtosecond. So what does this dynamics involves is that we launched an higher order soliton, it splits and it radiates to the other dispersion regime, say this as A2. We see that this radiation, whatever goes into this A2 region, if we actually, there are a lot of things actually hidden, but if we can separate out this dynamics, we find that this molecule kind of structures is also hidden here. Now we've plot the phase matching relation also. Now in order to emphasize that okay, we have it, what we did actually, we took the output, say we took actually this case. So this, in one of the case it is shown in absence of Raman, the other case in presence of Raman, but it doesn't matter. One can still see that this kind of this structures. So what we did is actually we took the output of the fiber and let them propagate to a longer propagation length. We see that this kind of bindness is still there. So this say for this is actually, this is not 0 matter. This is actually equivalent to output of the fiber and then give a long propagation. We see that it remains intact, it remains bound, although there are some spectrum also covering in the normal dispersion domain, but still it is there. So in order to check their bindness, we cut out one of the portions and let them propagate. We see immediately that it is dispersed. So from this also one can say that even for this realistic situation, even for this single pumping, one can create this kind of trap states or bound states, I would say. Then it can be shown that, or rather we can do, or rather we did some kind of parameter study that what will be the best pulse width of this single pump, what will be the best thing of the order where one can control this energy kind of things, energy transfer. Now we are saying that now this let's come back with the interaction stuff. So we have a soliton molecule and then we are interacting another soliton with the soliton molecule. Now what is the utility of this kind of complex thing to do? Well, one of the important utility might be that when we actually see the collision of a soliton molecule with a soliton, we see that this projectile soliton is actually compressed. So there is a compression factor, if I remember, around 1.5 or 1.6. So let's concentrate it for this stuff. Simple case first. So we have a soliton molecule and this blue curve indicates a soliton, projectile soliton, and we see after the interaction. So here the important thing what we found is that we launched one soliton here, but after interaction it goes to the other dispersion regime. So after the interaction, which we found is that there is a kind of localized radiation, and when we give a longer propagation of this localized radiation, we see that it is still the soliton. So from this one can also, that shows that one advantage due to this interaction, one can still create kind of, say, using this phenomena, we can do a kind of multiple kind of interactions, and from that one can compress this soliton also. Then let me come back to another system where we have a kind of, say, specialty optical fiber. What is the difference between this and the one which I showed here? The previously was shows here it's only silica, but now I was saying that instead of, if we have a kind of silica, instead of silica, if we have some silica with, say, metal nanometric inclusions, the advantage is that this silver nanoparticle is having a nonlinearity kind of negative, and then if we use this composite, what we can make is that similar to the dispersion profile, which we know that dispersion always has some frequencies, there are some positive and there are some frequencies that will be negative. So here also one can actually made it in such a way that at some frequencies, like say here for this particular case, which I shown, that from say 800 to 1150, this is negative nonlinearity, and then it becomes positive. So if we utilize this kind of concept, the dynamics will be kind of modified, and we will show that here what is the advantage here, that we can made two solitonic regions by having 1,0 dispersion wavelength. We see that actually by utilizing this kind of system also, we still find this trap state. We choose that in such a way that we here for this particular case, we see that this trap state is, for this case, it is n equal to 0, and then here we showed that sorry, this is like n equal to 0 and this is n equal to 1. So whatever dynamics was there, which in a conventional thing you can create here also, then the advantage is here that one can play with the solitonic regions. For this, how we choose the parameter in such a way so that both the regions are even solitonic region. So then again, this kind of this fiber, whether what happens if we utilize, or rather if we implement this Raman effect, actually we see that actually there's an interesting thing happens here. So first of all, that we took a weak trap state in the soliton, we let them propagate, that it will be robust, that at every time you see this kind of compound structures will be there. But if one take this value of like higher order trap states, that instead of n equal to 0, if we use n equal to 1, what we will find interesting is there that it starts to oscillate, and after a certain time this n equal to 1 oscillation becomes going to n equal to 0. So it will transform immediately. We can see a transition. Actually here we see actually a transition of from n equal to 1 to n equal to 0, and by taking different wave numbers, actually one can control this soliton movement. Due to this Raman, actually what happens is that soliton either decelerate or accelerate, but we can actually control this by taking this potential, whatever of the strength of the potential, like, and then in some cases we can actually also balance this thing also. Now let me summarize these things. So I started with generalized nonlinear Schrodinger equation, and then I show some things of soliton and dispersive wave, and then I showed that okay, whatever molecule we are showing is this, they are robust, and we showed some trap states and how we can create this kind of trap states. And in one of the examples, one to have about specialty optical fiber now, and what are the outlooks of this complicated dynamics. So the one immediate message is that whatever I showed the dispersion of about choosing all the about photonic crystal fiber, but it can be implemented in kind of integrated platform where we can use this silicon stuff. And also the important thing which I found recently, because now I changed my topic and now I was working in more quantum optics field. So whatever actually dynamics I showed that about the soliton, this trap state and dispersive wave. Now if this weak dispersive wave can be replaced with single photons, like if you have some quantum source, whatever phenomenon which I showed here, it will actually hold. And so I would say this is a kind of huge outlook where we can implement this technique. Yep, thank you very much for the attention, and I'm looking forward to the questions.
Thank you, Dr. Surajit, for such an insightful presentation. Now we will take some questions from the audience.
It was very nice and very wonderful. Can I go to the previous slide?
Sorry, I cannot hear.
Yeah, it was very nice talk and very interesting talk.
Thank you
so much. I have some couple of questions. Can you go to the previous slide? Previous slides.
Which one?
Previous, go to previous. Previous. You said about the Raman effect, right? Raman.
This one?
Raman somewhere.
Yeah.
Raman
Okay.
effect.
Yeah. Okay. So yeah, this one problem.
Actually, see, I'll tell you one more thing. Recently, we bought one Raman spectroscopy for maybe some 35 lakhs in my institute. Okay. So I am purely about signal person. So how can I use this kind of Raman spectroscopy and signal processing? I'm good in mathematics. I saw a lot of mathematics. I was very good. I was having knowledge about how to use the Raman spectroscopy. So can you give me some concept? How can we, whether the spectroscopic person and the signal processing person can be involved in this?
Well, how you can implement this Raman spectroscopy, that it will obviously depend upon the material you are using. So what I can comment from my work is that, say, for the configuration which actually I considered actually is like a silica photonic crystal fiber. Actually, during my although it's shown here is actually simulation based, but during my PhD, so I actually do experiments where we took a silica photonic crystal fiber with silica. So the material is silica, say, for the example, and we know that if you have the silica, we know this vibrational spectroscopy, and from that one can know that there will be the strokes and anti-strokes, and we know that from silica it is 13 point some terahertz. So that is also not important from my work. What we found is that if you implement, say, an ultra short pulse inside the waveguide, and due to this Raman scattering, what happens is actually this is an inelastic process where this high frequency component always transfers their energy to the low frequency components, and you would see a kind of asymmetric spectral broadening there. So I'm sure that if you have any material, and I don't know whether you wanted to launch this some ultra short pulse, but what I was saying that it can be of any material. If you launched it, you will see this kind of effect.
Okay. Okay. That means Raman spectroscopy can be useful only with respect to the materials, not with respect to some signals.
Well, definitely, at least for my understanding, that obviously this material is
not good in various. I was out of curiosity. I was asking.
Okay.
Yes, we bought some equipment. They are saying that they called me for a meeting, and we bought a Raman spectroscopy meter for 55 lakhs. So can we involve any of the research collaborations for the interdisciplinary research? So I was thinking, I'm a single person, I was purely about mathematics. What can I do? How can I contribute to this?
Okay.
Thank you so much, sir, for the wonderful session.
Okay, thank you, Dr. Surajit, for your valuable time.
Yeah, okay. Thanks.
So in this session, our last speaker is Dr. Rajat Subra Karmakar. Dr. Rajat Subra Karmakar obtained his PhD in electronic engineering from Chenggang University, Taiwan. He is currently working as a postdoctoral fellow in the Department of Biomechatronics Engineering, National Taiwan University. He is presently working on ECR-based tactile sensors with very high sensitivity. Major research interests are in plastic electronics, flexible electronic devices, material analysis and characterizations, development of sensor devices for different novel applications. So without a further ado, I would like to welcome Dr. Rajat Subra Karmakar to deliver his talk.
Hello. Am I audible?
Yes, sir, you're audible.
And can you see the presentation?
Yes, sir.
All right. Okay. The thing is, I will not take much time. I will have a very quick and crisp presentation here today. So without further ado, let me start. So first thing first, I want to thank the organizers for letting me be a part of it. And I'm Rajat, as I've been introduced very kindly, and I'm from National Taiwan University Biomechatronics Engineering Department, and currently I'm working on the ECR-based flexible tactile sensors. And today I'm going to present some of our basic data which we have obtained in last few months, which are titled in this slide, that is fully printed conductive ink-based tactile sensors on flexible substrate for health monitoring. So this is our goal right now. You can say that, yeah, we intend to go for the wearable applications where we can use our sensors for the vital signs measurements, or even for some novel applications. It could be, I mean, it could be anything, but let's just focus on the parts we have right now. So here is my outline. Simple. I will introduce a bit about the tactile sensors, what are these, and how we can use it, the motivation behind this work, the experimental sections, the results and discussions, conclusions, and of course, I'm going to acknowledge. And so here are the introductions. So I think you all have a very basic idea about the tactile sensors. What are these? The tactile sensors are the particular devices that can measure a given property of an object through physical contact between sensor and the object. So in simple words, let's say if this is our sensor and if we touch it, a very slight touch, or it could be a big one, it can sense it and it can transform the physical signal to an electrical one. Okay, so this could be the resistance, this could be the capacitance, this could be even there are even optical tactile sensors also. And what are the basic applications of these type? Actually, tactile sensors have been widely used in this last decade for various applications, which has a wide range, such as like health monitoring devices, robotics, especially the the human and robots in when there's some people back in Japan, I believe, there's a huge work going on. They try to give the robots more like a human touch. They can emulate our skin. Nevertheless, let's focus the flexible touch display screens, etc., and all. And there are the types which I just tell you. There are resistive tactile sensors, piezoelectric, capacitive, and optical. However, my personal interest always has been the resistive one. Why? Because I did my PhD on piezoresistive pressure sensors, not the tactile one. There is a little difference because I mean, yeah, structure-wise, there are little difference. However, I've been working on like the resistive or piezoresistive sensors or tactile sensors or pressure sensor, whatever you call it, for almost like last, I don't know, 10 years or something. So here are the basic things, like when you apply the pressure, it sends the it can sense it, and it shows the output data as a form of resistance. So when we apply the pressure, the resistance usually drops down. Very simple. That's how simple it is. And the advantage is it's a low cost and it's extremely simple. It has extremely simple fabrication technique compared to others. However, it has a major drawback that sometimes it suffers from low sensitivity compared to capacitive or piezoelectric. Especially capacitive, the capacitive sensors, they report like crazy number of sensitivity values, like more than 30 or 50 per kilopascal or something like that. Nevertheless, so a lots of work has been going on for to improve the sensitivity of the resistive sensors, or the piezoresistive sensors, if you call it. And I'm also part of the process. And here is the motivation. For the motivation, actually, if we can divide the entire pressure range, okay, from 0 to 100 kilopascal, then there is a particular range where I intend to work. This particular range, we call it subtle pressure range. 1 Pascal to 1 kilopascal. This is the range where I deal. This is the range where I dwell and I deal with particularly this area. So here, all of my sensors, the sensing range is in this area, and for the subtle pressure, it has multiple applications which can be used for the ultra sensitive e-skin or for some touch sensors, as we can see from this reference. And also, in my understanding, in this region, the ideal applications could be the wearable applications, where you can wear the sensors on your body and it can help you to gather the informations of your system. How? Let's go. We can see it soon. All right. And of course, for the motivation part, as I told you about that, I deal with this range. Of course, I try to enhance the sensitivity. And yes, I also try to use the low cost material as much as possible, because let's be real, cost is a big thing. Well, if we think in a very practical way, where you need to make the device for the market, then the cost plays a big part. So I always, right now, I'm always, dealing with or always leaning towards the low cost biodegradable substrate materials. What it is, let's see. So here is a very simple demonstration of our experimental section. Actually, our experimental section is like very, very simple. I know you are using the word simple way too much, but that's okay. So for the substrate, we have used commercially available tissue paper. Yeah, you heard it right. We made our sensors on tissue paper. So recently, what is happening, like whenever I go somewhere, if I see any paper with different textures, different, different substrate material, different substrate properties or anything, I just grab it. And I try to work on it. Like, can it be used for my work? That's how my brain right now wired. So yes, we have used commercially available tissue papers, which we use wipe the chemical waste on our lab. Okay, this is the thicker ones. So this is the tissue. So we have used the tissue paper, and for the sensing material, we have used the 2 different type of commercially available conductive ink. We have used the graphene ink, which was purchased by Uflex Corporation Limited, Taiwan, and the silver ink purchased from the DuPont, and the fabrication method was screen printing. So let's say if you put our substrate material here, and after we put the substrate material here, then we are gonna put a screen over the substrate. We're gonna put the ink, and then we use a squeegee to press the ink over the substrate, on a particular direction. Usually I do it from let's say from this way to this way. It's almost like a horizontal direction, it's like a one directional squeezing process, if I call it. And after that, I get the coating, but the coating is still raw, so I have to cure it. And my curing temperature, I always fix to 100 degrees C for 30 minutes. And by the way, for the screen, actually, you can have different types of screen. Okay. For example, if you want a particular pattern, then you can design your screen based on that. If you want, or if you don't want any patterns, you can use the blank screen. For my case, I have used the blank screen with a mesh count of 200. Okay. And here is the device configuration. So for my case, I have used 3 different configurations. I've combined the 2 graphene inks based substrates together, the 1 silver ink based, of course, and then just for fun, I kind of mix them together, something like that. Let's see what happens, right? So here is my experimental section, like mostly like how I measure the, how I fabricate the device, if I call it. And this is my measurement method. So in this photograph, if you can see it, this is how my device usually looks like. This is the how to say, the strip of tissue paper cut carefully and place them, placed together, and you can see like it's like it has like a face-to-face combination such as this. Right now it's a 1x1 device, but actually in future we are planning to increase, and we're planning not only increase, but first we want to scale it, then we want to increase it to a multiple array structure. Right now it has a 1x1 structure which has a 1 centimeter square sensing area. This is the part where we're going to apply the pressure. Okay, and we use a Keysight 344658 digital multimeter to obtain the data, and we apply the pressure over here. And how we apply the pressure? We apply the pressure using the precision balance weights. That's it. From the ranges 0 to 1 kilopascal. Here we have. So actually the measurement setup and the device fabrication setup is so simple that anywhere, if you have limited resource, you can pull this off. You don't have to worry about the very big setups or very big budgets or anything. Yeah, but I mean, if you need to work, if you are worried about like for the novel materials, because for the material point of view, yes, we are using the commercially available, but for the novelty aspects, you can have an argument like, yeah, this is not novel enough. I agree with that. But for the process point of view, you can pull it off almost anywhere. You need a very basic setup to make this work. Okay, so that's that. So let's have a quick look at the very basic data which we have obtained. So on the left hand side, we have our normalized resistance change with the pressure. So the normalized resistance, we define it by the resistance value we have obtained for all the pressure range divided by the resistance obtained at the zero pressure. Okay, so we can compare from 0 to 1 kilopascal for all these devices, and here is the thing. So you can see that device one, that is this one, the combination with a graphene. Device one, it has a quite stable. I mean, all of these have quite stable response. Let's be real. So here's the thing: for device one, actually, it has a relatively not too high, but somewhat of a high sensitivity at 0.05 kilopascal. However, at 0.5 kilopascal, it has 1.27 per kilopascal. Okay. For device 2, that is the silver ink based device, it shows somewhat of a higher sensitivity at lower pressure, but it shows it shows that lower sensitivity at somewhat of a at 0.5. So in my opinion, why this could be happening? This could be happening potentially because I think the silver-based devices, they might reach to a saturation point very quickly. And yes, there is one big thing about these resistive sensors, not just resistive tactile sensors, actually in general, the pressure or tactile sensors, they always have this nature. The sensors at the beginning, if they start from here, you have a very distinct regions. If it starts from here, then there's a rapid decay in the data in the curve. The rapid decay, then it gets saturated, and no matter how much you try, it doesn't get saturated. It doesn't change at all until or unless you change the device configuration. So that's also one thing we have to work on. So here comes the thing. Device 3, that is the combination of silver ink and the graphene ink. Surprise, surprise. We have 7.3 per kilopascal at 0.05, and for 0.5, 1.5. Well, it's true. 1.5 at 0.5 is not really that high, to be honest. Okay, let's be real. So that means like our sensor is not really suitable for the high pressure sensing applications yet, because, and of course we are not even thinking about it. We have limited to 1 kilopascal. But at 0.05, so far it looks like the device 3 gives us a better one. Now, why it could be? Now, initially, the thing is, the higher sensitivity always depends on the resistance differential. That is, if my initial resistance becomes higher, okay, then my sensitivity, which is calculated from the slope, it could be also higher. So this could be one particular reason, that is the surface, because of the surface interaction between these two samples, that is the graphene and silver inks, and also because of the rapid change of the rapid change we observed for this could be one. This could lead to this value. All right. And however, and here is the thing, when we try to apply it for the 5 cycles, five cycles data, where we periodically apply the pressure for 5 cycles, and we can see it's quite reasonable. Yeah, so far I would say it's quite reasonable for a lower amount of cycles. But however, what's gonna happen if I apply for like thousands of cycles? That's a good question. And this is something which I'm working right now, because endurance and reliability always been a key issue for these kind of sensors. All right, for a short-term goal, these sensors are great. Long-term, question mark, big question mark. And here is the sensing mechanism which we try to use. So as you have heard already, that we mostly work on the ECR based tactile sensors. ECR stands for electrical contact resistance. So in simple words, the interaction between the two interfaces, or two substrates. Sorry. So if this is the substrate, and if this is the film which we have screen printed. And by the way, one thing we have to understand, for this case, if the film is rough, it is good. It is good, no matter how deformed it is, no matter how rough it is. Rougher is better. Okay. So initially, let's say we put the film together like this, and then what we have, because of the rough surface, these contact points you can follow here, it is less. The number of contact points are less. So in a very simple argument, like the charge carrier conduction between these two conductive layers is less. Okay. Now, when we apply the pressure, when we apply even a slight amount of pressure, then what happens? The number of points are, they almost like they multiply with, I don't know, 4 or 5 times. Sometimes it depends, but they multiply nonetheless, and that's why we have a change in the normalized resistance value in my previous slide, if you remember. Okay, so that's how it's gonna happen. Now you may ask how you are supposed to change the surface properties, how you're supposed to change the surface properties and make it more rough. Since I've said like rougher is better, there are multiple ways. Either you can use the different type of substrate materials, such as for example, I've used the tissue papers, or you can use some other treatments to make it even more rough. For example, there are some works I remember they used to do something like, they used to pour PDMS over the sandpaper, and they peel it off so they can have a very rough plateau or very rough surface over, something like that. And also if you try to fabricate a device with a composite materials, and based on your composite materials, the filler size and the filler properties, it can also influence it. And yes, based on that, yeah, that part, for the composite part, we also published one paper this year in Sensors and Actuators, a physical. Though I didn't put any details here, but if you want to know more about it, you can contact me. I can provide you the details. And here are the applications which I tried. So as you I think remember that I told you about that we are working, or we are more interested in the wearable applications. So for the wearable applications, there are several parts which I was interested. For example, like if for example, the tactile sensors which I've used here. Okay, I wear the tactile sensors on my wrist. Okay, and somehow, one way or another, we were able to find the pulse rate in this, though this part is quite debatable, because I feel we need to work a lot to get a stable response for the stable response for the pulse rate monitoring using our tactile sensors. However, it is quite successful when we try to find out about the muscle movement detection, such as this, or for example here, for the vibration detection during our speech, or you can say like speech patterns, if I call it. For the muscle movement detection, for this case, it was where in a arm wrap. Okay, and it was attached to an arm wrap, and it was worn in a during on our bicep area. And when we do the flexing, it can sense the muscle strain. And actually, we have also tried this same phenomena, and we tried to showcase another application where we can detect our chest muscles expansion and retraction during our breathing, to find out exactly how about the breathing pattern. So the muscle movement detection was it was there. This much I can tell. And also, this one is particularly one of my favorite applications, the speech pattern or the vibration during our speech, detection. So basically, when we speak, and even if you, no matter what, you guys can understand that when we speak, there is a particular amount of vibration we can generate, right? So if we attach our sensor over here, as you can see in this slide, and when we speak, during our speaking, then we can also then there is a particular, then this vibration, it affects the sense, it affects the interfacial layer of the sensor, and that means we also get the response here. So here nothing is happening, I'm silent, and then when I start talking, then it goes down. The data goes, the normalized resistance value goes down, and when I stop, it goes back again. So that's how I kind of try to pull it off so far. So I will not take much time. So here's the conclusion. So indeed, yes, we try to we are still trying to fabricate the low cost fully printed tactile sensors, and we do and we use the electrical contact resistance variation mechanism. And to be honest with you, if we can pull this off, then probably in future we can have a very cheap alternative for the for the wearable devices which we have in the market right now. The sensitivity of 7.3 per kilopascal was achieved. Now it was further used to detect the vital signs, though I believe we have a long way to go. and the future works, the wearable sensing applications in a more detailed way. Why I'm saying this? Because because right now our sensor is still not packaged. The packaging is a big deal here. This is our like future challenge. For in future, I need to work on the packaging, because if we do the pre-packaging and the post-packaging, data will be totally different. There will be some changes. So I need to work on that. I need to also work on the circuitry part. I also need to work on the data, the data acquisition and showing the data, in a mobile device part. So we have a long way to go. This is only the tip of the iceberg, to be honest. And since I joined this lab on 2020, and I started this work on 2021, so you can say like, yeah, there are some progress we've made, but those progresses are mostly based on the device aspect. Like, I mean, the sensitivity enhancement aspect, finding out the new application, and also figuring out how to use the low cost materials. Both the substrate and sensing materials for this work. So this part we have made some progress, but still we have a long way to go. And as I told you, this work is only the tip of the iceberg. We are only getting started. And of course, for the acknowledgement, yes, this one was supported by, and actually all of our work is supported by National Science and Technology Council Taiwan under the grant. And yeah, this is my present, actually not in my present group. My present group is quite different right now. But yes, that's all from me. So if you guys have any questions or any suggestions or anything, feel free to ask. Thank you.
Thank you, Dr. Rajat, for such an informative session. So now from the audience, any question?
Hi, am I audible?
Yes.
Yes, thank you. There's really a nice talk
Thank you.
and very informative one. So I just, and we are running short of time, but thank you. You concluded
Yeah, I
in
know
time.
time is a big thing.
Yes, no, we had to wrap this up. The
Yes.
sessions. So now I will ask a very quick questions and very generic one.
Yes.
When we talk about medical devices,
Right.
one thing which comes in my mind is reliability. So since let's
Yes,
say
exactly.
we are seeing DB
A good one.
monitors,
Good one. It's a good
from,
question.
let's say even for decades or more than that, it's there in market, commercially available. Still, people are reluctant. Now, obviously, it's coming up more.
Yes.
Reliability has somewhat improved. So, so what can I say is like any medical devices takes a lot of time
Yes.
to
Yes.
make it a reliable one.
Right.
Doctors, to the community, and to the society.
Yes.
as well.
Yes.
So,
Yes, totally.
so what do you think? How can we make this challenge yet? Regarding your device or any device, so what should be? Because I don't think with more data, without more data, and that more data will be again, and that's again a problem. So unless people start using, we not have more data to say that okay, so this is very much reliable, and to have more data, you need to make people use it. It looks like a chicken and egg problem. How to break it?
Well, I think we are still far from that, the way I see it, because see, when it comes to my work, my device, actually, reliability is a big issue, especially when it comes to the flexible sensors or flexible devices. Whenever you are, as I told you, pre-packaging, post-packaging, data changes, right? So so I need to do it like multiple, like at least like hundreds of times, hundreds of times I need to try it to make sure that it works, and I need to make sure that the data is consistent. But does it mean that it's reliable enough? Not. Lab environment and the real environment is different. right? I'm trying on myself. I'm trying on my lab mates. That's different. But for a patient, this could be totally different, different thing also. So when it comes to medical devices, as I did some work back in my PhD days, you know, and when I was studying about the how to say, the FDA approval. Yes, yeah, FDA. I was writing a project about the FDA approvals and all. The way I see it, I think we still. I'm not totally sure how we can make people believe, or how we can make people more, you know, make them lean towards the self monitoring part. But I can tell this much: probably we need an affordable solution. One, that's why I'm always emphasizing on low cost device, quote unquote. And also another thing, probably we need more, I don't know if should I call it transparency between the data, the trials, so people can trust. Probably trust is a big issue for the common people, right? So if we can make this work in this way, like okay, we have enough trials. They don't have if they want to know the data, fine, whatever, but not the confidential one. But at least we have enough trials to make things work. So if we can make them trust, at least, probably we may break the mold, and people can lean towards more the self monitoring part.
Yes,
but still
yes, I think that should be the target area, and I think if it is printable, then definitely it is towards that way only. So yeah, so I think the computation cost at least we can tackle.
Yes.
Thank you. I think.
Good morning, everyone. I am Dr. Atun Wag, currently a research professor at Songyungan University, abbreviated as SKKU, at Republic of Korea. Today, I am going to present my current research on stretchable gas sensor for body attachable wearable electronics. So, okay. So this will be the outline of my presentation. At first, I briefly introduce the requirement of wearable gas sensor, and then the experimental design of, At first, I will briefly introduce the topic, and then the motivation behind designing the stretchable and wearable gas sensor, the experimental results, followed by results and discussion and summary. So at first, we should ask why we need wearable sensors, and then the question comes why wearable sensors are needed. In the era of Internet of Things, wearable technologies are expected to become indispensable part of our life. Thus, for this purpose, wearable sensors are being developed in different form. For example, it can be laminated onto the human body, or it can be integrated onto the body on textile and other consumer products. So next generation wearable technologies involved varieties of forms such as smart clothes, watches, bands, patches, bracelets, and eyeglass, etc. So wearable gas sensor can monitor different things. For example, it can monitor different health related physical, chemical as well as biological signals. For example, it can monitor human body temperature. It can monitor pulse rate, blood pressure, muscle movement, electrophysical signal, for example, ECG monitoring, and different biomolecular labels and body odor, etc. Among them, chemical hazards detection also takes a role for monitoring in a wearable device. So In the recent times, there are highly sensitive and flexible and stretchable gas sensors are gaining tremendous interest due to their applicability in wearable electronic platform, so which can monitor environmental gases, can monitor human health monitoring. For example, it can monitor the exhale breath pattern. It can be used for public safety and security purpose. Also, using wearable gas sensor, we can monitor the quality of the food and safety monitoring. So briefly, wearable gas sensors can be classified in 3 types. For example, in clothing type. On accessory, we can also build wearable sensors such as ring type wearable gas sensor, or on body type, so which can be tagged onto the body, and we can monitor the different presence of different gases. So using wearable gas sensor, we can here we can monitor the different environmental gases for the presence of different gaseous pollutants, VOCs, humidity, etc. Human health monitoring, we can do breath analysis or body odor analysis. For public safety and security, we can detect the presence of nerve agents or as well as explosives. For food quality and safety monitoring, we can detect the food spoilage, food contamination, and food protection purpose. Also, we can use this type of gas sensors. So with the rapid industrialization and urbanization, air pollution has been increasing day by day due to fossil fuel consumption as well as exhaust from different gases, different sources. For example, industries, etc., and from the vehicles, etc. So according to WHO, about 3.8 million people die prematurely every year due to household air pollution. And in total, 7 million people are causing death due to the air pollution. So employees working in different mining, medicine, and manufacturing sectors are being exposed of different toxic and flammable gases due to emission from industrial process and application. So long-term exposure to those toxic gases can cause respiratory related disease, and prolonged gas exposure can cause different heart related problems such as in addition also the cancer, and even it can cause stroke. So why we need wearable gas sensor? Because we in a urban or semi-urban area, we do have the pollution control authority, which usually feed air pollution information in a billboard, but we do not know that that information is actually gathered on a specific position or specific area, but the information is not specific to a human being. So even if the gas pollution level is not that much high, but in a particular area it can be higher. So acquiring location and time specific gas pollution information is very crucial nowadays, because with the high exposure of toxic gases can cause severe even death. So we need to monitor the different toxic gases or other gases presence surrounding us. So there is a huge thrust to develop a low power, low cost, miniaturized, highly sensitive gas sensor, which can be wired onto the human body. So if you see the structure of a gas sensor, it usually consists of 3 things. One is the sensing material, another is the transducer, and last is the substrate, which plays actually decisive role while we designing the gas sensor. So there are typical substrate available in the research field. For example, polymeric substrate, PI, PET, and etc., PDMS, textile based as well as paper based same substrate are being used for stretchable gas sensors. And in case of electrode, it can be of metal or 2D material types. And for the sensing material, we can use the carbon nanomaterial, conductive polymer, 2D nanostructure material, etc. But while we thinking of the wearable sensor, so among those substrate which are being used has different advantages and disadvantages. For example, PI is highly flexible, but it has poor stretchability. So for wearable electronic application, it is not suitable. And the commercially available silicon polymer, for example, PDMS, is highly stretchable, but it has other disadvantages. For example, poor metal adhesion. So for making electrodes on the PDMS is a little tricky. Researchers have been used textile type substrate also, so which are basically flexible and wearable, but due to the surface toughness problem, stability of the thin film deposited on the textile substrate is not good. And researchers have been used also the paper type low cost substrate for developing wearable or flexible sensor, which is basically eco-friendly, low cost, but it has also suffers from the surface roughness, and due to the hygroscopic nature, it absorbs humidity, so which also take effect the sensor response. So recently, our group have been fabricating different substrates for wearable electronics. Among them, two are being displayed here. So one is we did the surface engineering of the elastomeric substrate. So we call it mogul pattern elastomeric substrate, which is basically inspired from a mogul surface, which is actually formed during snowing in a uphill. So it is up and down. It has bump and valley type of structure. So inspired from this idea, we develop a PDMS substrate, which is which can be stretchable in which can be stretched in different direction. Even we see that in other paper, we see that even we apply huge strain, it can sustain the strain due to this is wavy nature. And also we recently also developing skin inspired substrate, where actually we embed different nanofiber inside PDMS. So we introduce stretch. One is stiff, another is stretchable fiber inside the PDMS, so that it can emit the human skin nature. So that substrate can be attached onto the human skin, and which also displays a stable response of the different electronic devices. So next component is the conductive electrode. So as we discussed, for making a sensor, we need stretchable substrate, then the conductive electrode, then the sensing material. Here I typically shows different geometric engineering as well as intrinsically stretchable conductor and composite material. I will not discuss too much here for this talk. And in sensing material, researcher has been used different types of sensing material. For example, zero dimensional, 2-dimensional, as well as 1-dimensional nanowires, as well as metal oxide semiconductors, carbon-based material, as well as conducting polymers. So each of these material has their advantages and disadvantages. I will discuss later during the motivation. And then the transaction technology. So for gas sensing, we usually have 3 or 4 types of gas transaction technology. One is chemristor, another is chemical diode, field effect transistor, as well as electrochemical gas sensors. among these different sensor types, chemistry strip type gas sensor has a huge advantage, which is mostly used by the research community due to its simple designing and low cost fabrication, and but there is a disadvantage of chemistry strip type gas sensor, because it is basically having detrimental effect on humidity and temperature exposure. So in today's topic, I will cover chemistry strip type gas sensor for stretchable wearable gas sensing platform. So what is required, as we discussed earlier, we need for the gas sensor, wearable gas sensor, one is the flexibility and stretchability of the wearable device. And then the other requirements are the high performance. For example, response should be high, sensitivity for a typical gas should be high, selectivity should be higher, as well as the gas sensor should be highly recoverable. And another is the low power consumption and room temperature operation. Why this point is important? Because in mostly the gas sensor are fabricated on semiconductor metal oxides, which requires additional heater, so which consumes huge power. But here we incorporated different strategy to minimize that problem. So we demonstrated room temperature operation of our sensor without utilizing any heater. So this is the structural designing of our gas sensor. So we actually deposited our electrodes on a PDMS substrate, mogul pattern PDMS substrate, and then we deposit RGO, and zinc ferrite nanoparticles are decorated onto the RGO platform. So above figure shows the typical structure of our device, and the right above shows the typical bump and valley structure of the PDMS substrate, which is basically, we call it mogul pattern PDMS substrate. So why we need RGO? RGO has a huge, large specific area. It is highly sensitive to NO2 and other gases. It can perform the room temperature sensing, and easy surface modification is available to us. And zinc ferrite nanoparticles are being used in this case because due to the nanoporous structure, it has actually higher active sites for the gas absorption. So it can make a local heterojunction with the zinc ferrite and RGO, so which can enhance the carrier separation. So ideally, MOF derived other gas sensor are used. It has other disadvantages. For example, because it is a metal oxide, it has high band gap, and it is low thermal stability, slow response time, and also it requires a high temperature. Here we combining these two material to have low temperature operation as well as high sensitivity. So this is the typical fabrication steps involved for fabricating a RGO zinc ferrite based gas sensor. At first, we do the 3D micropattern PDMS substrate by molding the PDMS on a mogul pattern, and then we deposit Al2O3 by ALD for surface passivation, and then for depositing the sensing material, we deposit the graphene oxide on a sensing area, and then we deposit the electrodes, which is actually chrome gold, that is deposited through a shadow mask, and then we chemically reduce the graphene oxide to make it reduced graphene oxide, and then different concentration of the zinc ferrite nanoparticles are decorated at the sensing area. So here is the typical material characterization of the RGO zinc ferrite based gas sensor. In the top, to confirm the presence of the RGO at the sensing area, we did Raman analysis. So it shows typical D and G bands of the RGO So we to see the presence of RGO at the bump and valley, whether it is deposited for both the bump and valley of the PDM substrate, we did Raman spectroscopy at the 3 different locations for both bump and valley. And then the next figure shows the XRD pattern, which is showing the phase purity of the zinc ferrite microparticle powder. And the next figure shows the porous nature of the zinc ferrite nanoparticles, and the lower figure shows the HRTEM of the zinc ferrite nanoparticles, which shows the polycrystalline nature, and the typical peak from the shade pattern. We can see the fringes of the 222 plane of the zinc ferrite, and the chemical analysis is also done from the EDS. It shows the typical presence of the zinc, ferrous, and oxygen in the zinc ferrite nanoparticle, microparticle. So then we change the different concentration of the zinc ferrite nanoparticle to decorate the sensing area by changing the weight ratio of a zinc ferrite nanoparticle. So the FSM image shows the surface morphology of the sensing zone with the increasing concentration of the zinc ferrite nanoparticles. So the area coverage of the sensing material increases. So this is showing typical surface morphology of the top view of the of our sensing material. So at the first image, it shows the we can successfully deposit the sensing material on the mogul substrate, and the high resolution SEM image shows the presence of the microparticles. So before doing the other sensing characterization, we did measure the porosity information. Here typical absorption desorption test has been done by BET analysis. So we shows the surface, we have the microparticle has the surface area of 53.3 meter square per gram. Then we did the typical IV measurement to see the presence, to see the effect of the loading of the zinc ferrite. So with introducing zinc ferrite, the current decreases. And then before going to measure other performance of the device, we did typical response absorption desorption curve for with exposing different concentration of NO2. So here this graph shows response curve of RGO zinc ferrite based gas sensor with different concentration of zinc ferrite nanoparticles with exposure of 2000 ppb NO2. So with the NO2 exposure, we can see that there is a change in the resistance, and when we purge the air, so it is fully recoverable. So, and the lower figure shows the band bending effect of the RGO zinc ferrite when it can make a heterojunction. Then with the exposure of the NO2 gas, how it varies. It is showing the band bending effect and how the current changes, which is displayed here. So here shows the typical dynamic response of RGO zinc ferrite based gas sensor for different concentration of zinc ferrite. So with the increasing zinc ferrite concentration, we can see the response increases until 1% zinc ferrite, and also the response time decreases with the increasing concentration of the zinc ferrite nanoparticle, as well as recovery time decreases with the increasing concentration of zinc ferrite nanoparticle. And this shows the typical dynamic response curves for zinc ferrite nanoparticle and RGO based gas sensor for two range. We did the sensing performance from 150 ppb to 4000 ppb, as well as 50 ppb to 2000 200 500 250 ppb. So we see that with the increasing concentration of the NO2, the response increases from 50 ppb to 4000 ppb. The lower graph shows the typical response curve, and this is also showed that with RGO zinc ferrite we get better response than only RGO type sensor. So for typical gas sensor, we need to also study the sensing performance of the repeatability study is highly needed. So for repeatability study, we do two type of experiment. One is for the 150 ppb, another is for 50 ppb. So we expose and then the sensor for 5 times with 150 and 50 ppb of gases. So here we can see that our sensor is highly repeatable. So in both in case of RGO and as well as RGO zinc ferrite based gas sensor, but with the introduction of the RGO zinc ferrite, the sensor response increases. Long-term stability is another issue for typical gas sensor. So we did a long-term stability measurement also for 20 days. So here the lower graph shows the typical response recovery curve for different concentration of the gases. Here we see that with the increasing concentration of the gases, the sensor response increases, but with the number of days, the sensor performance little bit deteriorates, but still it shows a good response for a low concentration of NO2. And this graph shows typical repeatability study for day 1 and day 7. You can see that it shows highly repeatable and stable behavior. For gas sensor, another important characteristics is the base resistance. So here we see that our gas sensor base resistance is also stable with number of days. Until 20 days, we see that even 0.3% of variation of the resistance base resistance. And this showed typical measurement of 25 gas sensor independent measurement we did for low concentration, that is 50 ppb, and this shows the response distribution with the number of sensor. Here we can get that for a typical gas sensor, it has around 23.7% increase in the resistance. So as we discussing we are interested to fabricate the wearable sensor. So study of the mechanical performance is another attributes which should look for. So this shows the typical gas sensor. Here we inside the chamber we applied the tensile strain until 30%. So this graph shows the sensing behavior with increasing concentration of nitrogen dioxide gases. So our gas sensor shows a stable response until 30%. Another is the cyclic stretching. So usually if we wear this wearable sensor, it is actually being stretched and unstretched repeatedly. So that is why we did the in situ cyclic stretching also, and then we expose to different concentration of the gases. So this shows that our sensor also stable even until 1000 cycle of 10,000 cycles of the stretching and unstretching. So here we also did the cyclic stretching experiment until 10,000 cycle, and we measured the response and recovery for 50 ppb repeatability, and we see that our sensor shows stable response even until 10,000 cycle. So this is typical stretching and after stretching behavior of the sensor response. One is with the increasing gas sensing gas concentration from 52 to 50 ppb, and this shows the 50 ppb concentration response with the number of cycle. So here we can see that with increasing concentration, the gas sensor response increases, but with the increasing number of cycle, the response decreases. And here we can see that with the increasing number of cycle, the sensor response decreases, but we can have the almost stable response for typical 5 cycle exposure of the NO2 of 50 ppb. So another attributes for sensor is to study the sensing performance under humidity. Humidity has a huge role in sensor performance. So we exposed our sensor we did measurement for zero humidity as well as 80% humidity. You can see this curve shows the typical response and recovery curve until 80% humidity, and we can see that with increasing relative humidity our sensor is deteriorating, but it shows still stable response. So we think that we can utilize for practical application too. So then we did our for checking the sensor response under ambient condition. We did a demonstration experiment also. We attach our sensor onto the human hand, and then we expose the sensor to 1000 ppb of NO2 under normal ambient temperature as well as ambient condition. We can have a good response and recovery behavior, which attributes that we can wrap it on the human skin and we can go get the sensor response. Okay, I'll skip this. And then selectivity is another critical parameters for practical application of the sensor. So we evaluate the selectivity of the sensor. Here we can see even with the exposure of 50 ppb gas and other tested gases are SO2, NH3, acetone, and acetic acid. With higher concentration, they are showing lower response, whereas for NO2, it shows very high response with respect to the other gases. So we can say that our sensor is very highly selective to NO2. So we also compared our sensing performance with other stretchable gas sensor. In our sensor shows highly sensitive and low limit of detection, so which is highly required for development of the sensor. So in conclusion, we developed a highly sensitive, selective, and mechanically stretchable NO2 sensor. So we introduced MOF derived zinc ferrite microparticles along with the RGO sensing layer, which shows room temperature operation under stretchable electronics application. So we introduced 3D micropattern PDMS substrate, which is actually highly stretchable, and it shows high stability of the signal under mechanical stretching, even up to 30% of the tensile strain. So due to synergetic effect of the RGO and zinc ferrite microparticles, we can detect NO2 even until 50 ppb concentration, which is quite low. So it shows superior sensitivity, response, and recovery compared to the RGO sensor. The sensor exhibits good selectivity towards NO2, long-term stability until 10,000 cycle stretching, and great repeatability and stability under humidity condition also. So the sensing performance of the gas sensor can lead to potential application in future wearable electronics. But before I conclude, I think there are few challenges remain. So one is the power. If we can integrate the power source to the wearable circuits, that can also good attributes for sensing application, and it should have high stability under normal ambient. So that are the two attributes. So before I end, so I would like to show our recent development in our lab. We are basically developing 2D nanomaterial based heterojunction gas sensor for different combination. We introduce 2D 0D, 2D 1D, and 2D 3D. We are also aiming to develop 2D 2D, which is under revision. And I would like to thank our dean of the school for allowing me to present this work, and other researchers who are working with me. And my funding agency, the National Research Foundation, and Sangyungan University Advanced Material Technology Research Center. Thank you for giving me opportunity to present my work here. I am open for question. Thank you.
Thank you, Dr. Atanu, for your valuable time and for such informative session.
So today I discussed quality of service over multipath routing in software-defined network. This paper is recently published in IEEE Transaction of TNSE. So this work was done by one of my student, Priyanka Kamboj. So before discussing about this topic, I want to introduce my group and the area where I am working. So currently I have 5 PhD students. So 2 of them recently submitted their thesis, and one of these 5 students, she is now in Alberta, Canada for his doctoral. She received one OBDF fellowship, and 2 students are currently working under me in. So one of Dr. Abni Vyas already received PhD degree in 2021 in wireless body area network. Neeraj and Amit, they both received MS degree. Vivek is working on vehicular ad hoc network. Priyanka is working in software defined network. Today I'll discuss her paper in this talk. Vidushi is working in blockchain and Internet of Things. Sweta is working on air pollution detection using machine learning technique, and Shruti has just started research in IoT, Internet of Things. So these are the outlines of my talk. So first we'll discuss some of my research area that I am working now. Then we'll discuss the software-defined network and how the software-defined network is different from traditional network. We'll discuss architecture of SDN network. We discussed one problem and application of this SDN. So first is that what is wireless body area network? My first student received her PhD degree in wireless body area network. So here what we work, we attach some sensor on the body of a person. So suppose in this first picture, I have attached some of the sensor nodes in the body of the person. So you see that generally this wireless body area network, we generally attach the sensor on the body because sometimes also we implant the sensor beneath the skin of the patient. So it is always easy to implant sensor on the body of a patient. And if suppose I have implanted here 8 to 10 sensor, and when the person will walk, this position of this hand will change and the sensor position also will change. So this changes the topology of the network, like the sensor position of this network is continuously changing while walking. If a person is walking, suppose this is a patient and we have attached the sensor on the body of a patient, and because the person is walking or the patient is walking, the sensor position changes continuously. So the already developed or proposed protocols for wireless sensor network is not these algorithms or protocols which are developed for WSN. These are not suitable for this wireless body area network because the sensor which we attached generally on the body of a patient, these are very small. The range are very small in this type of networks. So generally those protocols will not work for this wireless body area network. So many protocols also developed for this type of network. We also developed some of the protocol, and generally in this wireless body area network, it supports 2-hop communication. Either it supports direct communication to the coordinator node or the mobile node. Generally the mobile node or smartphone, maybe laptop laptop can be act as the coordinator node in wireless body area network, and they transfer those information to this. All the sensor node receive information from the body, like I'm suppose attached one temperature sensor or heartbeat sensor. So the heartbeat sensor will sense the information from the body of the patient and send those information to the coordinator node. So generally this, while sending information to the coordinator node, it supports either 1 hop distance or it supports 2 hop distance. So suppose if you'll see this picture here, the quality of signal degrades in sleeping human postures, I have written. So why quality of signals degrades in this posture? One is, suppose I have attached one sensor node on the heart, like near the heart of a patient. So if the patient is sleeping in this position for longer duration of time, and the sensor is trying to send the information collected, the heartbeat rate or some of this patient or any information from this patient, it will obstruct. So the signal will not reach directly to the coordinator node. So if you'll see this picture, we have collected some samples. You will see that some of the links are broken links. But this when the sensor node and the coordinator node are present on the same side of a patient, like suppose same side means this is the coordinator node and this is one sensor node attached. So they are present on the same side of a patient. In such a case, you will not see any broken link. But if the person is while walking, if the person is moving head to the back side, you will see some broken link. So to solve this issue, we proposed 2 or 3 solutions, and another we also did one experiment with that a person is sitting on a chair. We have attached some, if for this case we have used LSB mode, we have attached that LSB mode on the one receiver and one transmitter. So this is the, like suppose the laptop is like receiving the signal, and this is the transmitter, this is transmitting signal to this laptop, and we did this experiment like with human subjects here, and we published this paper in Smart Health. So next research area is, like I'm also working on Internet of Things and blockchain. So first one work I want to discuss that this we have implemented in our CSE building, computer science building. Here this CSE building is centrally controlled, like you can control the temperature of the all rooms and building centrally. So what happens sometimes in some of your rooms, we have like very low temperature, and in some of the rooms are very high temperature. So what we did here, we try to like keep many sensor nodes in each of the rooms and on the staircase on different floors and check the temperature. But while checking the temperature, sometimes it happens that some of the nodes are not working. So we term that those nodes as defective nodes. And how can you identify if a node is not working in that rooms? That we can identify with the help of, like if you have Wi-Fi connection, or if it is a centrally connected, and or if the range of these nodes are covered connected, the range of this node are in the range of the server, then we can directly identify that this node is not working. But here we have used multi-hop communication, and the range of the sensors are not directly come in contact with the server node. So we use Bluetooth communication, or also you can use this Wi-Fi communication, and we try to identify which node is not working sitting at the server side, sitting at the server. So in this work, we detected the presence of defective IoT node in real time. So we did another work like real-time vehicular air pollution monitoring, we did another work also real-time vehicular monitoring system. And also we are working on the blockchain. Suppose like we have used many IoT devices, and these IoT devices are connected in a smart home, and the smart home is transmitting some information to this cloud. So while transmitting information to the cloud, any intruder can listen whatever information we are transmitting to this node. So in such a case, like you can we use this blockchain and we prevent this. The next is we are also working on vehicular ad hoc network. In vehicular ad hoc network, if you see that here we have one RSU, roadside units, and all these vehicles are connected to these roadside unit. So when all these vehicles are connected to these roadside units, they are requesting some information to this roadside unit. Maybe it may be the traffic information, that whether the road is jammed or not. So if you'll see that in the second figure, this is one RSU1 and this is RSU2. The RSU stands for roadside unit, and these vehicles are requesting some data from this roadside unit. So this roadside unit is overutilized and this roadside unit is underutilized. So the battery power or the energy supply for this roadside unit will die faster as compared to this roadside unit. So we try to balance it, and we solve this issue by clustering similar interest, and then we are we provide the answer of the requested data from the RSU. So next is we'll discuss about the software-defined networking. So why do we need software-defined networking? So what is the need of a new architecture? So generally in our traditional network, this hardware and software are bundled together. So the hardware and software are bundled together in traditional network, and devices in this software-defined networking are not function specific. So are not function specific. Like suppose I'm using one smart camera. So I have to download all the software for this smartphone is different. And if I am using one suppose smartphone or smart camera or washing machine or any other IoT device I'm using. So whenever you are downloading any information from the traditional network, we need that software, and it is that device specific. So each device has to be configured individually in case of the traditional network. So we do not have any centralized management in case of the SDN. And sometimes we need high bandwidth demand, and some application needs low bandwidth. So these requirements we cannot fulfill this requirement using this traditional network. So because of that, the software-defined networking is developed, and in software-defined network, each device has to be in a centralized network. Each device has to be configured individually in a traditional network or centralized network. Whereas in case of SDN, it provides programmability to the network. You can, like here, if you see that this is device specific, so we need specialized application, we need specialized control plane for this particular device. Whereas in software-defined networking, we have a central control plane, and we have many number of networking devices are connected to this control plane, and this control plane will control all these devices. And with respect to this control plane is also handling different application. So this side is known as northbound API, and this side is known as open flow control, where we are controlling this open flow switches. So what are the main components of this SDN architecture? Generally, the main components of this SDN architecture is this data layer and the control layer. So what happened here, the main idea is to separate the network intelligence and place it in an exactly like external entity known as controller. So what is the use of this? What is the use of this controller here? Like the centralized controller, it provides a global view of the network, and it yields an improved network utilization. So the controller deploys different policies such as flow rule, a network for network devices for traffic management. Similarly, the open flow controller, this open flow protocol, it is used for the communication between the data plane and the central control plane. So the open flow protocol is used for communication between the data plane and the control plane. The SDN controller, it interacts with the flow table with the help of secure channel. with the help of the secure channel, and which is used in the open flow protocol. So the controller understands the open flow messages. This controller understands the open flow messages and to communicate and forward the instruction to the data plane elements. So in the data plane, the network devices, like the network devices in case of this network elements, the switches and routers, these are responsible for processing the packet based on the rule defined by the controller. So this is the SDN architecture, and here this application layer, we can do routing, we can provide security, we can do network monitoring, etc. So this side is known as northbound API, and this side is known as southbound API. So next we'll discuss one problem like quality of service over multipath routing in software-defined networking. This paper is, as I already told her, this is my student paper who had submitted her thesis, and this paper is published in IEEE Transaction on Network Science and Engineering. So first, one introduction, why, what is this quality of service over multipath routing? Why do we need this multipath routing? We will explain this with the help of one example. So before that, we know that the advancement of this emerging application like online gaming or vehicle to everything, for these reasons we increase the data traffic in the network. The traffic in the network nowadays are very huge. So, and every application needs demands more bandwidth for providing quality of service. So the quality of service requested by these applications, it ranges from high bandwidth to low latency, and we have to provide high reliability to this. So the present internet architecture, this is generally incapable of providing such type of things, and also it is difficult to provide this quality of service to these devices. For this case, we developed one solution. So first we'll discuss one example by how it is affected and what we did in this paper. So first is, suppose here a request is coming with a data rate requirement of 50 megabits per second. So suppose 50 megabits per second, this request arrive at switch A. So whenever 50 megabytes per 50 megabits per second, this data rate is arrive at switch A, we cannot provide we have three path 1, path 2, and path 3 to the server, but you cannot provide this 50 Mbps for this for any of the path. This is 10 megabits per second, this is 30, this is 20. So what we'll do here, we will divide this, we split, single path routing is not possible here. So we have to split the traffic flows, and then we have to, for this we provide the solution is multipath routing. We will forward this packet in multipath, either in path 2, path 3, or path 1, whatever is requested. So here we have divided, maybe we are forwarding 20 Mbps to path 3, with path 2 we are providing 30 Mbps, and with path 1 we are providing 10 Mbps. So suppose this is the incoming flow, 1, 2, 3, 4, 5, this is the incoming flow. So we're sending one flow 6, 3 and 6 in this path, then 1, 4, 5 in this path 2, and we are sending this in path 1. So after, suppose we have already sent this 50 Mbps, this bandwidth, to different path. So whenever it will receive by the server, here you will receive out of order sequence of packets. So you may receive packet 1 first, then 3, then 4, then 5, then 6, then 2. But the ordering of our packet is 1, 2, 3, 5 is serial order. So what we'll do, we have to again reorder this flows. So we need one algorithm for reordering subflow. So what we did here, we first need algorithm for splitting traffic flow, then we need another algorithm for routing the subflow, and then we need algorithm for reordering the subflows. So we propose scheduling scheme to enable multipath routing, formulate mean cost routing problem, and propose a greedy heuristic approach. greedy heuristic approach here. We design a flow, we formulate a mean cost routing problem and propose a greedy heuristic approach to find the solution for quality of service routing problem in SDN. We design a flow reordering scheme for the receive subflow through the multipaths. So what we did here, we formulate our problem like this. The set of path PF for flow F is described as P1, P2, Pn, etc. The path needed for distinct flow has to satisfy the following constraint. Like suppose this F SPL represents the splittable flow, and this pi P, it represents the binary variable that represents whether the P chosen for a particular flow or not. Suppose if we will consider this, then whether I will choose this path or this path or this path for my flow. So the next is generally our algorithm, first we handle this in packet in handler, then we flow speed manager is needed, then path selector, then routing module we have implemented, and then reordering mechanism we did this. And we implement this in these RU modules application. So our first problem is flow splitting. So how we will split the flow? For that, we have associated, each flow is associated with the weight. The weight of the traffic associated with each path has been computed dynamically based on this algorithm WUV, and like flows are coming here, and random we have used one random number generator, and we have assigned that much probability, and we splitted the flow in different bucket using these weights. Then we have decided the like cost function. How can you select the routing path? So for this, we try to select the shortest path routing issue, and whenever for that we have used one cost function, and we measure the using by using this cost function, you can define that which path you will select with, and we try to select the shortest path using this less cost function. Using this cost function. So we have formulated our optimization problem. I'm not explaining this equation here. So as I said that we need 3 algorithms. First one algorithm is multipath routing path. Another algorithm we need for the bandwidth allocation. So what we did, we first try to split the flow, and after splitting the flow, we using this random number generator, we assign the probability to which path we are assigning this flow. And for that also we have used one cost function, and using that cost function, we decided that whether we will transmit this flow to which path. So this I'm not explaining again. So this is the algorithm for this, that to 3 requirement. So then next flow detection and recovery. So for how can we implement this algorithm? For this, we use this at MPLS topology and GoodNet topology, and this is the simulator. We use Mininet emulator and RYU SDN controller. We use this at MPLS topology and GoodNet topology, and we use 25 switches in this at MPLS topology and 17 switches in GoodNet topology. Similarly, we use 57 link and 31 in GoodNet. Number of flow we have used 50 to 50. Bandwidth, flow bandwidth, these are 0.30 to 0.60 kbps we have used. Packet sizes we have used 94 to 698 bytes. So what we did, we compared our proposed approach with other benchmark scheme. One is multipath SDN, priority-based, dynamic multipath routing, and also we compare it with multi-constraint optimal path, MCOP architecture. So what we have seen that our proposed approach, average throughput of our proposed approach is better than the other technology. Like we have 250 flows. So if you'll see that, if you'll see here 250 flows, this 250 flow, the proposed approach achieves higher network throughput like 7%, 18%, and 27% with this technology like MCOP, MCOP, MPSDN, and PDMR. Similarly, with this GoodNet topology. So our average packet loss, it is in percentage. This average packet loss is also like lesser in our case, in our proposed approach as compared to the other approaches in both the topology. So end-to-end delay also is better in our case. It's very less compared to the other topology. So what are the practical application of this SDN or software-defined networking? You can use this software-defined networking in 5G network. In this 5G network are broadly categorized into three aspects. One is enhanced mobile broadband, ultra reliable and low latency communication, massive machine type communication. So the proposed scheme is beneficial to support such high bandwidth requirement while considering the delay requirement. So in 5G, we generally it will provide high bandwidth requirement and it will give good quality of service. So in IoT network also you can use this SDN network. The proposed scheme, it can be used to meet the deliver diverse quality of service requirement for IoT application. For example, when you are using video conferencing, when you are using autonomous vehicle, when you are using smart healthcare system, etc. So in conclusion, we propose a flow scheduling algorithm for this multipath technology to balance the network traffic and to provide better quality of service to the end user. The proposed multipath router scheme, it reduces the quality of service, violated flow, end-to-end delay, and it increases the average throughput. So in future, you can also extend this work in different direction. Like the proposed scheme, it considers the high bandwidth requirement of EMBB application. I have shown you 3 applications. So we have our scheme is applicable to this EMBB application, but we have not considered the other 2 applications like URLLC and MMTC application. So we can extend this work to this type of application also in future. So thank you for inviting me for this talk, and if you have any question you can ask me.
Today we have a session on electronic materials and devices and optoelectronic devices and materials. In this session we have 2 invited talks, Dr. Ravinder Jha from IIT Guwahati and Professor Venugopal Sir, Director CSR and MPA, and we have 3 more contributed talks. So we welcome Dr. Ravinder Jha and also Professor Venugopal Sir. So Dr. Ravinder Jha, he earned his PhD degree from IIT Kharagpur, India in 2017 while working on transient metal like chalcogenic based humidity and gas sensors. And then he moved to IIC Bangalore for his postdoctoral work in 2018, while he worked on advanced functional materials for sensing application on silicon flexible platforms. He joined CSIR Pilani, India in 2020 as a scientist in nanobiosensor groups, while he worked on industrial projects like development of non-dispersive infrared-based sensors. He is currently an assistant professor in electronics and electrical engineering department and associate faculty in the Department of Design, IIT Guwahati, India, where he established senior research group in 2021. So he has also published more than 35 peer-reviewed articles which were published by all the major publications like IEEE, ECE. So we welcome Dr. Ravinder Jha, and he will give a talk on current challenge in solid-state sensors. Thank you. What do you say?
Thank you. I will probably sit because we don't have much audience. So is that fine?
Yeah.
Okay.
Volume is maximum, so it's audible.
Yeah.
What do you say?
Thank you so much. I'm really disappointed with the audience. Right? Very less people are there. I was expecting at least yesterday, whatever people were there at this time. but it's fine. Okay. So I wanted to discuss on current challenges with solid state sensors. And I saw that mostly master's students were there. So I made the slides in a very basic manner. Okay. So just to introduce the sensors that we work on, basically solid state sensors based on our sensor elements like smell. Okay, so whatever we smell, the body has a sensory receptor, then we have sensory, and then it is processed in the brain. Okay. Similarly, the sensors that we develop has two different elements. One is receptor and another is transducer. And then amplification and pre-processing happens, and of course the computer processes very much. Okay. So we use gas sensors for various applications. Smart cities, farming, homes, everywhere you need gas sensors. Okay, but we are interested particularly for non-invasive disease diagnosis, for example, if you consider a gas, ammonia, in your breath, a healthy individual has ammonia of range, say 150 ppb to 500 ppb or so. But if the person is suffering from some disease, for example, if he's suffering from gastric diseases or say liver disorder or say renal problem, okay, the level of ammonia goes up, and these conditions are, these situations are very similar for diabetics, where the biomarker is acetone, and for healthy people it is less than 1 ppm, and for unhealthy it increases to say 1.8 or so. Okay, so these are different diseases and their biomarkers that I have just summarized. Okay, to introduce this sensors, IUPAC has fixed one definition. Very soon IEEE will also define it. Okay, so it is nothing but it has it performs two basic functions: a function to recognize a particular gas species, and another to transduce the gas recognized by the receptor into the sensing signal. So basically it has two very basic elements. If I'm not talking about the circuit element, the transducer and the receptor. If you go in detail, the receptor itself is a transducer only, but let's call it receptor. Okay. Then if I classify the gas sensors, this is the 6 different categories that I can classify. Of course, there can be others also, but we work on this type of devices. Okay. So if I'm measuring, say, change in resistance, okay, we call it chemi-resistive devices. Similarly, if you are measuring the change in mass, you have piezoelectric devices. Similarly, for capacitance, optical, you have various parameters like reflection, absorption, interferometry, many things are there. Then FET-based sensors are also present in the market, as well as R&D is going on in the field, and then electrochemical sensors. Okay. Before I go in detail, let's have some terminology, because everyone is not working in the field. So quickly, I will just recap it. Okay. So when I say response, it is the change of measured signal per analyte concentration. Yes, this is something like that. Say if this is resistance RA, okay, in presence of say air, and in presence of some particular gas, it goes to say to this particular resistance value. Let me take a point. Okay. So if it goes to this point, say RG, so the response is defined something like this: RA minus RG by RG. Okay. Then sensitivity is a change of measured signal per analyte concentration unit. So it has to deal with something like the slope of the response versus concentration of target gas curve. Okay, so we do piecewise linear approximation, and the slope of this we call sensitivity. Similarly, selectivity refers to characteristics that determine whether a sensor can respond selectively to an analyte or to a group of analyte. For example, here we have shown a sensor is selective towards ammonia. Okay, so Response time and recovery time are two important parameters of any sensor. So it is the time required for sensor to respond to a step concentration changing from 0 to certain concentration value. So nowadays it has been defined as a change in resistance from 10% to say 90% or so. And same is true for recovery time as well. Okay. Then stability of a sensor is the ability of a sensor to provide a reproducible result for certain period of time. Okay, this includes retaining the sensitivity, selectivity, and their response and recovery times. Repeatability is the ability of a sensor to show a certain response value when subjected to certain concentration of analyte. And this is one example where the same gas has been subjected to 8 different on and off cycle of subjecting to gas. Okay, and you can see that the device is able to retain its feature. So these are different terminology that we use in gas sensor, and when we talk about challenges, this will be in terms of this terminology only. Okay, so these are some other terminology like reproducibility, detection limit. We don't have that much time to go through them, but just to give you an idea that what type of what kind of terms we deal with. Okay, hysteresis is important, so let me let me point it out. So it is the maximum difference in output when the value is approached with an increasing and a decreasing analyte concentration range. So you can calculate the hysteresis of a device by two different manners. One is like this, where my pointer is, and another is by approaching like this. Okay, and in both the cases, you are able to find the hysteresis, and if you find the hysteresis, you can calculate hysteresis error as well. Right. Then coming to some real results. The challenges that we face. So this is the first generation gas sensors based on metal oxide. So this is the B2O5 sheet that we synthesized by some chemical mean, and we obtain our film, not homogeneous, as you can see from the AFM micrograph. Okay. What we do is we made this kind of film on a ID, interdigitated metal electrodes, which has been fabricated by photolithography. Okay, and yes, you have any question?
Are you doing chemical vapor deposition?
Yes, you can get by chemical vapor deposition, but this is done by very simple spin. Okay. Yeah, but what you can see that these green patches that you are seeing are the thinner part, like as you are seeing, this thinner is like 100 nanometer or so. Okay, and but mostly it is very, very thick. So yeah, we have given about say 1 volt to the device, so the biasing voltage was about 1 volt, and the device was not that great. It sensed about at 350 degrees Celsius. So you have to provide, you have to have a provision to give say heat of say you have to have integrated heaters, because you have your device is operating at 350 degrees Celsius. So this is one of the challenge in solid state gas sensors, that how to bring this temperature down. Okay, so most of these metal oxide sensors are working at very, very high temperature. So this example you are seeing is our sensing is at 350 degrees Celsius, and even at that high sensing temperature, the response is not that great. So it's just about 12% at 4 ppm of S2S. Okay. Then we have tried to synthesize materials by other means also, not by liquid exfoliation. So we use microwave assisted synthesis method, where the actual reaction happens in microwave ambient. We found that this type of devices are not selective at all. If you see the histogram, you can see that the response is nearly the same for all type of gases. Okay, so it is true that, and one important thing that I want to highlight here is that sensing happens at 250 degrees Celsius. So although you are able to bring temperature down to say 100 degrees Celsius, but still you are not able to improve the response. Okay, so the remedy is particularly for temperature is to sensitize these films or to use different set of materials. Okay, so there is some more examples. So here we have done CVD. Okay, so these are some examples that we did in our lab. Okay, but in all the cases we have found that the sensing happens at 250 degrees Celsius, 350 degrees Celsius or so. Okay, I will not go in detail on these slides because the ultimate aim is to just introduce you about the challenges that we are facing. Okay, so we came up with TMDs because most of the groups in the world has been investigated transition metal dichalcogenides, which are said to be next generation materials in the graphene era because of their nature. So you can find a plethora of materials starting from pure semiconductor to say pure metal, semiconductor, metal, insulator. You name the type of material you will get in the class of TMDs. Okay, and we have done some chemical vapor deposition on sapphire as well as silicon. So this is a cross-sectional TEM of MOS2 film. Okay, so we have utilized about 5 nanometer thick MOS2 in gas sensing, and we have found that the device is very, very selective towards NO2. Okay. But the problem with this type of devices is the current levels. So the current levels are very, very low, and there is drift also in the baseline. Okay, if you can see, the change is from 3.4 nano to 3.6 nanoamp. So nanoamp, if you package your device and then say if your interface circuit is not that great, then the environment factors like change in temperature, change in humidity, that will dominate, and the signal to noise ratio will be very, very less. Okay, so the challenges with the CVD grown TMDs are severe in case of the current levels. Okay. Then what we did is we also tried to synthesize these materials by some chemical, not by vapor deposition, but by liquid exfoliation, because as you know that these materials are layered material, we can they are attached by weak van der Waals forces. We can peel off the layers by high ultrasonic waves, and we were able to get few layers of WS2 by liquid exfoliation, and the device without annealing, we have got about 79.1% change for 3 ppm of ammonia. But when we anneal at 400 degrees Celsius in nitrogen ambient, this ambient is very, very important because these materials are very susceptible to oxidation. Okay, so that they can easily oxidize to WO3. Okay, so what we did is we annealed in nitrogen ambient, and we have seen that the performance enhanced like anything. Okay, it goes to 1800% or so. We had some doubt that this device will be stable, how much stable for over the time. We did measurement after 1 year for the same devices, okay, and we have seen that the performance has degraded a bit. But a device which is not desiccated, which is lying outside, 600% decrease in the maximum response is not bad. But if you see at lower detection limits, the response has not degraded much. So it seems that TMDs possess solution, but not 100%, because then again it comes on selectivity if it is not chemical vapor deposited. Okay, We have done similar measurement with other TMDs also. We have found some advantages and disadvantages with this type of materials. I will not go in detail on MOS2 because we have already seen two different examples, one on MOS2 and one is on WS2. What we did is we utilized the advantages of first generation metal oxide based sensors and second generation TMDs, and we have tried to make hybrids out of it. Okay, and this is the chemical setup that we utilize, and we try to functionalize this exfoliated WSC2 with Fe3O4 nanoparticles. Again, this has been done in microwave synthesis. We have seen that significant significant change in the performance. Performance has enhanced, and this has been dedicated to the localized PN junctions that has formed on WS2 Fe3O4 junctions. And these local junctions, what it does is it provides new active sites which is favorable for the absorption of ammonia molecules. Okay. So similarly, we tried with the I will not discuss detail on this. But similarly, we have seen results for other 1D, 2D hybrids of metal oxide and transition metal disynthesis. Okay, so here you can see that we have grown in situ ZNO nanorods on 2D sheets of WS2. What happened actually? The broken WS2 sheets. Kinks and corners at those sheets act as a nucleation site, so we don't need to actually catalyze the reaction. It grows itself. Okay, and let me show you some results. So that results I think will be very fascinating. So just see that with ZNO we were getting very poor selectivity. It was not selective at all. For 2D material that like WS2, we have selectivity towards ammonia to a certain extent, but surprisingly, when we use this type of hybrids, we have seen that there is a complete selectiveness towards H2S. Of course, the device has other issues also, so I will not discuss them more. But because this is still working at very high temperature, say 250 degrees. So we are not able to bring down the temperature, but at least we have success at one front that selectivity has improved to certain extent. Okay, we have tried to utilize other ways also. If you remember, I have just mentioned that WS2 has a tendency to naturally oxidize. So what we did is we let it oxidize during sonication, and we have found that if I allow to oxidize it, what happens is this type of structure WS2 WO3.S2O, this type of structure is formed. And surprisingly, WS2 was sensing at 250 degrees Celsius, but this type of complex materials, actually, they are able to sense even at room temperature. But it has some issue on the front of signal to noise ratio, but then also we are able to go to say 50 ppb. Okay, that is reasonably good as compared to pure WS2. We are also trying to utilize other elemental nanoparticles like boron. We are not able to synthesize borofin till yet because it can only be grown by bottom-up approaches, and it can only be grown on gold foils. Okay, but we tried to get boron nanostructures, but the device, although it was selective towards methane gas, but it has very high hysteresis, particularly if you see at higher values of methane. Okay, so the search continues. It's not like we have got something very novel. We are still working on different materials. We are still exploring different gates. I don't know which will open. MOF seems to be a potential material. We are exploring that also. So I will not. I have slides, but I will not discuss that because I'm already running late. Okay. So we are working on breath analysis on chip humidity compensation and transducers also. We are also working on printed gas sensors. So whatever material we have seen mostly has been processed by chemical means. So it can be utilized in flexible sensors. We are working on this front also. Then collaborative research is something that we are looking at. Our group has recently hired one postdoc who is expert in DFT analysis. Then we have PhD students working on machine learning based data analysis of the sensors, sensor arrays. Okay, interface circuit also we are trying to develop. We have developed a few of them. Okay, so yeah, so these are some results on. Quickly, I will share that some of the devices that we have printed recently. Okay, then we have some DFT results as well to show. Okay, what I would like to mention over here is our group is looking for some highly motivated PhDs. Okay. So if anyone is hearing this talk, I would suggest that you apply to EPIC-2022 regular PhD programs. We will be very happy to host you in our lab. Okay, we have done some auto balancing based interface circuitry as well. Okay, so the area is interdisciplinary, as you might have seen from my slides. Why this is hanging up? I have listed out various fronts at which one can. Okay, it can be on backend electronics, data analysis, data interpretation, device engineering, okay, then computational studies on materials, flexible sensor development, okay. There is a number of fronts on which a student can work. At the same time, we are also looking for collaborators on different fronts, because we know we understand that we don't understand sensors as much as others understand. Okay, so we also want to, so we consider ourselves as student of the sensors class, and we'll be very happy to collaborate on all these fronts, and there can be other fronts also which we might have missed. So I will be very happy to collaborate on every front. Okay, so we have already discussed this, the market value and other things I will not discuss, but because you already know that this is a very, very big market, and the government is focusing on nowadays on semiconductor based devices, and sensors will find its position separately. I'm sure, because still we are bringing everything from outside. So we want our industry to flourish. Okay, these are some references, and this is our recent review article which came on the front page of Advanced Material Interface. I think if someone wants to start from basic, it will be very, very helpful. Thank you so much. This is my email ID. Please feel free to drop me an email. And if you have any question, I will be happy to take it right away. And I'm there for whole day today. So even if someone is not present and if he is interested in, say, some undergraduate student or some master's student, we can talk. Okay. Thank you so much.
Thank you. Any questions?
Density functional theory, this is the kind of calculations we do. For example, you have seen that a material was there, CTIs. Okay, I want to check that, say I don't have any experimental. Okay. I'm sitting in my lab and I want to see that if TiS2, I can utilize it for some sensing purpose on. Okay, but we had some other problems with TiS2 as well, because it was not clear from the literature that it is a semi-metal or a semi. So those things you can, particularly this gas molecules, I told you that gas sensing, for example, if I take, say if it is, I have 4 different gases, say H2S, ammonia, some VOCs, and some other gas. I want to check that if the material is selective towards particular gas. I can use DFT tools to figure out that by using some energy calculations, that this material will be selective towards particular. So once I formulate that, I can also say by calculations that if it is going to say particular material, at which particular site it will be absorbed. For example, say WH2. WH2 has 6 hexagonal atoms: tungsten, sulfur, tungsten, sulfur. It is interacting with tungsten molecule or sulfur molecule, say ammonia. It is interacting on which point, or it is interacting on some defect. So you can create in DFT your material, like your tungsten sulfide monolayers. You can put defects also, and you can do these calculations. So you don't need to go to experiment. Okay, you can do initially with the DFT, and this is a very, very strong tool, because there is no certain rule that which gas will be selected towards what material. So DFT can be very, very strong tool in that. All right. So yes, we are working on handheld devices for non-invasive disease diagnosis. So we still don't have any project on that front, but we are trying to get it as soon as possible. Okay, so yeah.
What is the difference between the normal sensor and the solid state sensor?
Normal sensor, there is no word like normal sensor. There can be various devices, like for example, it can be optical. Okay. So as an electronics person, I work on, say, semiconductor device. So if you have done, say, you have studied this undergraduate, semiconductor devices are known as solid state. Okay, so yeah.
One question, sir.
Yeah, please.
Regarding this gas sensing, so is there any single pass cell through which you pass those gas, or there's some other device that how you sense that gas? For example, you have any material, so the hydrogen sulfide, or you can talk about the ammonia, or you can talk about methane. So is there any single pass cell or multi-pass cell where you pass that gas?
Okay. You are telling that how we are doing actual studies.
Yes, exactly.
So we have different MFs, mass flow controllers. Okay, and these mass flow controllers are connected with the different cylinders, commercial grids. And we make sure that that cylinder has, for example, say ammonia. Ammonia is of very, very good pure condition. And that the cylinders are calibrated. Okay, say a particular concentration. So, say for example, I have a cylinder which is calibrated to 3 ppm. Okay. So now I will pass it through, say, MFC watt. And if I want, say, 100% ammonia, it's 3 ppm ammonia, I will use MFC watt. But if I want, say, 2 ppm ammonia, I will dilute it with the pure air. Okay. I will using another MFC, say MFC2. Okay.
Yeah. These are the input and output. You have this gas cell, for example. You're passing some signal or something like that, or like that. Sensor will like that.
How you will do measurement? That's what. Yes. You have probe data and you have simple SMU.
So why is the sensor lying here?
Your sensor is lying on, say, for example, on some chart. You have probed it. Okay. If it is in initial condition, you have probed it. And it is inside the gas cell.
Okay, it's inside the gas cell.
Yeah.
So what you're taking it out is like Is it the absorption? Is the intensity or something like that you're thinking?
Okay.
How you
So
detect that?
got it. So if you have seen, I have discussed the resistivity. Okay. So it is basically the change in resistance. So say for example, I think you might have missed it. So I have shown that response of a device. That's why I have kept the terminology first. So response of a device is calculated as RA minus RG by RG. If you remember the first definition, R is the initial resistance. Say for example, I have probed my device inside a gas. Okay, and I have given a biasing, say 1 volt. Okay, and I'm trying to measure the electrical resistance of that device. So what will happen? For example, if you talk in very practical sense, the resistance will be varying initially because it is lying in the ambient, and after say 10 minutes or so, it will catch up. Okay, so that is your RA. When you will pass the analyte that you want to sense, and if your material is interacting with your gas, okay, there can be two phenomena. One is, and it can be third also, I will tell you. But one can be chemical absorption, another can be physioabsorption that you call. It can be a mixture of physioabsorption as well as chemical. Okay. If it is not interacting at all, there will be no change in resistance. If it is interacting, say chemically, let me complete. If it is interacting chemically or physically, you will have a change in resistance. But if your resistance is not coming back to the original RA, okay, it means that the absorption was chemisorption, because your sensing material is binding with the gas molecule. Okay. So you want your sensor to recover. Otherwise, it can't be called sensor, it can be called as a capturing element.
Hi, Ravindra, sorry to disturb you, but could you please wind up? You're already off by 20 minutes.
I'm really sorry, sir. Yeah. Actually, I started interacting. I'm really sorry. Yeah.
We can interact later.
Yeah. Thank you, sir, for pointing it out. Yeah, I'm binding it. Thank you.
Thank you. We just Dr. Ravi.
Wow.
Thank you. So next talk is by Professor Venugopal. So Professor Venugopal sir, is currently a director of CSR National Physical Lab. He is on leave from Tata Institute of Fundamental Research, Mumbai. While he is a professor, his research interests on the application of nanophotonics to single photon metrology, including single photon emitters and detectors and detection methodology.
I think that should be enough, right? Okay. Thank you. Right. I'll share my screen.
Yeah. We welcome you, sir. Thanks for being here. So, what do you, sir?
Thank you. So I've not turned my video on. It's right. If there is anything, please raise your hand or say something so that I'll stop and take the question. Right. So I'll be talking about materials for metamaterials. So how do we choose the right materials? Right. So our group interests are in light matter interaction, how we can change the material properties. Sorry, there's some echo. Could you please mute? That's it. Okay. Thank you. Right, we control the material properties or the properties of the light. So that's what we're interested in. So we have been working on metamaterials for a very long time, both for basic physics as well as applications. I'll show some of these examples, especially layered structures and how they can be used for different applications. Okay. So the first example I'll show is an optical reflectionless potential. The idea here is you solve Schrodinger equation, find potentials which give zero reflection, and you solve the second order differential equation governing the wave propagation, the wave equation, and the epsilon, the dielectric constant of the medium, you write in terms of the potential in the Schrodinger equation, and then you can get different functionalities. So in this case, like, so we found the potential which gives zero reflection or 100% transmission of energy in the forward direction. So we made this structure with Al2O3 and TiO2. It took about 2 years to make. The problem was that TiO2, which we are depositing with atomic layer deposition, because these are very precise with nanometer precision in the thickness is what we wanted. So we used ALD, but then the ALD was layers for even a few nanometer thick. TiO2 was absorbing quite a bit of visible band. This is because of the defects in defects due to nitrogen vacancies or nitrogen defects within the TiO2 film. The nitrogen was the carrier gas in the ALD. So then came the question like, so what kind of materials we can use for a given type of application and what process do we use? So for this, we used sputtering with oxygen control to make sure that like we maintain the stoichiometry and get the optically transparent TiO2 films. So we showed 0.5% reflection. The reflection reduced less than 0.5%, covering 500 nanometer to 2700 nanometer in this case. So these structures we used for coupling a short pulse, a 5 femtosecond pulse into a medium, in this case a glass substrate. Because of the high peak powers, it generates a second harmonic generation. And in the process, like we also showed that these layered structure, these optical reflectionless potentials have a broadband negative group velocity dispersion, as shown in the plot D here. Right. So the short pulse actually could convert with maximum efficiency the supercontinuum generation. So in the UV region, like we got more than an order of magnitude enhancement in the supercontinuum generation. Right. So the second example which I'll show in the layered structure is a perfect absorber. So here, basically, in 2008, people have shown that one can have a 100% absorption at a particular frequency. If you choose your 3-layer structure, the top metal can be unpatterned or patterned. In this case, what they've shown is patterned or structured metal on the top and a thin lossy dielectric medium of few nanometers thick, and then a thick ground plane of metal underneath. So the idea here is that the top and the bottom, the currents in the top and the bottom metallic layers are counter-propagating, they cancel each other. So there is an electric field null in the SiO2 region in this case, but the magnetic field resonance is exists within this thin film, and that's the resonant nature comes from that. People showed broadband response. We showed much better response covering visible to near infrared regions. I'm not going to show that, but for today's talk, I'll talk about the biosensing application. So one of the earliest applications of plasmonics is to use the prism geometry, and either you change the incident angle for a fixed wavelength, or you apply white light and look at the change in the wavelength for a given theta or the incident angle. Right. So with and without the analyte, you measure either the change in the angle or change in the wavelength, and that gives the sensitivity or to the analyte which is put on top of the gold layer here. To enhance the sensitivity, people do this ellipsometric measurements, which in which like so the psi and delta are measured. These are the ellipsometric parameters, and the differential phase with and without the analyte is measured to get the highest sensitivity possible, going down to a single molecule in this case. Right. So we designed an asymmetric Fabry-Perot type structure with a silicon dioxide layer on the top, so that we can integrate a flow cell on the top, and then we flowed the analyte in it, and then measured with and without the analyte the ellipsometric parameters. And we showed that these structures, the structure need not be changed. It's only the cleaning of the top flow cell is what is required. So this is cost effective, and it goes down to 100 femtomolar sensitivity to that we could measure in our lab. Right. So we also looked at this broadband plasmonics. So one of the structures is a plasmonic quasicrystal, and its properties and applications we have shown. And this is a perfect absorber, which I said broadband structure. So there is 3 different structures. There are squares, cross, and circles, which are chosen to cover 3 different wavelength regions. And these scattering elements are randomly distributed on the surface to get broadband response of covering this visible to near infrared wavelengths. And the highest absorption which you have seen is 99.8, 0.36% in this case. Right? So more recently, we are looking at these dielectric metamaterials bound state in continuum. So just to understand, we know the potential well problem in which the electron energy levels are quantized within the well region, and above the barriers, you have this continuum of energy levels. However, if the barriers are rough, what we see is within this continuum, we have this discrete bound state, which is quantum confined. So ideally or mathematically, this is an infinite Q factor mode, which means the line width is 0. So it's not feasible to experimentally measure this mode. Right? Over the last 10-15 years, people are more interested in the nanophotonics community for this, because there are symmetry protected or the accidental BICs which are possible in the scattering or emission geometries. So if you have a symmetric particle, if you're launching light at a gamma point or normal incidence, what you see is the dipole and the higher order multipoles, they all add up to give, they're all aligned in the same direction, and then the sum of them is emitting in one particular direction. This is a bound state in continuum mode, which happens based on the symmetry. There is one particular wavelength at which this happens. The similar thing can also happen if you have a random shaped particle. In this case, the vector sum of dipole and the higher order multipoles, they all add up to give emission in one particular direction. This is known as accidental BIC. This need not, you do not need to apply light at gamma point, or the resonance is off gamma point, or you don't need to shine light at normal incidence. You can come at one particular angle where this vector sum adds up to give directional response. Okay. So as I mentioned, these BICs are interesting because of high quality factors, directional emission, vectorial nature of the BIC mode itself. Right. So we showed that like you can have the symmetry protected BIC. These are TiO2 discs on top of glass. We showed that actually these are the calculations here at the BIC, which is 0 line width or infinite Q factor. As I mentioned, this we cannot probe experimentally. However, close to the BIC, you can get these quasi BIC modes, which are very high Q modes. And as you move farther away, so if you look at the launch angle, so at normal incidence or the gamma point, you have the BIC. If you're going to off normal incidence, as you go to larger angles of incidence of light, you see that the resonance is broadening, which means the radiation is coupling to the leaky modes and is not a BIC mode anymore. So this shows a symmetric line shape. And interesting thing is, if you just shine a circular spot on these structures and look at the reflected spot profile, you see that at resonance, it shows a circular profile. However, if you go to off resonance, the square symmetry of the lattice is reflected in the dispersion profile, and the shape of the spot also changes. And this is in the far field. In the near field, you see these interference patterns, which are interesting because they reflect the vectorial nature of the mode. Right. So these are shown in the experimentally measured properties here. So at resonance, you see the circular symmetry, and off resonance, you see the square reflected spot profiles here. And The interference pattern show the orbital angular momentum state L equal to -2 in this case. So there are two rings which are coming out, and that persists for longer time or longer values of the incident angle. Okay. So we demonstrated a polarization independent BIC when perturbation changes. So for example, all the red ones are of one single dimension, and half of these, the blue ones, are modified to have a slightly different diameter. So you have monoatomic to diatomic, a mixture of red and blue disks, this atomic structure. So what happens because of this going from monoatomic to diatomic lattice is that there's a zone folding, the M prime point here, it folds onto the gamma point. So these two are two orthogonal polarizations. So because of which you see that you get a polarization independent BIC resonance mode in this diatomic lattice. Right. So we showed this experimentally for linear polarizations, horizontal, vertical, then circular polarizations, left, right, circular polarizations, and all that, and showed that this resonance persists, and this is indeed a polarization independent resonance. So to control these high Q modes, we are using these bismuth doped yttrium iron garnet disks, and with applied magnetic field, so we are controlling and trying to reach as close to the BIC mode as possible. So this work is in progress. So we made the structures and measured. These are the preliminary results, which show that we can actually go closer to the BIC mode. Some of these blue points, so that is. So you need to enhance the resolution and do better measurements to go as high Q as possible. Okay. So these are the profiles of the reflected spots. Okay. And going back to the layered structures, I'll give one example of hyperbolic metamaterial. So here, basically, if you have a homogeneous medium, the dispersion profile is given by the first expression here. Okay. So in a homogeneous medium, you have one single refractive index or epsilon. Based on that, the wavelength inside the medium is defined. So it's 2 pi over lambda. Right. So where lambda is basically lambda 0 in vacuum divided by the refractive index. Right. So once the refractive index or epsilon is known for the homogeneous medium, so the k's which are possible, kx, ky, kz, are all uniform, and then you have a spherical symmetry in the dispersion profile. However, if you make your structure such that you have the structure is metallic in one plane and dielectric in the other plane, or vice versa, so then you see these the spherical symmetry is broken, and now you have this hyperbolic dispersion profile, which means that even infinite k vectors are possible or allowed modes within these hyperbolic metamaterials. Okay. So the interest in it comes because so if you have a layered structure and with a single dipole emitter like a nanoparticle inside, so then the dipole is emitting in all directions. So I mean the nanoparticle is emitting in all directions. So these can be coupled well into the this layered structure conforming to the hyperbolic metamaterial, right? And we put a patch antenna on top to get directionality. Just to compare, if you, instead of this layered structure, if you have one single uniform homogeneous layer of TiO2 and the same dipole emitter in the center, you see that the emission is going into the substrate as well because of the dielectric loading, in spite of having the patch antenna on top to give the directional emission. These structures can be designed based on, for example, our experimental conditions. So what kind of objective and optical setup we have, we can decide the cone into which this emission happens in all. So we showed 200 times enhancement in the measurements and 40% collection efficiency in these structures. Now the problem with using quantum dots or nitrogen vacancies in nanodiamonds is that they are sensitive to the surroundings in which they are. There are two problems in this nanoparticle emission. One is called the photo bleaching. If we shine light for longer time, what we see is that there is bleaching of the emission which happens from these nanoparticles. And the second one is because these nanoparticles are small in size, the surface defects contribute to the emission properties of the nanoparticle, because of which there is always blinking. So the excited electron can get trapped in the surface state, defect state, and then can be non-radiative for longer time. And after some time it emits, and then again the electron gets trapped, so there is no emission. So there's a blinking effect which happens. Right. So these are some things which we need to take care of while making these structures. Right. So this is something which I mentioned. So if we are applying 1 milliwatt even of continuous wave excitation, so the over say 25 seconds, in this case, after 25 seconds, the emission has dropped to 0 from these are colloidal quantum dots. And similarly, like if you put these nanoparticles, and I mean sprinkle these nanoparticles or just spin coat them and then put a thin layer of TiO2 in this case, even with 1 nanometer. So 1 minute corresponds to 0.3 nanometer of TiO2, and 3 minute deposition corresponds to 1 nanometer of TiO2. Right. So even with 1 nanometer TiO2 layer, so the emission is completely suppressed. This is happening because there's some oxygen diffusion which happens into these colloidal quantum dots, because of which the size shrinks and eventually the dot just stops emitting anymore. Right. So we studied a large range of these metals and dielectrics to look at for single photon application. We need to be extremely careful about what is the re-emission coming from these, what is the scattering coming from these, which is contributing to the background photons, which will in turn affect our measurements at the single photon level. So based on these studies, so we chosen materials which are suitable for making these metamaterials, and then we also studied a range of materials like polymers, which are routinely used in the literature, PMMA and PVA, made the hyperbolic metamaterial structures with them with the single quantum dot inside them, and looked at the single photon emission from these structures. Though the blinking to some extent has improved with the polymers, the overall stability and bleaching is not good when we encapsulate quantum dots with these polymers. Right. So the best material which we found is ALD grown, atomic layer deposition grown hafnium dioxide, which preserved the stability over, I mean, we measured up to 125 seconds. So there is very little loss in the emission, and there's no photo bleaching found. And the blinking also suppressed to quite a large extent. There are certain times when the emission stopped, but overall, like, so the emission is seen continuous over a long period of time. And then we measured the single photon emission from these structures. Right. So what I wanted to say is, like, metamaterials are basically design structures. We can design various kinds of metamaterials. I showed a few examples of them. And what I wanted to stress is that the choice of materials which we use for making these metamaterials is very important, depending on the application and depending on the active material which we want to put in. So we need to choose right combination of materials. And I showed an example for single photon emission and optical reflection rays potential in this case. Okay. So just to acknowledge, these are the people who contributed to this work. The ones in blue are the ones, the theoreticians whom I collaborate with. These two are currently in the group. Abhinav has just leaving. So thank you.
Thank you, Professor. Any questions from the audience? So I have one. I'm curious about this. Will we use this instead of this? Can we use absorption also for the gases? Absorption profile. Can we use those sensors as for detecting this hydrogen sulfide? And what is the effect? For example, you're talking about this quantum dot lasers materials. Right. Can we shift? Right. What if we shift application band and then detect this hydrogen sulfide in roughly 1000 nanometers, 15,
Absolutely.
70 nanometers.
Right. Absolutely. This can be designed for any particular application, whatever is needed. Right. I showed 100 femtomolar sensitivity for biomolecules. The same thing can be done for quantum dots as well. Sorry, the H2S or any gas sensing and other applications. I'm sorry, I don't know why I said quantum dots, but yeah, too much of quantum dots, I guess. Sorry, yeah. So this is a biomolecule. We studied, I mean, 3 different molecules and showed that like we can get 100 femtomolar. We are currently looking at different other cotinine and other things which are disease specific and have real world applications in detection. Yes, I mean, this can be certainly designed for gas detectors, among other things. Right?
So one more question, sir. For example, if we are using these quantum dot lasers, can we use this for the COM generation, frequency COM generation, and then pass that COMs to get the absorption profile? Is there any reference for that? For example, if we are detecting hydrogen sulfide, there's an absorption profile at 1575. So how come I will say that this for this absorption profile, this is a hydrogen sulfide gas that we have detected? I think this will be some reference absorption profile which we can compare those profiles, I guess.
Right. So the idea which we are going with is to use SIRS, and so for example, this is a broadband plasmonic structure. So what we're doing is we put the molecule or the gas which we want to sense, and instead of measuring one single resonance, we are mapping the resonances, the Raman signals from these molecules. Right. So it's not just one single resonance where the uncertainty which you mentioned is happening. So here, by having a few of these Raman lines detected, we can get better specificity to any particular molecule.
Okay. Once again, thank the professor.
Another question,
yes.
Why these MIM structure, metal structures are used in this type of device?
Why? Because you can get perfect absorption. So basically here, if you see, this is 99.36% for one of the polarization. For the orthogonal polarization, we could get 99.8% absorption of the incident light in 10 nanometer, or I mean less than 10 nanometer thick silicon or germanium. Any layer with weak absorption is good enough to get this near 100% absorption. Right. So why that is interesting? So it can be used for sensors. It can be very good for different applications. So there is one other application which we have shown is a stealth coating. So you can actually design these for mid-IR wavelength range. So where these IR cameras work. So IR cameras work by detecting the heat coming out from the body, whether it's a vehicle or a human body. Now we can have these pixelated perfect absorber structures where we can basically each pixel can be turned on or off. And if it is on, it's absorbing 100%. So all the heat which is coming out from that body can be is suppressed. You cannot see it in the IR camera. So you can have stealth. I mean, soldiers' dresses can be made out of this to make them invisible, or you can take an armored truck and make it look like a small vehicle. Okay. So there are different applications which you can use from these perfect absorbers.
So we once again thank Professor Venugopal sir. So it's an honor to have you here, and then it was wonderful talking to sensors. Thank you once again, sir.
Thank you. Thank you. I'll be logging out.
Yes, you can.